ZK Talks, and I wanted to take this time to not only introduce the team members that have helped to put this whole experience together, but also highlight the purpose and the intention behind an experience like ZK Hub. So as event organizers in the blockchain space, something that we've started to notice over the last year is a bit of side event fatigue. Anybody who's in the room probably can see that every major conference now has hundreds, if not sometimes even 1,000 side events, like in Token 2049. And I don't think that that's a signal of a lack of interest at all, but ultimately that there is more that wants to be happening in the ecosystem. Challenges of side events is largely that most of you don't get to attend them, and there is sort of an exhaustion that comes with that. And so what we wanted to do this time around is work collaboratively with the entire industry and co-create and really be role models for what masterminding something like this could be if we wanted to work together and worked independently. So as a ecosystem, we've invited everybody in the ZK space from, you can see Kakarot, O1 Labs, which also is represented by Minna, Alio, Risk Zero, ZKM, which I mentioned, mentees, and a few that aren't on the pillows on the stage right now that include HoloNim, StoreSwift, ZK Work, and so many other contributors that are not co-hosts, but of course include Polygon, Aztec, you name it. Ultimately, we've decided as a group of event organizers and ecosystem managers to work together to solve the problem of, a challenging sort of side event and also conference experience for all of the community. So enthusiasts and builders and investors alike can come together and enjoy each other's company, learn more about what's being built in the space, and ultimately solve some of the biggest problems and challenges in ZK and beyond. We are a small community. I know it feels really big sometimes because that's all that we talk about, but yeah, in the grand scheme of things within the blockchain space, ZK is still relatively new and small and niche. And so why not work together instead of, sort of continue on the competitive nature of what could otherwise be, more prominent in the industry at large. So lots going on today. A bit of housekeeping I think will be helpful. As you know, you're in the ZK Talks room or the ZK Talks space. We also have concurrently going on programming from all of our co-hosts. And the idea behind ZK Hub was largely that we would invite all of the ZK ecosystem members to run their own programming, but in one space. And then that way, if you wanted to go and learn a little bit about Alio, you could do that. If you wanted to go and learn a little bit about Minna, you could do that. You could go and chat with some of the ecosystem projects or contributors and not have to feel like you needed to, well, especially in Thailand, it's like 45 minutes sometimes by taxi just to go 8 kilometers. And so, fun fact, I took a motor, what do you call it, a bike? A moped? A moped? I didn't drive it myself. That would be terrifying. But I was sitting in the back of a moped on a grab yesterday, and to go 6 kilometers was 45 minutes. I was just like blew my mind. And for those Americans, that's a long distance, a short distance for a long period of time. Yeah, I think ultimately today a series of things will be happening. We have the co-hosts running their own programming so you can navigate through all of those rooms. We also have a technical workshops area where you can do interactive technical learning. Some of them also include rewards and incentives like Alio's Learn and Earn that will happen later this afternoon. And of course, many of you, I'm sure I can see, have been fed and have been drinking coffee and tea. You look very lively right now. And so access to the marketplace includes booths and an opportunity for you to connect with all of the co-hosts as well as the sponsors who have joined us today. Okay, question for the audience. How many of you would feel confident in defining what zero knowledge is? Hands up. Come on, you guys. Don't be so humble. You're at ZK Hub. Okay. Well, for those of you who don't You're invited to enjoy every program, every room, sort of hop in and hop out of every room, but also to really indulge in all of the amazing food that we have catered for us today. Those of you, of course, joining us on live stream, you'll have to eat imaginatively or eat at home. And for the speakers who will be joining us, and if you're already sort of in the room preparing for that, my ask is that you join me sort of on my left-hand side, probably your right-hand side if you're looking at me, and to walk sort of around the wall and onto the stage, just so that we're not blocking any of the camera access. So without further ado, I would like to introduce our first panel. I'm so behind, nobody told me. It's on optimizing proving infrastructure. Please, a round of applause for our first group of panelists.
Hello. All right. Welcome everyone to ZK. Thank you, Annie, for the introduction. Just a warm welcome to everyone here. Today we'll be talking about proving infrastructure, the future of it. Today I have a list of panelists who all have experience in the space of proving infrastructure. Yeah, at Protocol. Leo, co-founder of CISIC, and Dr. Wu Yang, co-founder and CEO of Snarkify. To begin the panel, I want to ask a question related to the primary challenges in scaling and proving infrastructure for ZK protocols. How do your projects address these challenges?
Okay, yeah, probably like I can go for first. Yeah, so like CISIC is like doing like a hardware software combined approach to address the concerns in the proving infrastructure. So right now we are relying on like a lot of like GPU to do the proving for like our customers. Like for instance, like in the past several months, we have generated like more than 7 million proofs for the ZK community. And we are right now also developing our own hardware, which will like achieve the real-time ZK proving. Like for instance, like we can use like our hardware to our like own ASIC chips to prove like probably like more than 500K keycheck functions per second. And this like hardware can like make it like like more accessible to the community, and we can also use the hardware to achieve the verge approach like from Vitalik. Yeah.
At Marlin, we are building a proof market called Calypso. And Calypso is basically a marketplace that lets you outsource proof generation to a third-party network of like provers instead of doing it yourself, right? And the broad vision is basically to get the optimization flywheel going for ZK. So given the market size in ZK today, you can probably justify a certain amount invested into like optimizations and like getting better hardware and stuff like that. And once you have better hardware, essentially your proofs are faster, which means your user experience gets better. And hopefully that's sort of like grows your market to a point where you can justify investing a lot more into ZK, right? So it's a real positive feedback loop that we've seen in like the mining ecosystem with like Bitcoin and Ethereum. And our goal is to basically get the same flywheel going for the ZK ecosystem.
Hey, hello everyone. I'm Jenna Ouyang, co-founder and CEO of Snarkify. We are building a high-performance proof network for end-to-end proving for ZK rollups. I'll start with something spicy. I don't think once you have better hardware, you automatically get higher performance proof systems. That does not happen automatically because we have to look at this problem end-to-end. You have the software part, you have the hardware part. Even if you build a very fast ASIC, or even we have faster GPUs from NVIDIA, there are still a lot of memory bottleneck data communication from the CPU side and the accelerator side, that would become the bottleneck, so that faster compute does not help. So we took an end-to-end approach. By end-to-end, I mean we have a GPU DP network, which handles the hardware supply. We also have a GPU acceleration layer with our in-house GPU software. We're quite strong on GPU acceleration. So instead of betting on ASIC or FPGA, we are heavily betting on GPU. We are probably we are probably the best GPU team in ZK because we have won many of the Z-Prize hardware accelerations. And on top of that, we also have our ZK research team working on proof systems and ZKVMs, trying to figure out how to design proof systems and ZKVMs such that they can run efficiently on GPUs. So that's our take. Thanks.
Hi, everyone. This is Norbert from Gavulot. Basically, we are building the first universal ZK infrastructure, ZK optimized infrastructure for the space. And I think regarding the question and challenges to scalability, I think fragmentation is one of the key challenges, and we are trying to solve that by making building a protocol that's universally supporting any proof system out there. You can use the pre-deployed ones, or you can deploy your own prover and generate proofs efficiently. The other thing is, I think, a challenge to scalability is centralization. Many of the teams currently out there, specifically many of the L2s, are actually doing proving in a centralized fashion. Idle time actually burns a whole lot of money. Hardware utilization is not optimal in those cases. So we are building a decentralized protocol to address that, to make proving basically fast, cheap, and truly decentralized. Yep, that's my take.
Awesome. Variety of experiences and different directions in terms of where you see the different projects headed. I noticed there was a question or an answer by Dr. Ouyang related to the hardware, what role hardware plays. Do you, I guess starting with Norbert, what role, I would say, like would Gavulot, does Gavulot play within the hardware optimizations, or how do you see that within the prover marketplace?
Thanks. From our side, basically we are kind of hardware agnostic. Currently we support CPU and GPU proving as well, but we are building our platform to support also any exotic hardware out there. I mean, I guess it's more for SciSig, more for Leo to answer, but I've seen some recent benchmarks from Fabrics VPU, about Fabrics VPU, like 5.5x increase in performance on RISC-V cycles compared to 4090s, or 11x compared to 3090s. So we are looking to support any of the exotic hardware out there and support prover node operators with such hardware as well. Yeah, I think it's exciting to see whether, as Dr. Ouyang mentioned, GPU proving is going to be the mainstream, or like exotic hardware takes off. Curious to see that.
Yeah, that's a very actually interesting question, and there's not a clear answer yet who will win in the long run. But I think our position is that we are here to make the GPU performance baseline as high as possible, so that it's very hard to beat by any other hardware accelerator. So we are the baseline. So no matter what kind of hardware you're working on, ASIC, FPGAs, you have to beat our GPU performance. I think people haven't seen the full potential of GPU performance yet. For example, from the most recent Z-Prize end-to-end proving result, actually judged by Leo here, one of my co-founder, Niall Imart, who is one of the best GPU acceleration guru in ZK, he actually achieved 900 times speed up for end-to-end Planck proof on a single GPU device. Well, this number sounds high and mind-blowing. The reason is that all the compute are put on the GPU for that particular problem. There's no communication between the CPU and GPUs. So the learning there is once you can design a proof system such that you can eliminate cross-device communication, you can actually achieve very high performance. This is true for both GPU and any other accelerators, because once you are bottlenecked on the memory communication or on the GPU side, no matter how fast your accelerator is, it's not helpful because it cannot saturate the compute. So I think both, like all the hardware accelerator companies are facing the same problem, which is how to design an accelerator-friendly ZK proof system. Yeah, thanks.
So as a proof market, we don't really have to take calls on which hardware will win out, because like the market doesn't really care about how you generate the proof, right? All it cares about is that like you have a valid proof and it verifies. So for us, the hardware doesn't really matter. What's important is that the marketplace is like competitive. So what that means is there's really an incentive for people to sort of like invest in creating better hardware, like hardware that's more optimized to specific proof systems or like specific projects. And we get to like onboard that onto the market, right? But personally, the trend that I've been seeing in the ZK space is the move towards sort of like hybrid systems, where a lot of systems today use a combination of like IPA, PCS, maybe some checks here and there. So building hardware for like an ever-changing system that seems to be accommodating more and more pieces of the ecosystem into like a single protocol is honestly quite hard, because you quickly run into like what's called the Amdahl's law, right? So the more you optimize one component, the less important it becomes, because all of the other components end up taking the rest of the time, right? We've already seen this happen with like MSMs and entities. We had a lot of ASICs come out that like speeded up MSMs and ASICs and all that. But the bottleneck has slowly moved on to like PCS and SumCheck and all that, right? So yeah, building hardware at this point might be a little early in my opinion, but yeah, let's see where it goes.
Okay, yeah. So like I'll like talk a little bit about like our opinion on the hardware part. So like the ZK proving hardware is basically like very similar to Bitcoin mining. Like in Bitcoin mining, like we started like using like CPU, then you jump to FPGA or like or GPU, then announced like there's ASICs coming from like BMN. So like in hardware, like there are like basically like probably like two metrics, like performance per dollar and also performance per watt. The first performance per dollar means like how much you need to pay for hardware. Yeah. So and the second is like performance per watt, which is like how much you need to pay every day to run this hardware. Yeah. So like when like SciSix like designing the hardware, we always have these like two metrics like in mind. We just want to build them. Like our main competitor is basically like a NVIDIA GPU, and we want to have at least probably like one order of magnitude better performance, like in terms of these two metrics. And also, so that's something like of our like design principle. The second part is about probably like I as a panelist mentioned, like there is always some change in the ZK proving part. It's not as finalized as the Bitcoin mine. So like so the real challenge right now is to say we need to design a hardware that's like general enough to cover as many possible proof backends as possible, but still within a reasonable budget, since we are just a startup, we're not payment. For that way, like you need to like have some like clever design on the hardware to make it like general enough to cover this like code-based, hash-based, or like curve-based proof system. Yeah.
That's a good point relating to the cost of proving as well as the speed, and what's to best optimize for the structure today. And actually, a follow-up question to that: is there enough proof demand for where this type of proving structures that you're designing? Are you optimizing for maybe things that are more cost effective today, and then later on we'll scale with demand? What are your trajectories looking like? And then we'll start with Leo.
Yeah, so like SciSix is also building like a SciSix network, which is a ZK proof and also verification layer. And in the past, I guess, 4 or 5 months, we have generated more than 7 million proof for the community. And it's basically like coming from like several like big players. We are right now like expanding like our support for more customers in the ZK space. Yeah, since like SciSig is like well connected with the mining community. So basically we can have like as many GPU as possible if we want. Like for instance, like in ADO mining, we have like more than, I guess, like 50,000 GPUs like enjoying. And if we can like have like more ZK customers, which right now we're exploring, so probably like we can I guess the demand is still like high enough to at least make a lot of like players in the community to survive. Yeah.
So personally, I don't think we are there today, but we are getting there. And there are like three main areas that I see us growing towards there. One is, of course, like ZK proof of work mining, as Leah mentioned. Just due to its very nature, proof of work can basically take as much hardware as you can throw at it, right? So it's almost like an infinite demand hack in that way. On the other side, we also have a lot of applications starting to use like ZKVMs and like onboarding like snarks and Gnac and all of that into their core protocols, right? So applications are also like a really fast like growing sector because again, there's no real like limit for the number of applications that you're gonna have or like the number of ZK proofs that they're gonna need, right? And I'm not that confident whether the roll-up segment will be that big. But yeah, seems like rollups also need a lot of compute space currently, as I guess Norbert will watch for it. The Aztec proven it is like slated to require something around the order of like 1,000 nodes per proven network. So yeah, depending on like how many rollups there are and like how intensive each of these rollups are, we might see like quite a bit of demand from that as well.
Well, our observation that short answer is there are a lot of supply of compute, either GPU or any other devices, but there's not enough demand yet. But we are seeing increasing demand. We are very opinionated about what kind of workload we care about. We don't claim to be a universal proof generation provider. Right now, we are particularly focused on block proving for ZK rollups. In the past 1 year or two, we have worked with ZKML companies, co-processor companies, maybe ZK bridges companies, as well as ZK rollup companies. And one thing we figured out is that ZK rollups is only ZK workload right now that can provide you volume. Like as a proving service provider, we care about large volume of proof generations from paid customers. I think right now those ZK rollups are the larger ones. And also, many of the ZK rollups right now are running on public cloud, AWS, GCP. Some of them have decentralized their prover infra. Some of them are on the decentralizing their infra right now. I think we are seeing the demand to open up so that like prover networks like us could have more potential proof demand. That's our take.
From my side, I think I agree basically with all of you guys. We are also very much focused, like short term, the demand is definitely coming from L2s and rollups. It's interesting to see the dynamics in terms of their decentralization paths. And I think there will be a tipping point there pretty soon. I would say maybe a couple of months where some reliable solutions occur, reliable providers, and all the rest of the industry is going to start opening up like in an increased pace. But another thing is that we are looking at heavily is OP seemed to have been winning, like the optimistic stack, not particularly optimism, but like the optimistic stack. And as we see like OP succinct or I don't know, risk zeros, Zeth proving Ethereum, or I don't know, many other proof systems or provers coming online with the aim to provide real-time proving. I think proving of L1s, optimistic chains transitioning to ZK is a very valid like next round after we have some mature infrastructure in place. And that's what we at Gevulot are working toward.
That's a common theme that I hear is that the L2 space is the one that is supplying the most demand, I guess. But not all L2s that I'm aware are currently using, I guess, like outsourcing their proving infrastructure. Sometimes some of them are leveraging, their own types of proving infrastructure. What would you think would be the key the key value proposition that will get these L2s to transition over from locally or from proving running their own provers to now outsourcing? And I guess we'll start with you, Norbert, if you want.
Okay, thanks. Well, I think what I see is that many of them have been and to learn from the mistakes maybe others are doing in their first steps. But jokes aside, I think as I mentioned, as the landscape matures, as the infrastructure, the proof providers mature, we had the STAC contest in August, September, which was basically the first decentralized proving, like live decentralized proof outsourced, proving outsourced in the space. I think with that, it largely kicked off a bunch of initiatives and started like minds opening up towards decentralization. I think the cost factor is going to be big because it's one thing that is hindering like decentralization and like also demand coming in is the cost of proving. Like I think there are a bunch of applications out there who would love to become verifiable, but it's just too expensive yet and it's not economically viable. What we are looking to do, and it seems to be absolutely realistic, is to decrease the cost of proving by at least an order of magnitude. With Gevulot, we see our economics, how it's working out, and you don't even need an auction for that. We are baking it into the protocol so it's available for anyone. And as soon as the cost of proving is small and you are able to provide an available network, a scalable network, and you also remove the idle time from the users, then they will start thinking, okay, proving is cheap and I don't waste money with idle time. And that's what many of the centralized setups with rollups proving with their own infrastructure are currently facing now.
Yeah, I'll second that. I think short answer is cost. They will open up their proving infra because otherwise they will not stay competitive because other people are moving into cheaper proving solutions. If we look at the OP operation cost, if you want to launch an OP chain, it probably costs you $2,000 per month from the REST providers. However, if you launch a ZK chain today using any of the open source, open ZK stack solutions, it costs you maybe 20 times more than that, 40K per month. So how to get the cost down? The first step is to move your proving infra out from the public cloud. So the off-cloud GPUs are 10 times cheaper. Maybe ASICs are even more cheaper than that. The second step is to build more efficient software proof systems so that given the same hardware resource, you can prove more stuff with a shorter amount of time. With these two in place, we can drive the proving cost down dramatically. And I think this will happen soon in the next, at least like moving out of public cloud part could happen in the next 3 to 6 months. We'll see how the proof system evolves in the next year, but it looks very promising. Yeah.
Yeah, I would agree with all that. I think I should also add that at the end of the day, it might not matter much as to how rollups really want to do their proof processing and all that. Because it seems like at the end of the day, all rollups want is just somebody to place a bond and say, hey, I'm going to generate a proof for this block, right? Beyond that, for one, they don't really care. And number two, there's no really a good way for them to enforce that their validators don't actually use a proof market, right? So yeah, end of the day, rollups for one, they seem to be agnostic about proof markets. Like if you want to outsource that, it's fine. But at the end of the day, they might not even have a say towards that.
Oh, yeah. Oh, okay. Yeah. So from like SciSix perspective, like I think like there are just the two factors. Like the first is the performance, and second is the cost. And if you can help your like record like the ZK project, they're just the customers. They want to generate their proof as fast as possible, as like very probably like as little cost as possible. So that's like what SciSix is doing. Like for instance, there's like a new customer like coming to like SciSix network, and we can basically reduce the proof generation time for them at least to 1/3 or like even 1/4. And we do it at we do it at the same price or even like lower for them to do the ZK proving. So like if you can if you have like any advantages over these two factors, then you can like win in like more customers like from the ZK community, I think.
Perfect. No, I like the variety of perspectives, but it all boils down to the cost, the speed, the liveness as well. So making sure that the proofs are posted at specific times, you know, to have those finality guarantees, and definitely good directions moving forward in terms of the customer facing approach. And I guess in terms of I guess when we talk about the decrease of proof costs, how are your projects, you know, attempting that, attempting to be competitive? You know, what unique strategies are you looking at, and then is there any potential room for expansion where you're looking further? And I guess we'll start with you, Leo.
Okay, sure. Yeah. So like to reduce the cost, like basically you can run multiple provers on a single machine. So you can open as many containers as possible on your machine, and hopefully the resources like required by these containers, they are not competing with each other, and you can like design some smart scheduling algorithm on your machine like to make it possible for these containers. They do not at least compete too much on the resources, and which means like it doesn't affect the performance requirement of your like ZK customer. So probably like just one tech part of like how you can like reduce the cost. And second, you can like attract as many GPU like servers from the community. So like record like previously like in either like Ethereum mining or like Filecoin mining, like there are like a lot of like idle GPUs like sitting there. You just want to, but these like GPUs they may not be like this like 4090 GPUs. They are like probably like 2080 or like 3070 something GPUs. Yeah, you just try to like deploy your like provers on this like probably like older version GPU and still making it like usable for the current like ZK projects. Yeah, so that's like just two ways to reduce the cost.
So we kind of look at this in like two ways. The first, probably more obvious one, is just incentivizing competition, right? Because that's basically how things get faster and better and cheaper. The second one is the fact that provers on our proof market don't really have to be like open source. They can literally be full proprietary, right? So what that lets us do is sort of monetize the ZK expertise of like the entire community, because as much expertise as our own team has, I'm confident that the wider ZK team probably has a lot more expertise, right? So you can run proprietary provers, you can invest into better hardware, run proprietary software, firmware, all of that, and you get to reap the benefits of that because you basically get redirected more revenue from the proof market essentially, right? So you can choose to customize whichever part of the stack you want. You can choose to focus your investments on whichever part of the stack you want. You can even choose to collaborate with others to build something like a well-rounded package. And you can sort of monetize that on the proof market without really having to like making it open source or anything. So yeah.
Okay. Again, I think we should look at the problem end to end. The naive solution is very straightforward. You source cheaper compute from the mining operators or whatever cheaper hardware GPUs you could get. But that's not quite interesting. I think we are taking the harder route. I call it ZKVM or proof system GPU co-design because I think the ZKVMs or the proof systems were not designed for the accelerators. So the current approach is that people will implement ZK library on the CPUs. It takes whatever resource with whatever of parallelization implemented in their library, Rust library. And teams like us, we took their Rust library, trying to make it fast with GPUs or with ASICs. I don't think that's a sustainable approach to reach the peak performance because from the mathematical level and from the system implementation or architecture level, it's not really accelerator friendly. It does not scale on the hardware accelerators when you got many threads on the chip as well as fast compute on the chip. So the way we want to look at this is we should redesign the proof system or the ZKVM with accelerators as a first-class citizen. Like when you start to design at the math level or start to implement your Rust library, you should have accelerators in mind. I think this is an ultimate solution to drive the cost down, other than just looking at the hardware cost. Another approach that down the bottom is actually to build cheaper ASIC. That's another approach to drive the cost down. But just competing on the hardware supply cost is not really interesting. It's also not a long-term solution. Thanks.
Yeah, I think you guys said it all already. Maybe just to add from our end, we are building a universal platform to be able to aggregate and support as many type of workloads or proof systems as possible, because we see that's one of the ways to increase hardware utilization. And on the other side, it will boil down to decreased operational costs per proof, per minute or per hour, whatever way you look at it. And also the other thing is that to offer like a scalable network where, for example, you get a couple thousand nodes in your network at 80, 90% or 70, 80% network utilization. I'm just throwing in something that has sufficient redundancy to be able to support, let's say, one S-stack proof falling in, which requires, let's say, 1,000 nodes for 10 minutes, because the proof tree construction of S-stack is so high. So it's kind of, it at the end boils down to like decreasing the cost of proving, removing the idle time from the user, and like kind of efficient orchestration within our network, both at node level and at network level, so that we can support whatever software efficiencies or hardware efficiencies have been gained by co-design, etc., etc. We are building to support all this from our angle universally.
I like the variety of perspectives, focusing on the GPUs, focusing on hardware acceleration, focusing on the competition side of things, and then the like leveraging this specific scenario on what you're trying to prove, and then designing the structures specifically for that. I guess one thing that wasn't mentioned is potentially standards. And how do you see standards within the proof generation playing out? Do you see it as, a type of, we'll see what the best type of structure is, or should there be maybe some alignment on that going forward? Well, I guess we'll start with you, Norbert.
Yeah, so I'd leave the standardization of proof systems and those type of things to our bright guys here. I'd say from my angle, standardization in terms of the proving infrastructure, we've kicked off an initiative solution, it's really hard. If you can build a piece of software like similar to like MathBoost or something like that, but it's ZK Boost, that connects proof providers from one side and anyone demanding ZKPs from the other side, and lets them just express what they want and have all the options available through the software. I think that's going to be key in terms of UX for outsourcing proving. And that's the type of standardization we are looking at, and we are part of the consortium as well, supporting.
From our perspective, standardization definitely very important. However, we took a different approach. We don't like create a standard and trying to push it out. We took the other side of the approach, which is we try to integrate with them one by one and to figure out what the right standard is. So what's happening right now is that we have different ZK clusters. For example, elastic chain. All of the elastic chains from ZK Sync, they follow the same kind of standard. They have the same proving infra. On the other side, if you look at a scroll ecosystem, they have a different standard and proving infra. It's not clear yet if we can create the same standard and apply to different ZK clusters. But I think within each ecosystem, the standard can work across their own chains. The challenge is really how to enable the ZK clusters to collaborate with each other and create industry-wide standard. Yeah.
So I'm kind of on two minds about this. So as a proof market, obviously it's really good when things standardize because it's less work for me to integrate anything. And it also means that my market doesn't need a lot of hardware. It can just focus on like one specific hardware, right? So from the perspective of a market, standardization is obviously really good. But I'm not sure if we're ready for that as an ecosystem yet, mainly because of the speed at which things are moving, right? Like if you think the ecosystem has slowed down, you just have to go to one ZK summit to figure out like, hey, there's so much new research still coming out, so many new curves and all that still being discovered. And yeah, I'm not sure we're there as a space yet, to be honest.
Yeah, so like from SciSec's perspective, like we wish there was a standard so we can just focus on developing the best hardware for the standard, but there is not. Yeah, so like I guess like for all the like proving infra, we can have some positive effect on like how the community reach consensus on like which standard we or like which like the ZK system we can use. If we can have like fast enough and also cheap enough like ZK proving infra, and probably like there will be a chance that the project, the ZK project, they can like migrate to this like new probably like standard or something.
Awesome. I think I was notified that we're a little bit over time. I was so engaged with the panel and the discussion. But I guess I'd like to welcome the audience to give a hand for our panel participants. And thank you all for coming.
Thanks.
Okay, thank you so much, Pavel. You were a lovely moderator. Thank you, gentlemen. I gotta say, these conversations are often very content heavy and can feel a bit dense sometimes. So I appreciate Doctor for the spicy commentary and very, very firm stance on his own perspectives. I was actually hoping that somebody would disagree with him. All right, for our next and first solo presentation, we have the CTO of Hylay joining us on stage, Lyle. Okay, come on, everybody, get a little excited. Woo!
Yeah. Okay. Awesome. Great. Thanks everyone for coming. Welcome to my presentation. This will be pipeline proving practical ZK proofs for applications and what we're doing at Hylay. Okay. The clicker doesn't seem to pull through to the computer. I'm too far away, that's fine. Anyways, so I'm Lancelot. I'm the CTO and co-founder of Highly, and I was previously working on Brick, an NFT project in the Starknet ecosystem, which is where I discovered zero-knowledge technology, validity proofs, all that jazz. I'm Variety on X, which I still call Twitter, because I'm a boomer. It is Twitter, exactly. Yeah. So I'm sorry, the clicker, oh, it just vibrated, but I still can't do anything, I think. Sorry, I switched too fast now. Well, this is the content of my presentation anyway, so let's talk about this. What we're going to talk about is the fact that rollups are good, but they have limitations and we can improve on them. And I'm going to tell you about some of the state-of-the-art things that we're doing with blockchains on Highly that enable this. So rollups are good. And this is, I just got it working once, I think, and then not. I'll do like flag gestures. You can move once. No, it's still too far away. Yeah, I'll just like tell you to switch it. It's fine. Rollups are good. Let's quickly go over what a rollup does. In fact, well, our definition of a rollup anyways, because these words are a bit overused nowadays. A rollup maintains state commitments on the layer 1. That's like the security guarantee and assumption. And each of the state transitions in the case of a ZK rollup is validated by a ZK proof, which makes sure that you can't have like fraud, you can't do invalid transitions, these type of things. However, usually it's permissioned. Only the layer 2 sequencer can post actual validity proofs that change the state transition, that like change the state commitments, which are usually centralized. And this is, of course, unless you have escape hatches, which as far as I can tell, none of the ZK rollups that are like general purpose have in production. And indexation is also trustless, but again, you need non-L1 actors to be able to access the information. So, next slide, please. Yeah, this basically looks like that. These are, rollups are icebergs. You got the state commitment, that's a little bit floating above the water. And then you have 90% of the thing, the whole data, which is under the water, and that's on the layer 2. I feel like I'm conducting, sorry, like this was just for simulation. Yeah, and so transitions are just proofs of state transition. Transactions are just proofs of state transitions. So you start from a green commitment, and then you have a ZK proof that takes you from the green to the blue commitment, and then another ZK proof that takes you from the blue to the red commitment. But with most ZK rollups, these are actually batches of a lot of transactions, batches of blocks even. And there are several hours between each of these state transitions because for efficiency, they need to recurse a lot, they need to batch a lot. And so that takes time. So that's the first thing. And then once you want to read the information, well, you have to go through an indexer. So you have essentially two options. You could theoretically do it on your own. It could be like user indexation, or you rely on like the rollup infrastructure. They have their own indexer. In the case of, say, Starknet, Starknet provides the state of Starknet because otherwise it just would not be very usable. But in theory, somebody could do their own indexation. I think there's actually some companies that have done that. So accessing the layer 2 state, accessing what's under the iceberg remains permissionless, but you have to have somebody doing it. It's not as automatic as on Ethereum. What's interesting is that if you don't do this with batches of blocks, but with individual transactions, you end up having something that looks a lot like what I'm calling a based ZK rollup, which isn't really an actual thing, but it's essentially the same thing, and this is like the exact same diagram for a reason. Essentially, each transaction would just be a ZK proof of a state transition, and on the layer 1, you just maintain the state commitment of your own application, and you switch, and you switch. And that's exactly like how rollups work. You can do a regular application with that. But if you want to try to do that, yeah, you're gonna have some issues because right now all of the rollups are bridged to the layer 1. So they are technically interoperable, except you have to go through bridges every time. Please enjoy my drawings. I've worked very hard on them. And each of these icebergs remains quite separated from each other and from the layer 1. So if you want to do things efficiently, you run into issues. It's difficult to compose contract calls. You have long proving times. Like I explained, you need to do batches of blocks instead of individual transactions because it takes too long. You have high latency, and it's very hard to do parallelization. One of the things that I didn't gloss over, but because layer 2s are centralized, you only have one person trying to post proofs, and so they don't have parallelization. If you try to have many users at the same time, then you run into issues. So rollups are good, but they could be better, and here's how to make them better. So first, the next slide, please. So first, composable contract calls. If you want to do composition right now with ZK proofs, you're the situation on the left. Let's say for some reason, maybe the metaverse is hype again, you want to do Tetris, but you want people to have a CryptoPunk to be able to play Tetris. What you have to do is verify inside the code of your Tetris game the code of this, the CryptoPunk contract. Sorry, this was just a gesture. This is annoying because if you want to change the identity verification that you're doing, you need to change the code of your own application. You're basically like doing boxes inside boxes inside boxes. If you want to change the innermost box, you have to open everything and swap it out. With proper composability, which is what we give you if you're using the highly protocol network, you can do the same independently. You'd have the CryptoPunk proof that's standing on its own. You'd have your own Tetris proof, and you just add a little bit of information inside your own proof as like metadata that you expect a proof of a CryptoPunk to exist. And you can just change that little bit of metadata. You don't need to change anything else to be able to support any kind of identity. And you can actually like even abstract it away and change the code of your application without redeploying or without relying. If the CryptoPunks update, you don't need to update your application. Obviously they wouldn't, this type of things. So that's like the solution to the first problem. The second problem, which is much more annoying, is proving time and latency. So here I have an example. This is the arrow of time, and at some point there is an auction, and at some point in the middle the auction ends. That's like the red line. Let's say you're a user and you see that auction and you want to make a bid on that. If you need to generate a ZK proof to actually validate your bid, that's going to take time. And maybe it takes so much time that by the time the proof has been generated and you can send it to the chain, well, the auction's ended, and you're kind of like, you're sad and you're crying because you didn't have enough time to do this. So that's both proving time and proving latency. They're like related, and it's annoying. The second problem is parallelization. Let's say two people see the auction at the same time and they want to make a bid on that. Except the other guy, the guy in blue, he's got a faster computer or a faster horse or whatever, and he sends his transaction with his proof to the network faster than you. So he switches from green to blue. In the meantime, you also saw the original green state commitment, and so you were generating your proof based on that state, and you want to switch from green to red. But by the time your transaction arrives on the chain, the state is now blue, and we can't do anything with that. We don't know how to switch from blue to red. We only know how to switch from green to red. So this is the issue of parallelization when you're just handling state transitions on state commitments with ZK proofs. And again, you end up being very sad because you couldn't actually commit your transaction. So the solution to this is the title of this presentation. It's finally arrived, pipeline proving, which is in a very roundabout way, kind of like going to the restaurant. You book a table and then you can kind of come whenever, well, hopefully on time, but there's still, in this example, two people, but things happen very differently. The idea is that we split sequencing of transactions from the actual settlement, which is powered by ZK proofs. So sequencing, what that means is that, well, maybe you both just send the information about your bid on chain. You send however much you want to bid. You send, I mean, like for an auction, this might be, actually, you might want to keep it secret and send the ZK proof directly, but these are like details. So you both send how much you want to bid to the chain. There's no latency because you're not generating a proof, so we just immediately receive that, we sequence that. We know in which order your bids have arrived. And so from then on, everything is fully determined. There's no guesswork, nothing can change. So we can start working on generating ZK proofs that you could legitimately actually bid on the auction. So maybe you can prove that you have enough balance or that you had enough balance at that time. You can prove that you were authorized to do the bidding because you send a signature or because somebody else authorized you or something. And we know that first we want to go from the green to the blue state and then from the blue to the red state, even though both users originally saw the green state. And we can generate ZK proofs for both of these transactions and settle them after the auctions ended, potentially. That's fine, because what actually matters for the order of operations is the initial sequencing. So the chain will only be able to reflect the state once we settle them after the proofs, but there's no way to change things, and so essentially it's like time travel. Yeah, which is pretty neat. This leads us into what we call lean blockchain, which is what Highly is. Essentially, basically we view blockchains as just custodians of data integrity rather than through zero-knowledge proofs. They only do sequencing, a little bit of data availability, and settlements. And with pipeline proving and native proof composability, you can get like really high performance. In theory, because it's like asynchronous, you might get like, yeah, it's in theory infinite. In practice, it's not going to be infinite, but it still could go really, really high if you do enough recursion in that like latency gap. And this is really cool because instead of the previous situations where everybody was talking through bridges to a layer 1, nowadays everybody is inside the layer 1, but everybody works like a rollup, so you can still do, you can write Rust code and run it on SP1 or ReZero or whatever, and you're already interconnected via native proof composability. So like ZK Rails, I drew some like high-speed trains because we're French. And this allows you to have a lot more flexibility than what you can do in current blockchain ecosystems. So this is like a random example and it does not yet reflect reality, but you could have, at the same time, permissionless on-ramp via, say, ZK email. You can prove that you're sending some money to a custodian off-chain. And this could be like fully decentralized and would work natively with, I don't know, a fully on-chain game like the ETH Frontier project that was announced recently, where the decentralization is assured by the players. And at the same time, you could do like DeFi pooling with permissionless strategies, but those strategies are actually private because they're run off-chain and executed using ZK proofs, or really any other thing you want. Of course, you can also do the regular blockchain stuff of NFT contract, any kind of identity, smart wallets, these type of things. So this is Highly. This is what we are building right now. We are still pretty early. We're in the development of the testnet phase. We're building a new Rust client. If you're interested in checking that out, check out our socials, Twitter, Telegram, the website. I think that QR code is for Telegram. So that, it might be Twitter. This will lead you to the correct places anyways. Thanks for coming, and if you have questions, we'll be around. We have a booth today at ZK Hub and tomorrow as well.
Thank you so much, Lyle. Just wanted to repeat that there is a booth outside in the marketplace for the Highlight team. So if you have any questions at all, that's the spot. Next up, we have the spicy Dr. Jian Yang from Snarkify. Please, everybody, a round of applause. I'm really looking forward to this one and all of the hotly contested ideas you have.
Thank you.
Okay.
Thank you, everyone. So, do I look my deck here? Okay. I'm Jenna Ouyang again, co-founder and CEO at Snarkify. Today, I'm going to present about our end-to-end ZKVM proving with GPU acceleration. Okay, next slide. Cool. So first of all, what is Snarkify? I think most people know us because of our Z prize winnings. Like on my slide, I listed six first places we won over the past 6 years. In the most recent one, which is a GPU Planck end-to-end proving, we achieved 900 speed up over GPUs on a single device, which is even mind-blowing for myself when I first see the result. For our company, we actually have a vertical integrated solution on different of the tech layers of the stack. So we are building a decentralized proof network that provides end-to-end proving for ZK rollups. By end-to-end, I mean we work on the bottom layer, which is GPU deeping, and the middle layer, which is a GPU acceleration library. And on the top of that, we also work on ZK proof systems and ZKVM optimizations, so that the whole stack is vertically integrated and optimized together to achieve best performance, latency, and cost. Next slide, please. Oops. Okay, so what is our end-to-end proving? If you look at the top, those are our potential customers. In the previous panel, I mentioned that ZK layer 2s, ZK rollups are the main demand providers right now. So what do they have in common? If you look at native ZK rollups, as well as the open source ZK stacks, and the so-called OP ZK rollups, actually all of them are generating block spaces that needs to be proved. Then you figure out what's the most efficient way to prove those block spaces. There are the traditional approach, which is you create a manually written circuit. For example, the ZKVM circuits from PSE and Scroll. They use Hello 2 to manually write a giant EVM circuit to prove the ZKVM. This is a proof system, the circuits I'm going to cover today. But the next generation solution is to use ZKVMs to prove Rust code, like RATH or THAT from RISC-0. You have a RISC-V ZKVM, and you can prove all kind of Rust code. And in this case, you use it to prove a Rust Ethereum node. So beneath of the ZK rollup layer at the top, we have a layer of ZKVMs. We are ZKVM agnostic. So our position is to pick the most performance and promising ZKVM architecture and do GPU integration with it to build GPU acceleration libraries for this particular ZKVM. And actually, those GPU code and the ZKVM is tightly coupled. So it's not like we just took some of the computer kernels, for example, NTT, and plug in a GPU NTT kernel to make it faster. That won't work. You have to look at the whole thing end to end. You measure where the bottleneck is, you rewrite many of the code, and as well as optimize for the workflow. For example, you figure how to lay out the data optimized on the different GPU devices so that you can have optimal data communication, etc. So the point is the GPU library and the ZKVM has to be tightly coupled and integrated together. Then at the bottom, we have the platform layer, which is a decentralized GPU supply that can provide you cost-efficient GPU supplies from those crypto miners where they have a lot of GPUs that are sitting idle. Okay, next slide. Okay, here's my agenda today. I'll do a case study of our integration with Scroll in production, like trying to showcase that. I tried to do a live demo here today. However, like the setup does not allow me to use a laptop. But you guys feel free to check it online. All those stuff up in production. You can see it on your own. You can check out our website and try. Then I'll explain how our architecture support the Scroll integration, and most importantly, what's the core component that's the in-house GPU prover we built. Right now, we are the only prover network that can provide both the GPU hardware and the in-house GPU prover, like end-to-end in-house. All the other GPU providers, prover networks are kind of running third-party provers from either ZK-Sync or from Scroll, where they are just improving the GPU hardware. We do both GPU supply and software in-house. Okay, next slide, please. All right. First of all, our integration with the Squirrel. Okay, next slide. Okay, this is already live in production. It's called a demo, but I can't do a demo here. But if you check out explorer.snarkify.io here now, you can see it live. We don't have a mobile version, unfortunately, right now. If you use your phone, the layout will be corrupted. But this is what it should like. So on the top is all the block proofs we generated for Squirrel mainnet. So we don't claim we generated a lot of proofs that we don't know what it is. This is all the proofs for Squirrel mainnet, and every block is proving a Squirrel mainnet block. So in total, I think right now, if you look at our data, we have proved 100K Squirrel blocks, mainnet blocks over the past 1 to 2 months. And the proving service is elastic, so that if we got more demand from the Squirrel side, we can actually spin up more GPUs and to provide more capacity. At the bottom, you can see some proofs are pending and some are already completed. Okay, next slide. So how does this work? I borrowed this slide from Squirrel. So if you look at the top, they have the rollup contract, which is their application contract on their layer 2. Then beneath that, they have the sequencer, which produces blocks. Like all the transactions are executed and blocks are generated. So then you have the coordinator that generates the proof tasks, like T1, T2 are basically proof tasks for each block. Then you have the coordinator that schedules all those block proofs tasks to those provers. You can see that all those provers, where they call rollers here, are running in parallel so that multiple proof tasks can running in the same pipeline. And finally, all the proofs are generated with an aggregator and updated to layer 1 and get verified. This is the existing Squirrel architecture. So we are here to see how can we integrate this architecture with our elastic prover. Next slide, please. Okay. So we create the bottom 3 component in blue is our like software. The top is Squirrel mainnet and Squirrel SDK chain. So there are 2 kind of ZKROPs from Squirrel. One is their mainnet, that's in production right now. Then is their open source stack called Squirrel SDK, where you can launch your own ZKROP with their open source solution. We create a gateway in between so that all the proofs can be routed to the gateway and then dispatched to our elastic provers. Here is a standard problem that we can observe. You can see that the way proofs get approved is different from the mainnet as well from the SDK chain. So somehow their mainnet is based on a pool model. So if you deploy their prover, you're actually pulling tasks from their coordinator. However, if you are running a Squirrel SDK chain, it's actually based on a push model, where the SDK chain will push proof tasks to your infra. This is where there's no standard. Basically, even inside the same ecosystem, they have 2 different ways to generate proofs. We have to abstract that different away so that we can provide a homogeneous proving experience inside our infra. Okay, next slide. Let's look at how our elastic prover work and how it can be integrated with the Squirrel infra. So elastic prover provide you the following features. One is a simple proof generation API. It's very simple, just like create proof. However, behind this proof API is elastic and also auto-scaling, so that more jobs you sending into this create proof generation API, you get more servers spin up and trying to serve those proofs. And finally, it's a pay-as-you-go proof model, because you only pay when you prove something, but you don't pay if you don't. Okay, next slide. This is deck from yesterday. It's not updated. However, I'm supposed to do a live demo here to show you how to deploy elastic prover. However, you can try it yourself. If you check out docs.snarkify.io, you will see our documentation online where you can find out a tutorial to launch Elastic Prover on our platform. It has to be in production for a while, 6 months or so. But we recently integrated it with our largest customer to see it in production. But yeah, try it yourself. It's very easy. Just take maybe 3 minutes to finish the workflow, deploy a prover, then you can try generating a proof on your own. Next slide, please. Okay, here's how to integrate with our SDK so that you can use our Elastic Prover service. As you can see, the API is very simple. You just define 3 things. One is a create proof endpoint, which is in the handler. You have a proof function. That's the main thing you want to define. Then you need to define how to serialize your input and your output. Basically, how to serialize your witness data as well as your proof, basically public input, private input, and witness, and then how to serialize your proof output. It's a very simple SDK you can integrate. Then you can use our serverless platform. Next slide, please. It's another demo. I want to show you the Scroll Elastic Prover deployed in production, but unfortunately, I cannot do it now. Okay, next slide, please. Okay, here's a main technical stuff. I'll go deep on this one. Let's look at how we optimize our Halo 2 EVM prover for the scroll circuit. So first, let's look at the target workload. The ZKVM circuit based on Halo 2 were co-developed by Ethereum PSE and the Scroll team. You can see it's a giant circuit. This way to develop ZKVMs is already deprecated, so that the PSE team has already archived this repo, meaning that they are not contributing new code to this repo. Maybe this is still a good example to see how we design ZKVMs and the ZKVMs, how the technology evolve. Like this is an old way, like from 2 years ago. Well, 2 years sounds long, but it's quite recent. The traditional way to do this is to manually reaching a giant circuit to describe all the ZKVM functionality. This is not very maintainable. Like once the EVM add a new opcode or a new precompile, you basically have to create a new circuit to describe that new opcode and compile. It's very hard to maintain. Also, the circuit is not modular. You've got a giant circuit proof, which creates some problems for our optimization as well. Next slide, please. So this table is more like a tutorial for Planck-proof systems, if you're not familiar with. In a Planck-proof system, you first convert all those circuits in the previous slide into a table. So all the cells in the table is called witness, and all the columns are called instance columns, etc., selectors, but it's not important. But from our GPU optimization perspective, we actually just taking in those giant table and trying to calculate some mathematical relations between those columns and as well as commit on those columns. Next slide. Okay, here's some parameters of this giant ZKVM circuit. The field is BN254 as on Ethereum, and the row of this table is 2 to the 20. This does not sound large yet. However, once you do the math, it immediately quickly goes into a larger called extended domain, which is 2 to the 23 number of rows. This is just the number of rows. If you consider each of the cell, which is a big integer, 254 bits, as you can see, which is 32 byte, which is actually making each column very large. So we are dealing with very large size columns in our GPU acceleration. That could be problematic because we need to move those large columns from the CPU to the GPU, do the computation, and then probably move it back. This is a huge bottleneck there. Then the column count is also very large. For a simple circuit for Poseidon, you probably see under 10 columns, pretty much. However, for the ZKVM circuit, you see more than 1,000 columns, which gives you a huge table. And the custom gates and lookups are basically the constraints or relationships between those columns that has to be satisfied. So we need to do those computation over those columns for those custom gates and lookups. Okay, next slide. Okay, here's some performance data. This is a baseline from like CPU baseline. In the whole proof generation process, you have 5 phases. From weightings generation to calculate the lookup arguments, compute column permutation, polynomials, evaluate polynomials, and multi-open. This stuff is familiar with if you are working on ZK proof systems. However, if you're not familiar with them, that's fine. Let's just look at the performance data on the CPU. In total, the end-to-end runtime for this proof generation is 1,700 seconds. Close to 1,800 seconds. You can see it's very long time of proof generation on CPUs. It's quite an overhead. And most of the time, we're spending on phase 3, which is compute the quotient polynomial. And we'll see how we can reduce the compute time with our GPU acceleration. Next slide, please. Okay, the first step is to take is, I think, well understood right now, which is optimize the most important compute kernels. It's well known that MSM and entities are taking a lot of time in proof generation. So MSM stands for multi-scalar multiplication. I used to give a separate talk on MSM at ZK Summit, as well as entity acceleration, which is basically FFT over this large field. Those are very compute intensive. With our GPU acceleration, we achieved 3.9 times speed up on MSMs as well as 62 times speed ups on entities, thanks to the open source compute kernels from Zprise. Many of them were did by my co-founder, Nayo Ahmad, as well as the Spark open source library. Like, this is how we improve the baseline of ZK proof computation. Once we open source these high performance kernels, anyone can integrate them in your production system and have faster compute kernels. However, this is only part of the story because, as you can see later, the majority of the compute are not actually on MSM and entities anymore. So we did do more to make it end-to-end faster. Next slide, please. Okay, this is, I think, most technical heavy optimization we did in our end-to-end Halo 2 proving. We built a transpiler to translate Rust computation into CUDA code pretty much. Because here we are doing some polynomial evaluations. We have a large number of polynomials. You can think of, we have many columns, and you need to compute some addition, multiplication, element by element over those columns, and you have an evaluation graph. So how do you compute this thing effectively on the GPUs? Note that you cannot hold all the columns at the same time on the GPUs, so you have to consider how to arrange your data so that you can move some columns, compute the result, save the result, and move some other columns into them, and then merge the result. Think about A plus B multiplied by C, this kind of expression. How do you run it over 3 huge columns on the GPU? So to do this, what we did was, first, we dump the Rust evaluation graph into an intermediate representation. It's a simple IR. Then we write a parser of the IR to translate the IR into CUDA kernels. And finally, we figure out how to arrange the data to run those final evaluation over multiple GPU cards. This is definitely an oversimplification of what we actually did, because this talk is not supposed to be like that technical. Also, this work is done by our another CUDA engineer. So if you are interested in this, how to do this transpiler, reach out and we can follow up with those details. As you can see, the performance is actually very impressive. We reduced, I think, phase 3 runtime from over 1,000 seconds to 36 seconds on the CPU. This is 40 times improvement and account for 61% time reduction on the for the end-to-end runtime. So this is actually the most important optimization we did for the end-to-end acceleration. I think the learning here is that maybe 1 to 2 years before, people think that if you want to build a fast proof generation system, you optimize MSM entities. That's what all people think about. They also think about how to build ASICs for MSM entities. So learning here is MSM and entities are no longer the bottleneck. The bottleneck is on things like this. Then we need to figure out how to build customized algorithms for bottlenecks like this. And once you kick out this bottleneck, some other bottlenecks show up. This is the challenge of doing end-to-end optimization. Next slide, please. Okay, the multi-open is only consumes 1% of the time. I'll probably skip this slide. Let's look at the final end-to-end acceleration result. On the left, that's what I've shown before. You have almost 1800 second end-to-end runtime. On the right is 3.8 times faster, which is around 469 seconds. Reduced because our optimization of MSM, NTT, as well as polynomial evaluation. However, you can see the blue sector becomes larger, occupies a larger area. That means the weightiness generation is becoming the bottleneck. Weightiness generation is always a challenge for hardware acceleration because it's a scenario, it's kind of a serial computation process where you execute your code you want to prove, and you fill in a table row by row. It's by nature serial. However, there are ways to optimize it. For example, if you look at our latest Z-price result, which did the end-to-end Planck proof, we actually have a way to do very fast weightiness generation on the GPU for Poseidon-based macrotrees. So we have to look at the weightiness generation process into details to really make this thing faster. This also shows that to achieve fast end-to-end performance, the stuff you want to optimize is very heterogeneous. For example, first of all, we deal with NTT and MSMs. I think people spend 1 year or two that's finally achieved the fast MSM entities on GPUs, and that's solved. Then immediately polynomial evaluation becomes a bottleneck. Then people, I think during the past 1 year or two, this problem is solved again. And finally, the weightiness generation is here. It's not completely solved yet. I think it's work in progress. How can we generate weightiness fast enough on GPUs as well as on ASICs? I think that's an open problem still. Okay, next slide, please. This part is slightly touched by Neil, in the earlier panel discussion, is that it's possible to run multiple provers on the same server to achieve better throughput. It just ensures that there's not a lot of resource competition in your resources. So here we try to run the same prover, run different number of provers on the same node. It's an 8-card GPU server. So we run 1 prover with 8 GPUs, or 2 provers each with 4 GPUs, and 4 prover each with 2 GPUs. You can see the runtimes get higher because they are competing on the CPU side or other shared resources. However, the throughput, proofs per hour, get higher. That because you achieve better resource sharing. For example, if you do 1 prover 8 cards, when the GPUs are idle, all 8 cards are idle. Them to do some other work instead of making all of the 8 GPU cards idle. So do some resource consolidation can improve the throughput is our learning here, and also confirmed by other teams like SciSig. Okay, next slide. All right. I think what I've covered is also a simplification of what's actually happening in production. There are more nuances there. For example, in Scroll's proof pipeline, they have the concept called multiple layer of proofs. what we described is the layer 0, which is actual ZKVM circuit proof generation. After that, they actually have something called layer 1 and layer 2 proofs. These were for proof aggregation. Because if you aggregate the layer 0 proofs directly, it introduces a huge overhead. So to solve that problem, they actually did 2 layers of compression, I can call it, so that the result you get the result Planck table, you get fewer columns and smaller rows, so that it's cheaper to aggregate. Then the layer 3 and layer 4 are actually the batch proof, which is the aggregation layer. So in order to achieve cheap aggregation for batch proof, they actually did 2 more layers of compression on top of layer 0. So that's a nuance in production. It's not just one proof, you have to make it fast end to end. You actually have multiple layers of proofs. And then one thing to mention is that we use circuit-specific optimizations because the polynomial evaluation, the transpiler I mentioned, is circuit-specific. Once you change a circuit, we need to rerun that transpiler. So the learning here is it's really good to have a ZKVM circuit, sorry. You have a RISC-V ZKVM so that you have one circuit that you can make it extremely fast instead of have evolving circuit that you have to redo all the optimizations every time. And finally, we figured that data movement between CPU and GPUs are definitely the bottleneck. If we do not solve this, ASICs won't help. No matter how fast the ASIC or your GPU is, if the bottleneck is on data transfer, nothing helps. So the solution we think here is to do ZKVM and GPU acceleration, GPU co-design, or ZKVM ASIC co-design, so that you can reduce the communication between CPU and the GPUs or between GPUs, so that you can achieve way better performance. Right now, we are not even saturate the GPUs, and NVIDIA are producing even faster GPUs. So I think we are having software or like ZK proof system side problems to saturate the fast accelerators we have. Okay, next slide. Okay, looking into the future. I think I'm tight on time, but I'll touch it briefly. Next slide, please. Next slide. So the first thing is all the ZK rollups are shifting to ZKVM based. For example, the scroll ZKVM, they build on handwritten circuit, but right now they're shifting to ZKVM. Same thing as ZK Sync side, MATLABs, same thing. I think what's not discussed a lot is ZKVM agnostic rollups. Because all the rollups right now are ZKVM based, actually it does not matter if you prove your rollup with scroll VM, ZK Sync VM, RISC-0, SP1. It's the same. You just pick the fastest, lowest cost one. So I think the competition between the ZKVMs are heating up because they are providing like an agnostic interface, which is RISC-V, so that like everything above don't care what kind of ZVM is underneath. And then one interesting topic is native ZK rollups and OP ZK rollups. I discussed this with ZK Sync founder yesterday. Like, what's the overhead of upgrading an OP rollup into ZK compared with you running a native ZK rollup from ZK Sync? I think his answer is that OP introduced extra overhead to make it ZK. So it has to be ZK native to, like the ZK rollup has to be designed for ZK to make it efficient. The next topic I can discuss maybe is decentralization of proof network. Why decentralization is important for proof network? I think our position is that we are not a decentralization first company. We're not taking decentralization as a first principle. The suppliers can be decentralized so that you can have cheap supply. However, for the infra itself, in the early days, it does not have to be decentralized. You can provide a pretty good service with a centralized proof generation service. And eventually, we will figure out the decentralized payment or the decentralized coordination. That's our position. Okay, I think that's all I have. Next slide, please. I have our Twitter and Telegram. So if people are interested, can stay in contact with us. It's just Snarkify _ZKP. Very easy to remember. I'm not sure if I have a question next time to take questions, but if you can find it around. Find me around. Yeah, thank you.
Thank you so much, Doctor.
Thank you.
I love calling people doctor. Okay, this next one's really exciting, especially because it's a live podcast recording. I am thrilled to be introducing you to my friend and education lead at ZKM, also host of the House of ZK podcast, who's one of our media partners for ZK Hub, who will be live interviewing ZKM's Chief Research Officer. Is that right? Yeah, that's right, Ming Guo.
Hey, hi everyone. Thank you, Annie, for the introduction, and really excited to be here today. I'm Alice. I'm from House of ZK and then also ZKM. I'm joined here today with Ming, who is the Chief Research Scientist and co-founder of ZKM, and I'll just be moderating this discussion about the vision of ZKM and then also Ming's vision for DAC economy, which is his overall view of the space. So very excited to have this discussion today. I'm wondering, Ming, if we can first start off with, since you're the co-founder, if you can speak a bit about the origin story of ZKM. So why did Metis choose to have a ZKVM spinoff?
Right. It's very natural because optimistic rollup, that's what Metis is built upon, needs a solution for the instant finality kind of shortcoming that people are seeing. So it goes like this. So optimistic rollup has instant confirmation. So it's pretty fast, but then you need 7 days to finalize the transaction. And that's seen by many as a shortcoming because people want to restore their fund and have it finalized instantly. So a solution would be to add a ZK rollup component to optimistic rollup. So yeah, so this is a joint program initially between Metis and OP. And the reason for MIPS is that the OP stack is also built upon arguing on the MIPS architecture. So it's very natural for us to go about ZK MIPS, and that name for ZKM. That's the origin story, yeah.
Nice, and then you also, I just want to dive a bit more into the why MIPS component because we're seeing a really big trend with a lot of ZKVMs, especially using the RISC-V architecture, but ZKM is using MIPS, and you mentioned that one of the reasons is because the OP stack also utilizes MIPS. I'm wondering if you can also talk about any other advantages that MIPS may have over other ISAs and why specifically we chose to use MIPS for our ZKVM.
Yeah, actually, you know what? MIPS actually is the true and best RISC real because it's the first RISC architecture that was pioneered by John Hennessy, the late Stanford president. They have a famous textbook on computer architecture. And John actually started a company called MIPS, which is the first RISC architecture CPU. It's been around for a couple decades. It's simple, it's very stable. And right now, the ZK MIPS, ZKVM solution, ZKM is built. We're to reach the third beta. It's pretty mature. And we're actually naturally just faster, 30-40% faster than our nearest competitors. And the reason is because MIPS is just 30-40% simpler. So that's the reason, one of the reasons. And I think the most pertinent reason for choosing MIPS over RISC-V is that RISC-V, well, by the way, RISC-V was started by David Patterson, the dual in that textbook. And RISC-V is new, but it's also very fragmented. because the core is only 47 opcodes. It's Turing complete, but no one builds a real CPU with only the core. So all the vendors add their own architectural focus, preference, their own opcodes. So it's not compatible on a opcode level. Meaning that if an app developer is not a problem, because the toolchain will abstract that away. But for ZK proofs, we're actually proving the execution trace of a virtual machine or CPU. And that matters, because if you have one opcode difference, that's another proof you have to seek. It's not the same proof. So for that matter, it doesn't really make sense to have a RISC-V, because your RISC-V VM will not possibly match most of the vendor RISC-V CPUs out there. And because we're doing a proof of a CPU, not building a real CPU, so the benefit doesn't really seem to be there. And right now there are other very ZK optimized virtual machines designs out there, for example, from LIDA. And so the reason for choosing a architecture like RISC-V or MIPS is because you can probably do a proof for a real world CPU application. For example, a lot of these sensors, routers, critical infrastructure CPUs are built with MIPS. So there's a reason that we want to probably generate a proof. And RISC-V is targeting consumer CPU. So most likely there's no point to do like ZK or Things Wisdom. So the point is just the moot. So there are a lot of reasons I can go on here, but that's the majority of the reason that if you choose a real world CPU, MIP is stable, simple, matching all of the legacy and critical infrastructure CPUs that's been around for 30 years. And you can probably just take an executable from maybe 20 years ago, generate a proof, and we can prove it online. That cannot be said for RISC-V. So MIPS is actually the best RISC for ZK VM.
Yeah, thank you, Ming. And it's very fascinating to see all of the decisions that come into choosing the specific ISA. So from it being with a streamlined set of opcodes to it being simple, and then also the fact that MIPS has been around for quite a long time. So very established architecture. So very interesting to hear about all of that. I wanted to talk a bit about more on the applications that ZKVM is currently working on with the ZKVM. So you mentioned in the beginning with the origin story that you saw a need to combine both ZK and optimistic. So for ZKM, you're specifically working on the idea of hybrid rollups, so combining both ZK and optimistic. Just wondering about if you could talk about the benefits for combining the best of both worlds and what new capabilities or opportunities will be led compared to just using ZK alone or just using the optimistic approach alone.
Right. So at the beginning, when the idea of rollup kind of first surfaced, there are two paths to the final ultimate scalability solution for Ethereum. One is the optimistic rollup. Another one is called the ZK rollup, but ZK here, stands for zero knowledge, is actually a little bit of a misnomer because on blockchain everything is already transparent. So it should be called succinct rollup, or ability rollup. So, but ZK rollup is very hard. I think many of the projects are still kind of code, from Vitalik, it's still on the training wheel. So, so naturally, optimistic rollup had already acquired 90% plus market share, and all the dApps built on optimistic rollup will need to change their API, their interface to move over to ZK rollup. Because fundamentally, ZK rollup and optimistic are not compatible, and it's not even possible to just wrap around because they have totally different philosophy and view of the finality and everything, right? For example, optimism rollup, we had this thing called instant confirmation, because the transaction is already put on L1, right? So the finality comes later. It's an afterthought. If there's a problem, then there's a compensation. But you can see confirmation as another kind of finality that's already there. And it's actually, for this matter, is actually pretty fast and cheap. And ZK rollup cannot say for the same. They have an instant confirmation, finality, but that's a totally different concept. So it's hard to convince all the apps already built over the years to move over. So from market share point of view, ZK rollup is kind of lost already. Well, that's my personal opinion. So for us, we would like to provide a solution for the best of two worlds, right? So you will still have an OP kind of shell. Then all the DApps developed for OP will need to change. They will take the benefit of a ZK rollup or a validity rollup component that will deal with withdrawal. So you will have the peace of mind of what ZK rollup can provide, and you have the instant confirmation and all that goodies for most of your transactions that does not involve withdrawal. So literally best of both worlds. And also Happy Rollup also kind of improves Optimistic Rollup as well, because the time used to secure the transaction is just time, right? 7 days. But 7 days sometimes is not enough. In the American banking system, it takes like 12 days for a check to clear. So 7 days is a compromise. But with hybrid rollup, you can actually go higher, right? Someone might be want to transfer like $1 million or more. They probably want to wait even more time, maybe 30 days. And hybrid rollup can provide the flexibility of longer or shorter clearing time, and also provide instant withdrawal like ZK rollup. So literally the best of two worlds.
Yeah, and thank you for also mentioning about having the choice to select different challenge periods for that window. So you mentioned that for a lot bigger transactions, people may want to wait even longer for it to clear, whereas if you're sending just maybe a very small amount, a week may seem long, but we could make it or reduce it to just a couple of days. So providing users with that choice between a short and a long period, I think is
right. That's the
very
idea
important to emphasize.
behind.
Yeah.
Hybrid rollup.
Yeah, thank you, Ming. And while we're on that topic of rollups, ZKM is also working on entangled rollups. So wondering if you can talk a bit about how the idea of cross-chain interoperability can be enforced without having to implement a bridge or without having to introduce any new trust assumptions.
Right. So so originally Rollup was developed to solve the scalability problem of Ethereum, but with the most recent Ethereum upgrade, I think that problem is mostly solved. So we need to look at another use cases for rollups. Rollups is actually a pretty strong mechanisms to go beyond scalability. So I think a big area that kind of overlooked is interoperability, right? So traditionally, rollup was thought as a kind of like a vertical bridge, right? It will just be within one layer one ecosystem. You don't do cross-chains, which is kind of like a horizontal bridging. But we here at ZKM, we looked hard and deep into the mechanism rollup. We found out that you can actually use rollups to do cross-chain quote-unquote bridging as well. But in order to do that, we actually don't want any bridges between different layer one blockchains. So there's a kind of hard question involved is that if you rely on bridge, you have to add security assumptions because a bridge does not have the security guarantee of either the source or the destination blockchain. So they have to have their own security, separate security mechanism devised, which has nothing to do with source or the destination, which makes it very brittle. So we decided to completely ditch any bridges. So we will call our solution a bridgeless bridge. And we also found out that if you want to do bridging without bridge, you have to ditch the most important characteristic of a bridge, which is ferrying information over. So for bridges for bridges not actually exist in the first place, you have to ditch that too. So you don't have any information ferried over from the source and destination. So what gives, right? If you don't have information over, how can you do a kind of beat your purpose, right? Which is to make a connection between two blockchains. So the solution is to use an idea we kind of borrow from quantum physics called quantum entanglement. Well, it actually doesn't have anything to do with the real quantum physics, but we borrow the idea because it works very similar, is that the universe exists, before the actually transferring of the information. You don't need to actually get that information over because the universe exists for that already. Yeah, this sounds a little bit magical and difficult to understand. So let me say that this is something we call precondition. So when you fulfill the precondition, you actually don't need to transfer the hard information over. So with that, we implement something we call Entangled rollup, which is a bridgeless bridge. And you can have the same security assumption of either blockchains. And so it's very secure. You can actually do interoperability for native assets, which can never be done with any bridges that we implement today. So let me just stop here. And this is exciting technology we're developing on top of our ZK-MIPS, ZKVM. We can do this because we also implement the universal L2. You don't need to differentiate between different L2s because in our eyes, all the proofs are ZK-MIPS proofs. On top of it, you can have EVM, MoveVM, or even C++ from a real-world application. For us, it's all the same. It's the same proof that being used to secure everything. That's why it's a universal L2. That's why we can build Entangled rollup on top of it. And we call this a bridgeless bridge.
Yeah, thank you, Ming. And it's pretty incredible to think that you can use the underlying L2 to enable for that cross-chain messaging, for that native cross-chain asset transfers without having to introduce any kind of new security assumptions. So
right.
It's pretty incredible to think about that, yeah. And just wondering about our stage right now with developing Entangled rollups. So recently we had a spin-off project called Goat Network that is a Bitcoin layer 2 and is the first step for achieving this. I'm wondering if you can speak about what comes next for Entangled rollup, what stage we're in, and then also the long-term vision for building out this network.
Right, so Entangled rollup can connect any blockchain, any L1 blockchain. So we decided to start with Bitcoin because Bitcoin is very hard. We all know that Bitcoin script engine is not very capable. So it's kind of hard to develop a verifier like other, more capable blockchains. So we developed Goat to utilize sustainable yield for very exciting BTC L2 applications, not just for Bitcoin, but across all blockchains. So this is something like differentiate Goat from other BDC-L2 projects. Next step, we're looking to develop other ecosystem, for example, the Move ecosystem, like Sui, Aptos, and the possibility is limitless, so we want to build a universal settlement network based on top of Entangled Rollup and connects all the blockchain that can support ZK Rollup.
Yeah, thank you. And very exciting time indeed for all of these new applications coming up. But while we were on that conversation of rollups, I'm wondering, are there any sort of applications that ZKM is considering to build in the future beyond hybrid rollups, beyond the Entangled Rollup network?
Right. The Entangled Rollup, it's not just for financial transactions. It's a universal messaging protocol. And upon this, not just the financial apps, traditional financial apps for blockchains, you can actually do applications that beyond financial transactions. I'm looking into like GameFi, SocialFi, and we can probably redo that and beyond. And the power of this technology is limitless. We'll see applications that never been possible before. So let me just paint this vision for you, and I will not hinder the imagination by just limit them to the things like we have today.
And I also wanted to transition a bit into DAC economy. So just to give some context, Ming wrote a light paper a couple of years ago just shaping the vision for how he sees the Web3 space today. And that vision is DAC economy. I'm wondering, Ming, if you can speak about what drove the vision behind it and how it differs from our traditional economies and how we perceive value today.
Right. This may sound like a little bit unorthodox, is that when we see the space of decentralization, we equal them into blockchain and crypto. Crypto is another kind of, let's say, money currency. And with that, we have what we call like decentralized banking. So we could provide banking to people who doesn't really have like banking services before. So this is a very hefty goal, but just to remember, this is still not the ultimate decentralization, because decentralization is not just one dimension. So the dimension of money. For every aspect of human life, you can sort of do decentralization as well. For example, decentralize the whole value system. Value is not just one-dimensional. I see value as multidimensional. Let me give you some example. We, of course, know that crypto is for providing access and service to the unbanked, because there are like 2 billion or even more people that don't even have a bank account. Without bank account, you cannot easily join the global economy as we have today, and then your income is very limited. And basic approach to solve poverty, for example, need people to have access to financial services. Otherwise, you couldn't get connected to the whole global economy. Then obviously that's very difficult to lift poverty for many people of the world. But that is only one aspect of poverty. There are a lot of value creation process that people can't access or can turn that into income, right? Because for today, income is the only way for you to get subsistence support for your living, right? For your life. So, for example, domestic service. Traditionally, women provide domestic support, raising children, and do a lot of house chores. And these are not content in our normal economy. They're not paid. These are obviously valued, but they're actually not valued, right? So these I call, aside from unbanked, I call this unpaid. There's a lot of work unpaid for people who are providing those valuable economic activities. So that's something we also want to decentralize and to provide value for. That's the most important thing. And there are more. Also, for a lot of work that human do, for example, creative work, right? Artists, right? A lot of artists, they create arts every day, but maybe only a very small slice of those are actually turned into income. Most artists they're just bankrupt, right? They're broke. So a lot of value, what's the difference between some painting, some digital art, right? Some graffiti that could sell like millions of dollars, to someone on the street, right? Just had the inspiration to paint something I think many people will think also as valuable, but they're just there, not getting paid, not getting turned into income. So I call those unvalued. So now we're only tackling unbanked. What about the unpaid, unvalued work, human creations? They should have value too, right? And we actually think they have value. It's just they're not participating in the global economy. They're not turning into any income. So dark economy is about using the technology we developed for crypto and blockchain and turn them into technologies that can actually turn the unpaid, unvalued into income that can participate in the global economy and provide subsistence for every human being's creation, their sweat, and their aspiration. Imagine you can turn your aspiration into income, and that is the way to fulfill the ultimate goal of decentralization. And we aspired from the beginning of human history to get every life their value worth.
Yeah, thank you, Ming. And really important that you emphasize that a lot of our times in our traditional economy, we only capture a fraction of the value that's actually generated. You mentioned that a lot of value that comes from creative work, from housework even, gets lost and it's not accounted for. But hopefully when we have decentralized economies and when we reach the vision for DAC economy specifically, we can capture value in all regards. So it's a very, very exciting future ahead of us. But just as a closing question before we wrap up, I'm wondering if you have any last thoughts or any advice you want to give to the audience?
Right. Let me actually closing that with the vision I just mentioned. I think one way that we all know is the challenges of AI. Right. It looks like in our current economic scheme or regime, AI will just take work away from people, and everyone will become unhired. Will become lost their jobs, even ourselves, right? Because AI can just do anything like human can. And the reason for that is actually rooted in the economic regime that I talked about, right? Because it can only turn a little bit of value, one dimension of value, into income that can sustain people's life. And if you think from a different point of view, if all these values are to be fulfilled, we can actually turn every kind of human activity into income. And then we don't need to worry about AI taking away our job, because in that new vision or world, AI can be equal partner with human. So this is something I'm experimenting to build. It's a new project I'm doing right now called Last AI. Yeah, we try to build a system with human AI as co-partners, create value, multi-dimensional value, and that's to fulfill the vision I was very excited to talk to all of you, the unpaid and the unvalued, and turn AI into our partner instead of our greatest rival, which is the past. Like if we rely on the Web 2 world, the corporation will probably monopolize all the computing power to for AI world overlord, right? That's the one way that human can end up with. Another way is I try to build with Last AI, which is a coexistence with AI and humanity. Yeah.
Yeah, and hopefully in the future we can find a co-partnership between us as opposed to one trying to compete over the other. But very exciting times ahead, and thank you again, Ming, for telling us about your insights behind ZKM and then also the overarching insight behind the whole space with DAC economy. So some really great insights, and thank you all for joining as well.
Thank you, Alice.
Thank you.
Thank you all.
Amazing. Oh my gosh. I'm so glad I'm right at the front because that was incredible. I love a good origin story, but I also really appreciate you taking the time to talk about your why behind the work that you're doing. You know, ultimately, a topic like ZK is so highly technical that we forget like there's real world value and significance in serving communities that don't necessarily get represented in a place like a tech conference, right? So I think about mothers, I think about individuals of color, those who are
Definitely.
yeah, those who are and don't have access to the types of things. And I think people forget too that there is a significant number of people in the world who don't also have access to technology. So as wild as that sounds, like we have the opportunity to do something really remarkable. So thank you. Thank you both. Those are great questions and even better responses.
Thank you.
Thank you.
Okay.
Right.
Oh, fun fact for those of you in the room who feel like this is a little bit, intimate, there's 10,000 people who are watching this live stream. So, yay.
Yeah.
Nice.
Nice. Thank you all.
Thank you.
Okay, on to our next solo presentation. We have Matthew from Kakarot. I'm totally saying that wrong. You're gonna correct me, right?
Everyone. I'm super happy to be here, and I'm going to present you and talk to you about Kakarot. Kakarot is a company that is building efficient and secure EVM probability solutions for various technology stacks, but mostly using the Starknet stack and the Starkware technology. So just for some context about Kakarot, Kakarot was initially a project of the Starknet ecosystem and later evolved to be a full-fledged ZKVM and EVM probability solutions. Why? Because we believe that all software will eventually be provably secure, and we believe that Ethereum and Bitcoin together are going to be the settlement layers of the internet. And as Vitalik said a few months ago, probably in a few years, all rollups are going to be ZK rollups. And we agree with that take, and we're building with this vision in mind. But ZK rollups are, or had until now, some user experience hiccups, let's say. And that's why optimistic rollups until now had the lead on the UX and usage of ZK rollups. But ZK rollups have major advantages, and we want to see these advantages more represented in the real usage of Ethereum rollup technology. These advantages is the increased scalability, because you can totally parallelize the proving of your ZK EVM or your ZKVM. And unlike with optimistic rollups, you don't have the requirement of locking a lot of capital for economic security of your rollup. And finally, one of the major drawbacks of optimistic rollups is the long finality time. You have to wait until the dispute window is over for your funds and your transactions to be considered final, which can take up to 7 days. And ZK technology allows you to bring that time window down to a few hours and maybe a few minutes in the future. But ZK EVMs have a lot of limitations. They're expensive and they're hard to maintain because you need a lot of engineering resources, and the Ethereum protocol and the EVM is constantly evolving. So when you're building a ZK EVM, you need to build an EVM thinking about the fact that that EVM is going to change a lot in the next years, and you need to be able to maintain that EVM. And EVMs might run into problems when you're developing your EVM to target a specific kind of prover, and that prover ends up being not efficient enough compared to the competition, and you always want to make sure that you can transition your technology from one prover to another, which is kind of what we're doing at Kakarot, because Kakarot is currently proven using Starquest Stone Prover, but the Stu Prover is coming in the next month and will bring up to 100x or 1000x improvements over the current prover. And because of our architecture and tech stack, we'll be able to benefit from these improvements from day one, and that will considerably change things about the position of Kakarot in the ZKVM landscape. So there are different ways of building ZKVMs. Let's say that the first ones to build ZKVM, they like ZK single squall, they had to use quite complex approaches, which is either you are writing ZK circuits by hand, or you are compiling a higher level language like Solidity to assembly code that can be proven. So that's, for example, the ZK-Sync approach. You take the Solidity compiler, and then you have like an intermediate target, and then you compile that target to something that you can prove. The problem with that is, in the first case, it's not very scalable to write all the ZK circuits. It's not very secure. I mean, it can be secure, but there's not a lot of people that are competent enough to audit these secrets, and it's hardly maintainable. In the second case, it actually leads to some incompatibilities with the default EVM spec. So for example, if you do like a create transaction on ZK-Sync, the create2, the created address is not the same as the one you would expect from the EVM spec. And that might sound minor, but when you're developing an app that is deployed across chains, you always want to have the most simple flow possible, which means you would like to have the same address on all chains. And if you don't have full EVM compatibility, this can be like a serious problem when developing, and it makes bringing multi-chain apps to your network a lot harder. But now we have a new way of building ZKVMs that was demonstrated first as a proof of concept by RIS0 last year, where they basically took an existing execution client like Reth. They used Reth as the starting points, and they used the RIS5 instruction set, compiled Reth to RIS5, and then they were able to prove the code that they compiled to RIS5, which means you can take basically any Rust code written in general purpose programming language, compile it to an instruction set that can be proven, and prove that instruction set. So this is great because you're actually approaching building ZKVMs with an engineering first approach and not with a cryptographic first approach. And that makes maintaining ZKVMs super simple. Like, Reth is getting updated, then you can natively benefit from these improvements and prove these updates. The only problem with that approach is Reth was not built to be proven. And the compilation to RIS5 is not necessarily the most efficient approach that you can think of. And that's where Kakarot comes in, because Kakarot is designed to be proven from the first principles. Why? So the first thing is the tech stack. Kakarot is using the Starquest tech stack, the Starknet tech stack, which is composed mainly by the Cairo VM. So the Cairo VM is one of the first ZKVMs that was put in production, and it has secured Ethereum L2s for over 4 years now. One of the most major use cases was a StarkX, for example, DYDEX. That was one of the most successful scalable solutions available a few years ago when it comes to DEX trading. The thing is, DYDEX and StarkX was not a general purpose L2. It was very specific to trading operations. But the thing is, if you want to have general purpose computation and benefit from people building any kind of apps, you want to have a general purpose L2. And if you want to have a general purpose L2, then you have different solutions. Either you go the EVM compatible way, or you go the non-EVM compatible way. If you go the non-EVM compatible way, then you don't have the tech burden of the EVM, and you can innovate on what you're going to build. And this is the path that, for example, Starknet had chosen. The problem is that like 95% of stablecoin supply is actually on EVM chains. So if you're not building for the EVM, you kind of miss on all that TVL and all that activity that your network could generate. And so Kakarot reuses the Starknet tech, but uses it to build an EVM compatible software. And so the thing is that you can take a high-level programming language like Cairo, as an engineer, and you can write an EVM. You just follow the EVM spec as Cairo, and your EVM becomes de facto provable. You can just run it and generate an execution trace, send it to the stone prover, and prove your trace. And because Kakarot is built, is made to be provable, that means you don't have a lot of inefficient operations, because we have thought about how to build Kakarot by removing unoptimized operations that were not strictly necessary for the provability of the EVM. And we also made sure to make the computations as friendly with the underlying ZKVM as possible. And that's possible because unlike the RISC-0 approach, we're not taking a standard code base and making it provable. We're thinking about it when we're building it. So let's take a look at the standard example of a ZKVM flow. Basically, you have like a user that sends transaction to a regular EVM client. That could be Geth, Reth, Bezu, or even Kakarot in the future, although for now it's not fully compatible with L1 requirements. The RPC is going to like send the transactions to a node, and the node is going to execute it and execute the transaction in the EVM. The state is going to be updated, stored in the DB. And you can actually do this quite fast, because you don't really need to prove every transaction in real time, although that's the standard we like to see pushed in the future. So once you have sent all your transactions, you can wait for thousands of transactions or thousands of blocks to be processed, and you can batch them all together every once in a while and send them to a prover synchronously. And that prover is going to batch all the blocks that you have to prove, compute the new state root, and prove that all the transactions were valid, and send that proofs to verify on L1. So far, it's pretty standard. And the way Kakarot is doing that is, the first product that Kakarot is making is building a ZKVM on top of a Starknet. So the architecture is slightly different, but the end result is the same. So a user would just send a transaction to an Ethereum RPC, and the transaction would actually be converted to a format that is compatible with Starknet. So what you have is, you just use regular EVM tooling like MetaMask, send your transaction to our RPC that wraps it inside a Starknet transaction, and then we just send your transaction and what you have signed to an EVM interpreter. The EVM interpreter is just going to run the transaction data that you have sent inside a Starknet smart contract. So you can actually deploy a smart contract on Starknet that is an entire EVM interpreter that allows you to deploy contracts, run pre-compiles, do like complex EC operations, like EC pairings or any kind of operations required for ZK, and everything runs inside a smart contract on Starknet. And then, like the proving is actually handled by the Starknet chain itself, and the state updates are handled by Starknet. And you just need that small component of the Kakarot EVM to prove any EVM transaction. So because Kakarot is deployed on Starknet, the first product, it means that you actually have two ways of using it. Either you go the standard EVM flow, but you can also think that because it's deployed on Starknet, you can actually use anything from the Starknet state. You can actually interact with any Starknet contract. So that means, let's say you have an application on Starknet that's working really good, but your users, they don't necessarily want to install new wallets. What you can do is, let's say you have your Starknet call data to execute your transaction on, for example, one of the leading DEX, which is like a Uniswap v4 DEX called Ekubo. What you can do is just take your TX data, convert it to EVM bytes, and then we can implement inside the Kakarot EVM custom precompiles for execution optimized for Starknet. And in that case, you can just, we have developed a precompile that allows you to call any Starknet contract from the EVM, which means Starknet is now multi-VM, and you can use it from the EVM side, from the Starknet side, or both together. So we're still in testnet. Our mainnet launch is planned for next month, but we're seeing good tractions with more than 100K active addresses, more than 100K Twitter followers, more than 1 million transactions processed. And this is good, but it's only the first step towards our vision of EVM probability, because with one code base, we can actually have 4 different use cases. The first use case is what I just presented, making StarkNet EVM compatible and multi-VM, but it's not the most exciting one. Once we have EVM available on StarkNet, we can start selling ZKVM app chains running the StarkNet stack. And once we have that, we can actually start thinking about how do we make a general purpose EVM backend for proving blocks. And that's going to be very interesting because it's super aligned to the vision of having real-time block proving at the protocol of Ethereum. Like Ethereum could just, block producers could produce blocks, compute the proof of the block computation, and send that proof along with the blocks to other nodes of the network, which would only need to verify the proof to attest that the block was computed properly. And because Kakarot is designed with this provable approach in mind when engineering the code base, that means we could get a really good approach to real-time proving, and we think that our solution, whose benchmarks will be public next month, our solution is probably going to be a 10x improvement of the state of the art of EVM proving right now. And of course, what's also really interesting is how to make a ZKVM running on top of Bitcoin. So we're working with Starkware on that. Starkware is pushing a lot of research on how to use OPCAT to have Stark proofs verified on Bitcoin. And if you have followed, you know that Kakarot is deployed on StarkNet mainnet, and you can launch ZKVMs using the StarkNet stack. So that means if OPCAT is enabled on Bitcoin, any StarkNet chain becomes can be settling on Bitcoin. And if you settle a StarkNet chain on Bitcoin and that StarkNet chains run the EVM, that means you can actually have a ZKVM working on Bitcoin with no security compromises. Thank you. If you have any question, feel free to ask. Yes? So there are actually 2 different reasons why we think that. So the question was, sorry, can you?
Yeah, you mentioned that your ZK EVM would be much more performant than any other ZK VM currently in production. So what were the reasons for that? Is it because it's going to use Starknet and its Circle Starks and other proving infrastructure, or is it something else?
So there actually are multiple components to why we think that. The first one is that, as I said, we thought about designing Kakarot from a provable approach, which means that when you're going to do EVM block proving, you basically take an input, which is the sparse Merkle tree of the state that's going to be changed during the block, and the transactions to run. And the output is the new state tree and the change state. And the thing is, and the good thing about Cairo is a language that expresses assertions on memory cells. But the memory cells themselves, they don't really have to be like the computational intensity of calculating what's going to be put inside these memory cells is not done at the Cairo side, it's done by the prover. Which means from the point of view of Cairo, you're only verifying whether some constraints inside your memory are holding. It's actually a language to describe constraints. And when you think about this, when you're building several components of the Kakarot EVM, you can actually think of clever ways of how do you design each component so that you are making the least amount of operations in the Cairo language, and you let the prover fill the memory, and you don't let the prover fill the memory with something that would not be sound or that would not respect the specification. So when you have that in mind, you actually have another approach to building a ZKVM than just like you would do in Rust, because you're taking advantage of the non-deterministic memory approach of the Cairo VM to only prove the assertions that you're making. And so the hard work is done by the prover, and you're only in your trace generating these assertions. So that's the first step of why we think it's going to be a lot better. And the second one is, of course, that the Stu prover is going to be the best prover on the market, probably for a few months, years, or I don't know how long, but compared to the current state of the art, so today we already are seeing good results. We've run simulations of, for example, how much does it cost to make an ERC20 transfer on the Starknet mainnet. It's on par with other competitors. But if you make that cost go like 100x cheaper or 1000x cheaper, then we're going to see a lot of improvements. And if you remove the Starknet component that I presented and just keep only the block proving system, then you can have a lot more optimizations possible, which will lead to that performance increase.
Okay, any other questions for Mathieu? Did I say that right? Mathieu? No. Matthew, okay. You know, in Canada, it's Matthew. Okay. Thank you so much for your time.
Thank you.
Yay. Appreciate the question as well. I know it's never easy to ask in a big group of people. So before we get to our next panel, which is one that I'm particularly excited about because my colleague Zach, engineer lead, is on it. He's not here yet. But I wanted to make a quick announcement for anybody in the room and then anybody who is looking to exit the room to do something different. Holonym is hosting ZK Trivia in the Human Keys Lounge. That's just at the end of this hall. So if you're interested in partaking in some ZK Trivia and earning some rewards, showing everybody what's up, that's the place to be. In the meantime, I'm gonna suggest that maybe we take like a quick stretch break. Do we want to do a stretch break together? Yeah? I don't know, do you guys want to do a stretch break together, live audience? I feel like maybe you can get up, move around. Actually wore pants today. I mean, I always wear pants, mostly wear pants, but I wore pants particularly today so I could do lunges. We could do lunges on screen together. No, come on, everybody up. Let's get up. Do a little shake. I mean, you're either on your phone, your laptop, or sitting in a chair, so I think it'll be nice just to do a quick stretch. That's right, yeah, look, even the videography team is doing it. Yeah. I wish this would be a great time for some like exercise music. What do you think? A little left, a little right. Everybody who's online like, right now is like, what is she doing? Who hired her? Don't worry, you guys. Nobody is paying me to do this. This is all volunteer. Okay. So for the speakers who are leading and contributing to the next panel, I'm just going to ask that when you do join us on stage to come around and to my left, to your right, so we're not blocking what's being recorded online. Yeah, we're gonna start shortly. We're a little early, which is kind of exciting, and I have everybody on live stream stretching with me. This is, you wanna join us for the stretch, Zach? A little lunge? No. Okay, well, for those of you who are on the live stream, I mean, many of you in the room have heard this story already, but I do really enjoy talking about, oh, there's music, okay. This isn't really exercise music, though. They're actually stretching. Okay, I'll just take a break, and we'll come back right before the panel starts and have hopefully a whole audience to do that. All right. Okay, so for those of you who were not here earlier, there was a bit of an exercise break because we were so on top of programming that we were early. Yay! Yay! No, honestly, that never happens. Like, we're usually 30 minutes or an hour behind schedule, but of course, you know, Irina and Rux are exceptional at what they do, and that's why we are, you know, prepared with exercises and walks around the conference. Okay, so not to actually further delay us, I want to introduce our next panel. I feel like there's a little bit of like discussion happening back there, but while there may not be a completely packed room today, I do want to highlight that there are more than 10,000 live viewers on our live stream, so no pressure, no pressure, no pressure. Okay, introducing our next panel, hosted by Ovia from Octo and CoinDCX. I am honored to be presenting the group that will be discussing the challenges of building on privacy blockchains. Yay! Come on! Wow. I think there's introduction music, yes.
Hey everyone, thank you for joining us today on what promises to be a fascinating discussion on privacy enabling blockchains and their challenges. Privacy is often talked about as a core principle in blockchain, but it's never kind of realized in the way that we want, which is scalable, secure, compliant, and even one of the core principles of the Web3 ecosystem is being transparent. So we're here with this amazing panel of experts to talk about what are the challenges that occur in building privacy-enabling blockchains. So we have Zach from Alio. Hi, Zach.
Hello, hello.
Adam from Aleph Zero.
Hello.
We have Zane from Horizon Labs.
Hey, everyone.
And Rahul from Aztec.
GM.
So I just can't wait to hear all of your insights on this. But before we start, I'd just like to go around and have you introduce yourself, what you're doing at your various respective protocols, and what the protocol does as well.
I'll start. I'm Zach, an engineer at Alio. I was building a wallet on top of Alio before. And at Alio, we're building a layer 1 blockchain. It's actually live on mainnet now, and it's the first private programmable blockchain. We don't need to clap every time.
Hey, so I'm Adam. I'm a cryptographer and one of the co-founders of Aleph Zero. And right now we focus mostly on building a privacy hub for EVM, which is actually a universal privacy pool for interchain operations. And we think about it as a universal wallet, and our main front end for it will be wallet kind of front ends.
Thank you.
Hey, everyone. I'm Zane, CTO of Horizon Labs. At Horizon Labs, we're builders on 2 platforms. One is Horizon, which is an L1 blockchain that is home to the Zen cryptocurrency. It started out as a fork to Zcash, so it was a privacy coin. And then the other platform is called ZKVerify, also an L1 blockchain solely focused on proof verification.
Hi everyone, I'm Rahul. I'm a senior PM at Aztec. I'm leading our testnet. Aztec is a privacy preserving layer 2 on Ethereum, since there are L2s on Solana as well. We are aiming to launch fully decentralized on day 1, which is something no L2 has done. Excited to dive deeper.
Amazing. So inspired by the talent here. Let's start by looking at the big picture. So blockchain's core principle, one of the core principles of blockchain is having transparency, right? There's no centralized entity controlling anything, and anyone can audit what happens on the blockchain. But it's always at tension with when you want to bring privacy. How do you get privacy and blockchain in the same in the same system, right? So how do you guys view this tension, and what does the state-of-the-art technologies do to kind of balance these 2 concepts? Zach, why don't we start with you?
Yep, so I mean, how we view it is that if you want to have payments and actual use cases that we use every day, or businesses transacting with stable coins, or voting systems adopting blockchain technology for the cryptographic verification it offers, you have to have some form of privacy. The internet started without it, then it adopted TLS, SSL, you had HTTPS, and so that's what we want to introduce for the blockchain realm. And to get to the technical level of how we do that, we use a technology called zero-knowledge cryptography, zero-knowledge proofs, and that's basically, I can prove something to someone without revealing the underlying information. For example, I want to prove I'm older than 18, but I don't want to reveal my date of birth. And that's a very simple example. And you can think of that for transactions on a blockchain. If you push the computation of the transaction to happen on a user's device, like their phone or their laptop, and they generate a proof that they ran this code correctly, then they only have to put the proof on the network stored on the transparent ledger that we're talking about, and the inputs and outputs to that function, and you encrypt those. And so via zero-knowledge proofs and encryption, you achieve privacy in a transparent realm. That's how it's done.
Adam, what's your take?
I mean, there's a question where actually I think most of us have similar takes, so maybe I'll just try to extend the previous opinion. So, yeah, I mean, that was a very good explanation of how it is actually done. What is often asked is, like, why do we want privacy on blockchain? So I think this is in a way, incorrectly posed question. I mean, we do have non-private blockchains now, not because someone wanted non-private blockchains, but because of technical limitations over times where the blockchains were invented. So it's not like this is the universally good thing to have non-private transactions. No, this is actually very weird. And if the blockchains would be designed with only features on mind, not caring about the technical limitations, surely they would have privacy from day zero. So like what we see the privacy movement is trying to achieve is that it's trying to achieve this obvious feature base that the blockchain should have from the get-go, and they just didn't because that's hard. So yeah, that's my take. Thank you.
Zane, anything to add?
No, Adam's said it really well. Yeah, I feel like, I mean, for me, privacy and transparency are, yeah, two sides of the same coin where you want to be transparent with what you're doing in a way that still retains that privacy. Privacy is this fundamental right for all of us. I studied computer science and also was very interested in psychology. And it was very interesting to me where, you know, in our physical lives, we care so much about privacy, and really we have all these like physical walls up there, and you know, the privacy is that fundamental right. And I want to see that extended into blockchain in a transparent way, of course. And as Zach mentioned, ZK proofs are just one of the mediums there.
I'll add a spicy take here, just to keep things interesting. I think the idea that blockchains care about transparency is a false dogma. If you go back to 2014, blockchains were advertised not as transparent, but trustless. There was no talk about transparent. I think just because all the blockchains were public at the time, people just assumed the goal of a blockchain is to be transparent. I don't think any systems are meant to be transparent at all. It was just, that's the best cryptography could do at the time, and we are lucky now that we can do more. But to actually answer your question, most of the teams here work on ZK-based privacy, right? Am I right using that? Including Aztec. ZK does not allow you to do private shared state. So most of DeFi, or things where people actually need transparency for, will anyway happen on public land. The only place where you can have private shared state is like if you start using TEs. I know Zach called Alio like the first programmable blockchain. I actually think that's not true. Like Secret, Fala.
Programmable and private.
Secret and Fala are both programmable.
They do not have,
especially Secret.
I mean, they do the computation in trusted execution environments, sure. But then the fee that is paid is public. You can delegate that fee.
Sure.
It's not maths that is giving them privacy. It is that trusted environment trusting Intel's hardware, right? So
Sure. So now we're talking about like, okay, what is private, what's not, right? So for example, last I checked, please correct me if I'm wrong, Alio did not allow privacy for function call data, right? And then I can say, well, that's not privacy. That'll be false of me to say that because privacy is a spectrum. So I think it's unfair to call. By that logic, I can call Alio
you can see
public
what
as well.
is called. You can see this function has been called, but you cannot see if the transaction is fully private, because we also allow someone to have certain public state, certain private state. But if everything is private, you will just see a transfer was executed. You cannot see who, you cannot see to whom, the balance. So,
so that's the answer to transparency, right? You have a public state, and most things will go on in public state.
Okay, this is actually really interesting. So it kind of brought to light that we really don't, everyone has a different definition of what privacy is. Also, maybe like one of you can actually define it for our audience on what we're exactly talking about. What do we actually mean by privacy preserving blockchains?
I can take a gander. Privacy is basically, I think of it, if I do an action, like think of it on the internet. If you send some data to someone, like on a messaging app, other people cannot see that message. Like if I send a message to Annie, other people cannot see that message. So by privacy, by default, only the people interacting can see the message. Everyone else cannot see. So by privacy, I mean what you're doing with a blockchain, or just what you're doing is hidden, right, by default.
So as I understand it, you have to choose what data you want to keep private, like that no one else can actually read the
I think it
message about.
should be the contrary. I think it should be you choose what you make public. By default, it should be private.
Oh, okay, that's interesting. Cool. So we spoke about transparency in privacy-preserving blockchains, but scalability is also a big problem that it's generally there in Web3. Like we can't bring Web3 to the masses if we don't have scalability, right? So what, in your respective protocols, what compromises did you have to make? Do you think you have achieved scalability with privacy? Or do you think you had to make adjustments and some trade-offs? Maybe we can start with Rahul.
Yeah, so let's define all the different ways of scalability, right? So from the user's point of view, it's TPS. From the sequencer, validator point of view, it's like how many people, how many nodes can you have, how much bandwidth can they share with each other. Then there is like scalability from the data availability point of view. So I'll talk about the latter two first. Aztec will be a layer 2 on Ethereum. Ethereum has taken the approach that L1s are much harder to scale, and that's why you have L2s, vertical scalability. We use blobs. That's what gives us scalability for data availability. Yes, blobs are very minimal right now, but I think they're doing some great work to increase it with PRDash to multiple megabytes a second. Otherwise, you also have EigenDA, Celestia, a bunch of really cool projects. And then on our nodes, we'll kind of have around like 5,000 to 6,000 node capacity using our proof of governance network that we'll have. The trade-offs there are you can create ZK proofs, but like they shouldn't be so big that nodes, when they're gossiping with each other, they can't gossip too much. The trade-off comes like, okay, can home stakers actually do this? I know Ethereum loves home stakers. Can we actually also do it? What's our RAM requirements? And then you get into some really fun engineering problems that I can go into detail about, but it's like, okay, how can we design our VM such that you have more columns, lesser rows, so you have lesser proof sizes, lesser bandwidth, on and on. And like you do those kinds of fun trade-offs to get to higher TPS or higher nodes.
Is there like a gold standard of what do you measure scalability in? Like what is good enough for scalability in privacy blockchain?
This is a hard question, like because so few companies have done this. There is no real gold standard, right? The gold standard is how best can you do. So you just keep pushing the limits. It never ends. It's kind of like a cat and mouse game. You put a product out, we take like how many ever years to build it. By then ZK advances, kill the product, new product, keep going on and on and on until you can actually compete with like, it's just an order of magnitude more than public blockchains.
Always room for improvement, right?
Always.
Anything to add?
Yeah, always room for improvement. Well said. In terms of scalability, it reminds me of this concept that the ZK researcher from the Soundness Protocol had mentioned. He calls this concept continuous proofs. What he means by that is that he views someday in the near future that there will be proofs that are generated continuously, like just like data. For example, data is generated continuously, it's overflowing. We as average humans, we generate, I think 2023 numbers were like 150 megabytes of data per person per minute. So this researcher feels the same way, where proofs are going to be generated pretty much every minute and multiple of them. So that could come from all the Web3 apps, DeFi, privacy. It could come from even Web2 and this budding area of Web4, which is AI and IoT. So for us at Horizon Labs, we believe that these continuous proofs will happen. They will proliferate. And we're attacking it from more like a holistic standpoint. There's this like proof value chain. You can attack it from proof generation, proof aggregation, and also proof verification. So we're building a blockchain that's solely focused on proof verification, specializing on it, all the different proof types that may come, that new, and we want to bring costs down and really keep up with the innovation frontier.
Adam, your point of view?
So how I see it is that in ZK scalability, I mean, there is inherent trade-off between scalability and latency or user delay. And on the other hand, latency is perhaps one of the biggest obstacles for ZK adoption. So like, why people are not using private actions so much? Well, because it's slow, because they need to download much more blockchain data, which takes time, and they need to generate proofs, which takes time, and sometimes even they need to wait for the proofs to aggregate, which also takes time. So it's just way less user-friendly. And then there is this trade-off between scalability and this delay. So like how we are approaching to it is that we don't scale more, we try to don't scale more than we actually need. So like we're trying to be as fast as possible right now. When we grow our user base to a point where it's actually unbearable anymore, then yes, we hope that solutions like, for example, Nebra or solutions for this aggregation, for creating recursive proofs will be mature enough that they can be just added on onto what we're doing. But yeah, I think right now, like from the get-go, most projects can reach the scalability of maybe 30 TPS because this is all about proof verification on chain. So like with the new developments, like for example, Ref, the Rust-based EVM, I guess we can get it much higher without actually any changes in how we verify the proofs, because the gas limit can go just higher. So perhaps we can go like for free, we can have around 100 TPS. And like if we want to go above that, well, currently some trade-off needs to be done, and this trade-off will be with latency. So like as we're right now trying to mostly solve UX problems by fixing the proof generation time and doing a lot of this level optimizations, we don't go much into this scalability area yet.
Understood. Just a quick follow-up on that. I mean, the current non-Web3, non-private, like, I mean, you can say private, systems like Visa, MasterCard, they go up to like 30,000, 40,000 transactions per second, right? I mean, can we even get there? Is that like a number to even aspire to? Or how long do you think that it'll take to get
I mean, with very caution, yes, I do think it's viable numbers to reach. I guess that would add, I don't know, 10 maybe 20 seconds to the waiting time by how this things looks now. And well, currently we have like together proof generation, on-chain action and verification done within maybe 3 seconds. So like for us, additional 10 seconds is a lot. Like from the user perspective, like no one has actually thousands of transactions per second in blockchain. I mean, I know there are some chains which are claiming that. I don't.
100,000 TPS to the moon. What are you saying?
Yeah, but I mean, like, but the real usage. When it comes to the real usage, I don't think there are chains with this kind of usage. And when it comes to the capabilities, well, like what people want to do on chain usually are smart contract interactions and not just the regular financial transfers. And when it comes to smart contract interactions, it's way harder to reach these numbers, like this thousands and thousands.
Could I interject? Okay, so if you compare apples to apples, right? So Visa level privacy on blockchains, how do we get there? Okay, so on Visa, transactions settle every 7 days. So you're looking at in blockchain lingo, that means block time is 7 days. You see it on your bank in 1 day. So pre-confirmation time is like 1 day, right? And on top of that, you have all of the validators can see everything, but the users cannot see anything. So you have encrypted mempools with 7 days block times with 1 day pre-confirmation. In blockchains, instead, we do 250 millisecond block time, 250 millisecond pre-confirmations with around 2 hours block time, let's say, roughly. L1s have it way, way faster. L2s, if I define block times as like the time to settle on L1, then you can average it out roughly to 2 hours. So like by that method, blockchains are already like at least 100x faster than Visa. If you want to compare exactly apples to apples.
That's really interesting. That's a good point of view. Often, like as users, we tend to miss. We see that the transactions happening immediately, but we don't really realize that they're not actually confirmed. Okay, so we spoke about scalability, transparency, but like when you actually start building privacy systems, you're kind of introducing a whole new vector of security attacks, right? I'm just curious to know more about like the breadth of what kind of attacks are possible in privacy systems. Zach, maybe you'd like to take this.
I mean, I think, I don't know what like new vectors you're introducing, but as long as given the system you're building is, for example, in our case, using zero-knowledge cryptography, if you have the validators verify that this proof is correct, the zero-knowledge proof generated, then you can trust the maths and that this has happened correctly, and then the technology of a distributed system of a blockchain that, hey, you're not printing money or you're not spending something twice. So I think no new vectors of attack in that case, as long as you can verify the zero-knowledge proof.
Well, you have attack vectors of the proving system.
So, if I can take, so I think I mean, not necessarily a vector, but there is new type of attack, which is invisible attack. I mean, it's very possible that a given ZK system will have a vulnerability which will allow attacker to mint new tokens without it getting noticed for years. So like someone knowing such an exploit can continuously exploit the protocol for years, minting new tokens, doing withdrawals, and if he's smart about it and is not exceeding some thresholds where it's becoming too obvious, well, he can, I guess, go away with it for quite a long time. And this is not only a theoretical scenario, this actually happened in 2018 with Zcash. So there was, this exploit was there on mainnet for, I think, at least 9 months. Just a handful of developers were working on fixing that. And well, I mean, it's it's not clear, and it will never be known whether someone else knew about this exploit and whether it was actually utilized. I mean, it may be the case that we're living in a world where someone has basically infinite amount of Zcash tokens minted, but he's smart about it and just using them sparingly. And yeah, I mean, is it a new vector? I don't know, but like the old vectors of attack are getting way more dangerous. Regularly in DeFi, the very moment someone is using an exploit, it's kind of burned and everyone knows about it. Here it's very different. So I think like this situation is much more dangerous, and the audits are way more important than in non-ZK area.
You just need very good cryptographers like we have at Alio.
Yeah, I'll just add to that. Yeah, it's true in terms of the verification of the proof and writing that verifier correctly. That's definitely an area of attack. There are new proving systems. They're like happening all the time now. Just coming back from ZK Summit 12, feel like there's yet another proving system, and there's like, I don't know, 12 new research papers per quarter. So I think in writing these verifiers, they're often contracts on chain, and they need to exist and follow the protocol, the proving system that they're built for. For us at Horizon Labs, we want to build this blockchain solely focused on proof verification, where developers don't have to worry about writing a verifier. We would write that verifier for any new proof type, and then get it audited, and also make sure that it is written in a way that is very secure.
I think all privacy systems increase the attack vector by at least 10 to 100x. I agree with you there. You have the proving system that you're writing. The answer, like people who hate T's like to say, okay, yeah, you're trusting Intel, ZK is better. We say that too, for the record. But for ZK systems, you're trusting, is the proving system written correctly? There are like 300, 400 cryptographers in the whole world who can write this. Out of the 400, let's say 200 work in competitor companies. So there are like, you're left with 100 people in the whole world who can audit this. All of this is writing brand new cryptography that is never written or thought about before. There's bound to be a lot of bugs in every proving system, no matter how good you are. Bugs could be, in the proving system, it could be under constraints, so you didn't write all of the assertions correctly. It could be in the verifier contract. It could be double spend issues, nullifier issues, the way you Merkleize state. Like, you take a normal blockchain, you have all of those issues, like if you do consensus, did you implement the consensus correctly? And then you have this additional problem of like, if an attack actually happens in private land, how do you even know that an attack happened? You then have a different problem. Did the attack happen at the app layer or at the protocol layer? Because you messed up with your protocol design. Then you have a third problem. If you figured out all of that, then how do you debug this? It's all private. Luckily, all privacy chains have this thing called an all privacy chains have this thing called a viewing key, which let you debug all of the encrypted data that has come to you. So at that point, you might have to share your viewing key with a security engineer who can help you work through your logs and see what happens. But even then, that's like really horrible. Ethereum is has been used for over 10 years. The tools still suck. They're great, but they still suck. The only thing is we all have used them for so long, we know how to use with them. New blockchains like Aztec, whatever, their tooling will suck even more, and it'll take a lot more work to figure out how to use it. So debuggability is something that actually scares me.
That's true. So what I'm hearing is there are bugs and attacks everywhere, but it's just more expensive in private chains because
Get the best cryptographer.
yeah,
They're still humans. They're still humans.
Okay, my next question is specifically for you, Zain, and maybe Adam, you can also chip in. So when you come to the business side, like privacy and compliance, like how does that work? So because you're dealing with so many geographical entities and they all have their own laws and regulations. So how do you bring privacy and compliance into the system, which is kind of global in nature?
So I think it's usually it's about future-proofing the protocol. I mean, right now, for vast majority of jurisdictions, there is nothing illegal with privacy protocols as they are, but like everyone knows, regulations are coming, so there are several ideas of how to make it more. I mean, not more. It's not like how to make it compliant, because the protocols without these systems are not uncompliant right now, but how to make them future-proof. So I think there are two main ideas out there. The first one is based on the idea of proofs of innocence. So the idea here is that, like, when I'm using a given privacy system and I'm doing a withdrawal of funds from this system, for example, I go to either centralized exchange, or maybe I'm just buying something, then I generate yet another ZK proof, and this proof should be the proof that, well, I'm not a criminal, basically. So what does it mean? That probably means that I never interacted with some list of addresses which are known to be malicious in some way. So there are several projects doing that. Here, unfortunately, there is a big problem, because the list of these addresses, I mean, there needs to be some reasonable time frame for this list to get updated. And well, usually, unfortunately, the government's agencies which are doing stuff like that, they are not doing it within minutes or even hours. That takes days, if not weeks. So that would mean that if we want a system that works using this kind of proof of innocence, well, actually, it should have a delay of, I don't know, several weeks for users, because otherwise, I mean, it's very much probable that someone would launder the money there just by putting it and getting it out relatively quickly. Not too quickly for the privacy, but like also not months, but rather a week or so. So this is one of the ideas, which is, well, like ideologically very nice, because it doesn't compromise privacy, but well, it can be argued that it may be not enough. The other idea is based on some way of non-voluntary revealing the trace of transactions. So on deploying some kind of a system which will be able to operate with a master key to reveal a certain user. So usually the pattern, the money laundering pattern that is seen is that there is some kind of a hack which is on public protocol, then the funds can be traced to some very particular transaction or set of transactions which are entering the privacy pool, and the money are gone. So like then we can deploy the systems which, based on decision on the particular deposit, will reveal the trace that is left after these transactions. So this is what we're trying to do, where this system, we want to progressively decentralize this system to a committee, and then there will be a voting on which of these transactions should be revealed or not. This is one of the ideas. Generally, we are designing in a flexible enough way that we can add more system on top of it, as the situation is still pretty dynamic where it comes to what will be seen as a general standard. And yeah, I think this is a very much experimental area still. Like viewing keys is definitely something that is used by everyone for years. Right now it seems that it's probably not enough because it's purely voluntary, and well, it's enough that someone will deploy checks or other protocol that does not require showing the viewing key, and well, then it doesn't work. And actually the same argument goes for proofs of innocence. So yeah, I mean, I think we're gonna see. I've seen so far mostly these two branches of solutions.
Yeah, I think that's really interesting, the proof of innocence and this like proof that essentially captures the auditing trail. That's really cool. Yeah, in terms of compliance for Horizon, Horizon, right, being around since 2017, a home of the cryptocurrency Zen. Zen is available for trading in the main tier 1 exchanges, Binance and Coinbase. Last year, we were hit with a monitoring tag from Binance, and we were part of a group of privacy coins that were hit with that tag, and that kind of set up alarms for us. But in a way, the exchanges are this like, I don't know, they have this good almost like pulse for regulation in a way. So we ended up removing the privacy, the shielding feature from our blockchain. And we took that opportunity to say, hey, we want to build Horizon from the ground up. So we were a UTXO-based chain, and we want to move it to proof of stake, this substrate Rust-based chain, where first we'll start with specializing in that piece of the proof value chain, which is proof verification, and then we'll layer on other pieces of privacy after that.
That's very nice. We're kind of running over time right now, so I just want to hear some kind of closing remarks on you, any privacy myths you want to debug, or any message that you want to pass on to the community who are building on privacy blockchains. Just some closing remarks.
Yeah, well, anyone watching that wants to build a new application that makes use of privacy and blockchain technology, you can go to alio.org right now and look at our developer documentation. We're live on mainnet. So you can build it in a week and deploy it and see what happens.
So I can say that if anyone wants to build such a private application, focus on user experience, not on solving yet another academic challenge. And we've got a lot of people solving academic challenges, and definitely not enough projects with like a reasonable use case on mind and a good user experience. So I think like right now, this is the biggest challenge in the industry, not pushing further the cryptography.
I think that more and more what I'm seeing is collaboration within the ZK space. I think there were a few projects that were very interesting. For example, collaborative snarks, which is combining snarks and MPC for proof generation. And then I think Zama is doing the snarks plus FHE, so that's private verifiable computation. And I think that these like new ways of doing snarks and proofs, they're just going to continue, and I'm really excited about all that.
Me too. Rahul?
Just say, privacy opens up a bunch of cool apps. Think dark pools, secret algorithms, private NFT marketplaces, uncollateralized lending. You can take TLS Notary, you can take ZK email and do crazy things with it. And I think if you're interested in privacy, rather than joining one of these amazing teams, build an app on any of these networks, but build apps. We need it massively.
I'd like to thank our amazing panel and for their great insights. It's clear that building privacy blockchains requires balancing complex factors like transparency, scalability, security, compliance. So yeah, it's a long journey ahead for us. Once again, please put your hands together for our amazing panel.
Thank you, thank you.
Thank you.
Thank you.
Thank you.
Thank you.
All right, welcome back everybody to ZK Hub, ZK Talk Day. I am so glad that you have all got the opportunity to enjoy a little bit of lunch. Come on in, come on in, come on in. You're not in the wrong place. Everybody's just using the restroom, I feel like, after a long, really delicious meal. So those of you who are not with us in Thailand, it's been a delicious overdose of Thai cuisine. I ate way too much Penang curry. I too could use a break to lay down, but I'm here instead. There's thousands of you online with us right now, and I want to kick off our post-afternoon programming with a co-founder of Sizik, Leo Van. Yay! Thank you!
Okay, yeah. So in this talk, like I'll describe how SASE network works. Like SASE network is a ZK proof layer. It will accelerate the ZK proof with next-gen compute. Okay, yeah. So first of all, ZK is here. So we have ZK layer 1, ZK layer 2. They are all I guess some of them have been already listed in the exchange. And in addition to that, we also have the Verge approach proposed by Vitalik, where he basically want to snarkify the Ethereum layer 1. And in addition to that, we probably in the future everything in the world should be proven, such as if you want to show your passport, then you can use ZK to prove that, and you can use ZK to do some KYC. Yeah, so that's yeah, the ZK technology is here. Okay. Okay. Yeah. Okay. Okay. Yeah. So for here, I'll talk about some basic info of SASE network. So in SASE network, we first have a bunch of agents. So those agents are right now we are using smart contract to deploy the proof task. It will send the proof task to a bunch of proofers who can do the proof generation. And then afterward, we'll have a bunch of verifier to verify the proof, and all the things will be settled in the sequencer. So that's basic overview of SASE network. Yeah, so SASE network is a Cosmos CDK. It's a layer 1 blockchain. And we basically using the layer 1 blockchain to the transaction there to keep track of the status of the SASE network. All the tasks, it can be the status of the task can be in several status, such as initiate, waiting for proof, waiting for verification, and also success. After the success, we reach a success status that the fund will be will be transferred from the smart contract to some other smart contract. So that's how the SASE network, the infra works. Yeah, so for the consensus, when we develop a new consensus called the proof of compute. So basically, it's a combination of proof of work and proof of stake. It contains these 4 steps. First of all, we have the user contributes their computing power to SASE network, and then their contribution can be quantified in this VE token, and the VE token can be then delegated from the users to the validators, and then participate in the proof of stake commit BFT consensus algorithm. And then after that, of course, you can get the blocker reward pro rata, proportional to your contribution. Okay, so that's the consensus part. Yeah, so to have the to facilitate the participation, we also developed the dual token model. The dual token model, basically, we have 2 tokens. The first is a governance token, the CGT, which is used to do the staking, voting, ecosystem governance. And the second is a network token used for the gas fees and transactions. Yeah, you need to stake some of the token to participate in the activities on SciC network to join as prover, as verifier, and also as the validators. And when you accomplish like some proof task, like you will get some like SciC tokens reward. Okay, let's wait for the next slide. Okay, yeah, so now let's talk about the performance part. Yeah, so like using like SciC GPU, like our basically the CUDA library, we can reduce the proof generation time by a lot. Like for instance, for the Hello 2 EVM you used by Score, like you can do it like on 2 4090 GPU cards in about like 15 minutes. And for the Bujang EVM, which is used by like ZK Sync, yeah, you can reduce it to like about 1 hour, and we can support other proof backends as well. So that's for the ZK proving part. Then the second is verification. To just okay, sure. Let's continue the next slide. Okay, so the verification and like one purpose of like having SciC network is to say you can actually settle your proof on SciC network, and the proof settlement will be like much cheaper to settle on SciC network compared with like Ethereum. But if you are like cautious enough, like we can also have this aggregated proof to put it on Ethereum. And right now it's like for 10 proofs you only need to spend say like 2.8 K gas to do that. So that's the aggregated proof. Okay. And we also have a phone-based status client where you can verify the proof on your cell phone. Like you can verify the Score proof, ZK Sync proof, probably also like in the future, the Ethereum Verge proof. And to go alongside, we also have an AI agent there. So AI agent will counterfeit some like fake information. Yeah, so for each proof, for each like client, you only need to have say like 1 kilobytes data as the initial one. And for the data transmission, it also will be minimal. So that's the phone-based one. And we are also developing a Telegram mini app to verify the proof on Telegram, in Telegram. So that's to onboard like more users to SciC network. Okay, yeah, so here's the summary. Like we launched the testnet about 3 months ago, and it's a Cosmos CDK-based one, and we have like more than 22K application to be verified, and in the past several months, we have generated more than 5 million ZK proof. Okay, that's all. Thank you.
Thank you so much. Okay. All right, everybody. We have a few minutes between now and our next panel. We're going to just wait for our panelists to join us. But if you have any questions for the SciC team, do you mind just bringing up the slides again, the last slide? I think that might be helpful for, yeah, because while there is an audience live, we also have a big audience online. Yes, so we want to make sure that if you have any questions for Leo, you can find him here. This is your Telegram, right, Leo? Your Twitter account. And are your DMs open? Okay, lovely. All right. So a lot of things going on at ZK Hub right now. We have Puzzle from the Alio network that has decided to set up a, what do you call it? Like the bow and arrow? I forget what that's called, but I tried it many times and did not hit the bullseye. I didn't even come close, and I'm actually kind of eager to go back out there and try again. We also have ZFi Day happening in the other room where we're talking about ZK-powered decentralized finance, which I'm super interested in, mostly because one of my first experiences in blockchain was finding my partner's Bitcoin that he bought back in 2014. So for those of you who don't know this story, and I would imagine many of you do not, because I've only shared this one other time in Istanbul at DevConnect last year, and my my foray into the blockchain space came at a time when everybody was sick with COVID, and because nobody was going to work, or at least I wasn't going to work, I was hanging out at home, taking care of my partner who was sick with COVID and eventually got COVID myself. He, in his delirium, told me that he had purchased Bitcoin back in 2014. And this is a partner who is not the most technically savvy, so I was a little dismissive and honestly didn't believe that he had Bitcoin, mostly because I didn't think that was even possible for like a very tech-savvy person, simply because what I'd known about the blockchain and crypto was just so abstract. And so, of course, because neither of us was working and we were both delirious from being sick, I was like, you know what, I might as well help him find it. If it doesn't exist, I kind of assumed it wouldn't exist anyways. But lo and behold, after 3 weeks of searching through all of his emails and seeing things that I did not expect nor did I want to see, I ended up finding his 2.5 Bitcoin on a Binance account. And I think at the time it was just before things had dropped considerably, and it was worth about 200,000 Canadian dollars. And fun fact is that he let me keep it. And of course, that was the catalyst into me wondering what the heck this magic money is. And along the way, doing more research about the technology and figuring out that, wow, this thing is so much more promising than just financial opportunities or financial gain. But like many of you, I think the introduction to blockchain is, for the most part, through decentralized finance and the opportunities of a decentralized asset like Bitcoin. I don't know how many of you have also found that significant amount of Bitcoin hidden away in a centralized exchange, but I think that's part of the reason why that room is very full right now, with many who are curious about what's next for decentralized finance and if privacy is in the works, is in the cards. So I'm going to take a quick pause, and we're going to round up our next group of panelists, and I'll do a quick introduction to them. Okay. I am thrilled for all of you to have some familiar faces and some new faces to the stage, the co's and prawns of co-processors. Welcome to the stage, our panelists. I feel like the music should start when I go like this.
Awesome. Hello, everyone. Thank you, Annie, for the introduction. panel, the pros and cons of ZK coprocessors. We're here joined by a number of high-profile individuals that are all to the aspects of coprocessing. We have here Scott, the CTO of Space and Time. We have Michael, the co-founder of Brevis. We have Stephen, the head of strategy at Risk Zero. And we have Ayush, the co-founder of Layer Edge. I guess to give a context of ZK coprocessing, it is a critical element in enhancing blockchain performance and comes with unique challenges for complexity, compatibility, and managing these increased costs. We'll be exploring the implications of adopting coprocessors, their benefits, and their trade-offs. So I guess to start off the panel, what are the primary advantages of using ZK coprocessors in blockchain infrastructure, and how do they impact overall scalability and efficiency? We'll start off with Scott.
Sure, great to be here. Excited to see some familiar faces. ZK coprocessors offer a way for smart contracts to kind of offload a lot of computations that they either can't do on chain, like technically can't, or where the gas is too complex to do on chain. And furthermore, it allows those computations to be executed against historical state from the chain, right? Like most smart contract developers are often a little shocked when they get into smart contracts and realize smart contracts have no access to like historical blocks and ask complex questions about historical activity on chain. So the up and coming ZK coprocessor space offers a solution to allow those computations to be done next to the chain and then proven back to smart contracts that need those computations.
Well, that is a great answer. I think that summarizes up a lot of what coprocessor does. I just want to provide a perspective in terms of like the trade-off dimension, the trade-off space, and how we evolved from the early stage of layer 1 blockchain all the way to coprocessor. Right, so in the early days, if you look at the layer 1 blockchain, we only have 3 dimensions in the trade-off space: decentralization, security, and scalability. Right, so what Ethereum chose was obviously high decentralization and high security with pretty poor scalability. Now we have better scalability in the Ethereum ecosystem because we have layer 2. What are layer 2s? Well, layer 2s are essentially introducing an additional dimension in the trade-off space to make the trade-off space from 3-dimensional to 4-dimensional. That 4th dimension here is unity, or unification of states and liquidity. So what Rollup did is to trade off or significantly reduce the liquidity unification and user unification and improve performance that way. So we have better performance on rollups, same level of security and decentralization, but much, much worse unity with liquidity fragmentation and user fragmentation. Right, so however, if we look at performance, it is still not enough. Like as Scott rightfully pointed out, there are still a lot of type of computation, things like access historical states and do the computation on top of that. That is very, very hard to do even on layer 2 rollups. So this is why we need to play the trade-off game again by introducing yet another dimension of the trade-off playing space. And this time we introduced the synchrony. That we introduced an asynchronous architecture to allow blockchain to offload computation to an off-chain environment in an asynchronous way, and then bring the result back, so that we can have infinite level of scalability, but at the same time, 0 fragmentation of user liquidity and everything. So I would say this is how I view the evolution of coprocessors.
Yeah, I mean that's a very comprehensive answer. I don't think there's much else to add other than something that really excites me about coprocessors is what they mean for developer expressivity. Because at the end of the day, whether you're on a rollup or even a super high performant thing like Solana or Monad, you're building in environments like EVM and SVM. And naturally, those are extremely restrictive and really limit what developers can do. A lot of the ZK coprocessors that our team is really focused on, because they're grounded in a ZKVM, allow developers to build in Rust. And we've actually seen this be a really big thing in terms of what it enables developers to do, whether they want to build order books now with fully Rust-based matching engines, basically we've seen a substantial improvement in like what applications can functionally do because of this new developer interface.
Yeah, so I think all of the everyone has actually completed like what advantages that we can get from like the group processing. Like I can only add like the point that like it actually enables like a lot more like aspects of things that were initially not possible in the very decentralized way. For example, if we ever want to now, like in our case, we are creating aggregation. So like if we do all the computation, say on chain, it's like nearly like impossible for us to do. But like with the help of coprocessors, like it can be done in a fast and efficient way. And like along with that, like a lot of things, like for example, if you want to give any VIP points or any, like there are a lot of new use cases that have been enabled by processors. So I'm like pretty like bullish on like those type of things because that can actually move like DeFi from a like a plainly the vanilla DeFi that we currently have to like more of a like real world financial institution, like assets and like mechanics we can implement.
Perfect. I think the overall theme is taking the historical data and taking data that's inaccessible within the blockchain context or just too expensive, taking that off chain and then bringing that back on chain essentially as a way and a means to compute off of that data. And so essentially taking the stuff that's complex, bringing it off chain, then putting it back on chain in a verifiable manner. And I guess, can you, I think I actually missed this in terms of introductions. Can you also introduce yourselves and say specifically how your project is operating within the ZK coprocessor space and anything that you're currently focused on in that way? And then I guess we can start with Ayush, if
sure. So like what we are basically trying to do is to create like bring aggregation to like the Bitcoin space, because in Bitcoin space, like right now, everyone is trying to do the native verifications on Bitcoin with like one-of-n trust assumptions. So like this is very good, but the main problem with everything is like it's pretty expensive. Like right now, if you see, it's like close to like $900 per block. So what we are trying to do is to create aggregation layer for all the ZK chains and protocols, and for creating the aggregated proofs, like we are using like ZK processors for like creating the aggregated like Merkle tree and like doing like the recursive proof generation so that we can come up to like a root node.
Yeah, what we're building at RISC-0 is a ZKVM, and that principally makes ZK development substantially more accessible and performant. All of this is being based around Rust-based development. And then what we're doing with the ZKVM is then connecting it back on chain using our protocol called Boundless. And what this enables is this ZK application stack that very much mirrors coprocessor-based architectures where the majority of compute is moved off-chain. That's really what our mission is at this point. Basically, how can we take all the on-chain compute and move it off-chain? We think with the performance of ZK, with things like aggregation and other mechanisms, we can get to a point where a lot of the logic of applications can be fully ported into ZK.
Yeah, so at Brevis, we build off-chain verifiable computing, in the coprocessor architecture. Now, there are many different kind of a product on the roadmap, but the first product we launched is a ZK data coprocessor that focuses on offloading, data access and computing, historical data access and computing type of computation from on-chain environment to off-chain environment. And with that, you can essentially build application that is driven by historical state and behavior of your protocol, of your user, and differentiating user experiences, and do many things like that. So our solution is we try to kind of find the optimal trade-off point between performance and also programmability. So we offer an SDK that is highly programmable for developers to express their business logic using different type of data stream APIs. But at the same time, for the specific use case of on-chain historical data access, we provide extreme, fast ZK proving engine to do that. So yeah.
Scott Dexter, co-founder of Space and Time. Space and Time is a ZK coprocessor specifically for SQL against indexed chain data. So one thing that's unique about space and time compared to most ZK coprocessors is that we're not building a ZKVM, we don't support arbitrary computations, and we don't we actually transform the data a little bit before loading it into the processor. We actually kind of build almost like a Dune-style data model of Ethereum data and Bitcoin data and a number of other chains that we've indexed. But then we allow smart contracts asynchronously to query all that on-chain activity with SQL. And so we spent about 3 years just building the fastest frickin' ZK coprocessor we possibly could, just hyper-focused on SQL against blockchain data.
Awesome. I see like a various different types of directions in this space, well, from generalizability to specifically based on the blockchain. So for Ayusha's Bitcoin, for risk zero, for generalizable ZKVM, and then like for Brevis it'd be specific like SDK for the development, and then we see for space and time we have the highly performant and indexable SQL-based ways. So there's different methodologies for that to getting performant optimizations or generalizable depending on the flavor of the co-processing that you're looking for. And I guess like on that note, in terms of the biggest challenges associated with integrating the co-processor in terms of data, I guess we'll start off with Scott again, and what were the biggest challenges for that type of integration with that to occur to be performant? Like, what was the design considerations for that?
Yeah, good question. And this panel is the pros and cons, so I'll talk about the cons in that context. I think one of the biggest challenges of coprocessors in general is the asynchronous nature, and you called this out well too. The problem that we all have is smart contracts will get their answer back, like the result of some computations that are executed off-chain in a coprocessor, or a query result, or the output of some DeFi calculation executed in risk zero. Like, they'll get that answer, that output back in later blocks. And the problem then is there's additional gas that's paid usually by the coprocessor themselves to verify proofs on chain. So there's gas for the verification, and then there's gas for the transaction to asynchronously submit the answer back on chain to the smart contract that requested it. Oracles like Chainlink had the same problem during DeFi summer in 2020-ish, right? The asynchronous nature of calling an oracle, passing a payment, getting back an answer later. And that slows down transactions if the co-processing needs to occur during a transaction. A lot of the coolest use cases that are already popular are more asynchronous by nature, like use cases that don't require an answer back next block. Where there's no hurry. Hey, you have a big processing job where I don't want to pay on-chain gas for the actual computations, and it can run for as long as you need. Just give me back the answer sometime in the next hour, and that'll make some decisions like rebalancing a pool, or some governance decisions, or maybe rewarding node operators or something where it can just happen once a day. No problem. But for transactions that need to kind of get their answer back quickly, the asynchronous nature can be challenging.
Yeah, I mean, like, I definitely agree. This is definitely the biggest kind of a pattern change in terms of developer experience and developer, kind of a build how developer can use ZK coprocessors. But just like any kind of a trade-off space, games that we have played in the last, 50 years in computer science history, there's always a way to just add another layer of abstraction and try to mitigate that. Right, so like, we had this kind of a similar problem in Web 2, actually, in the early 2000s. So the entire web architecture, like internet website architecture, was very much rooted in a synchronized architecture back then. You have one server that handles everything: authentication, data storage, computation, everything. So that was super slow, and internet, user grow like rapidly, and that architecture couldn't handle that. This is where we actually introduced this type of asynchronous web architecture, where you have a web server now, like Nginx and all the popular web servers are just acting as a glue for many back-end kind of specialized coprocessors, things like AI, things like data processing and everything, right? So The way that people can mitigate this challenge is by providing developer with an illusion or abstraction of synchrony. So like, even though that underlying what happens is there's a message sent out and then, something goes back, but today's web development architecture doesn't actually expose the raw asynchrony to the end developers. Developers themselves are just writing functions, they understand the basic concept, but they don't need to handle the messages, send a message and everything. So that's where we think, the ZK coprocessor space will also go by providing better abstraction, better user, developer tooling to mitigate that kind of a, fundamental challenge there.
Some architecture that we've recently seen that I think excites me, and also kind of gets around the async issue, is taking the application as a whole and moving it off-chain. We're seeing this with kind of what it's called provable exchanges or provable applications. In this case, like the order book fully runs off-chain, effectively in a server in their office. And then every hour or so, all of the bids and asks and the order matching algorithm as well are processed through ZK and submitted onto Ethereum or onto Arbitrum. And basically what you get there for the user is a Binance-like, sub-millisecond bid-ask order matching experience. And then the only thing that lags behind is this sort of hard finality, which is dictated by the ZK proof itself. So basically, instead of having to try to sync up with Ethereum or whatever chain after every single proof, you kind of let the application run by itself, and then the ZK just creates like a hard finality checkpoint every once in a while. But obviously, you do lose a lot of trust guarantees with this, right? There's censorship, there's a lack of decentralization, which can be fixed in different ways using traditional distributed systems. But it's a cool architecture, and I think for the developer, they built the order book like Binance would have built it. They didn't have to think about async anything. The only thing they had to build on-chain was this sort of deposit withdrawal mechanism, which is relatively standardized across most rollups. But in this case, they don't have to deal with blocks or sequencing or consensus or anything like that.
Yeah, I can add like from a developer perspective, like the architecture is actually good because it allows like a lot of new applications, but there is a problem of like sometimes like learning the architect, like the whole like what you can say, using coprocessor for the first time, because the onboarding experience, like as per like my experience which I had with some of the developers, is like it takes like some times because it is relatively way more different than regular regular development, like for any like what you can say, smart contract developer. So initial learning phase is a little bit rough, but like after that, like the advantage that we actually have is like pretty good. So like as a whole, like as you're saying that you have developed like certain set of like toolings, how like these things can be abstracted out. So with this, like the adoption for the developers would be like pretty huge. But this is a problem that initially like a lot of guys faced.
Perfect. I think definitely different methodologies, being closer to finality and then further away, and then the level of programmability within there as well, like taking into consideration like when do you want the data, how, and then dealing with those asynchronous properties. I guess you talked a little bit about the developer experience within these ZK coprocessors. Are there any particular challenges or opportunities that developers need to be aware when building with these technologies, or specifically your tech stack?
Yeah, so like for like the specific coprocessors thing that I found, like the guys who have working with like backend and decentralized systems for a long time, for them it's like relatively easier to grasp compared to the smart contract devs. And like as a whole, this has enabled like a lot of new like opportunities for us. Like for us, like we are basically like focusing much more on the security aspects and the aggregation aspects. So for us, it's like a very good thing because we can easily be able to like create our own like aggregation modules and then basically settle like a single time on Bitcoin, and then by that we can save a lot of costs. But for that aspect, like it was like a very genius thing because if we have done it in any other way, we would either like not be able to do it, and the concept of actually abstracting out all the computation and just getting the like verifiable proof at the end of it, which is actually justifying all the transaction, the computations happened, is like phenomenal.
Yeah, two interesting things that we've seen with people building coprocessors is one, when you're ingesting a lot of state and data, like querying Alchemy for hundreds of thousands of blocks in a minute is actually extremely difficult. And Alchemy themselves don't have really good infrastructure for that. So that's been something we've been tackling with a lot of our partners. And then the second thing being data structures, right? Like on-chain data structures are still really unique, especially because you got to basically Merkleize all your data. And when people are building coprocessors, at least a lot of our partners, they just want to use traditional data structures because that's what makes most sense to them. And then we need to go to them and be like, hey, how do you want to Merkleize like a gigabyte, 10 gigabytes, 100 gigabytes of data every single time you generate this proof? And then somehow submit it on-chain and kind of maintain some sort of connection between your existing database and then your on-chain Merkle root. So a lot of interesting things to play with and a lot of new ideas that people haven't really touched before, which is kind of exciting. So yeah, basically right now, every single coprocessor partnership we're looking at, they are bumping into something new.
Yeah, definitely. I think one thing I want to kind of add, on top of all that is when you're building coprocessor-based use cases, it's very important to understand and think about what type of data you actually need, right? So there are so many different type of data on blockchain. The most kind of a straightforward one is like states. What is the ownership of an NFT? All the view functions are built based on only just like the Ethereum states. But there are also a lot of information that is not being captured by just the states, such as transactions, raw transaction data, and events, like what is the result of user behavior, right? So these kind of things are sometimes can be extremely useful. For example, if you want to calculate what is the trading volume for a user, you don't need to kind of re-execute the state of every transaction. Instead, you can just look at all the historical events and sum them up, right? So when you're trying to understand and build your business logic, think wider than what's available on-chain as states, but also what's available and emitted as events or the user transactions, interactions, block states, and account state. All of these things, everything on blockchain is accessible by coprocessor, and in this case, Brevis, provide the widest amount of data available for you to kind of use. So that's something I want to note for the developers.
Our focus is, like I said, SQL, and we're kind of thinking through a lot of real-time use cases where we can run a sub-second ZK proof against, 60 gigabytes of Ethereum transactions or event logs from, a certain DeFi protocol, smart contract events. And we have a lot of customer or partners that come to us that are trying to build more sophisticated DeFi. Think like lending, where the lending protocol looks to see whether the borrower, as they transact, as they take out their loan, see if they've already paid off some loans on chain and give them a better borrow rate if they have. That proof cannot wait very long because the borrower submits a transaction and is waiting for their transaction to get approved, waiting for the loan to be granted to them. And if space and time as an intermediate solution providing the data for that transaction slows down the transaction, that's a frustrating user experience. So we're hyper-focused on how fast can we give this data back to a smart contract verified on chain to give it the context that it needs to facilitate a real-time transaction. I think there'll be much better solutions than space and time for offline processing, like massive and long-running computations that can be verified on chain whenever. Like I said, a minute ago, like examples where there's a proof that's needed like once a day. Like, hey, I'm going to reward my node operators once a day and ask a Brevis or a RISC-0 to calculate the rewards per node. But if a smart contract just needs to know about the user that's borrowing right now, as fast as possible, sum up the total volume of their loans paid off, we're trying to bring that back on chain next block.
Really good use cases and definitely directions for different implementations for developer experience. And it seems like developers are driving, or at least it's use case driven, like for lending, order books, and other means to leverage the on-chain nature of events. And then in terms of these, in terms of the costs, I would say like costs versus performance. Does your solution, and then I guess this question would apply to everyone. Does your solution optimize more on the speed, on the costs, on the different types of finality guarantees? So like where are you? Where is your solution leaning towards, and or maybe just extensibility in that case? And I guess we'll start with Scott.
Yeah, we had to make a lot of tough design decisions because depending on what type of commitment you want to use for your data, it might determine how expensive on-chain verification is. And unfortunately, like the design decisions that we made had to balance cheaper on-chain verification at the cost of slower proof times, or vice versa. Speed up proof times, slow down or increase the gas of on-chain verification. Ethereum is tough. We don't really have a great set of curves available as precompiles yet on Ethereum. And so a lot of teams sort of have to make do and make design decisions that usually include folding or recursion prior to verifying on-chain, which then slows down the total round-trip time to get an answer back to a smart contract that needs it. We also made a huge design trade-off on interface, right? Our interface is not Rust, it's SQL. And that's all we're going to support forever. Like we just want to make it really easy to run SQL. And that comes at the cost of some teams can't use space and time because they have a Turing complete need that goes beyond SQL that would require Rust or something.
Yeah, I think one way we look at kind of the cost, profiling is that there are really two ways you can do co-processing in general, right? So like ZK co-processing specifically. One way is you can do everything in ZK end to end, all the time, right? So, this is what we offer as the first model in Brevis as well. We build an extremely efficient ZK proving core with highly parallel and elastic scaling and everything, right? So to push down the cost and, increase performance at the same time. Now, as every computer science problem is a trade-off problem, we can also introduce another dimension in the trade-off equation here by introducing some latency. So the idea here is that you can use something called an optimistic co-processing with ZK fraud proof, that what we offer as a second model in Brevis, where the co-processing result will be generated first by a class of a node that is right now running an AVS, and without actually computing the whole ZK proof, because this is where the cost will come from. So the result will then be posted on chain as a proposal and open a challenge window. During that challenge window, during a challenge latency, if a challenge initiated, you can actually initiate a ZK fraud proof as a challenge to kind of correct the result. This way, for most of the cases, you get a cost to the level of a centralized system that is very, very close to extremely low cost without any kind of ZK proof cost. But at the same time, you trade off a bit of latency. So if your use case is not latency sensitive, then you can use this model to get you the same level of security as a ZK-based, pure ZK-based system, but with much, much lower cost.
Yeah, at our team, we're definitely cost sensitive right now because ZKVMs are inherently a lot slower and more expensive than non-ZKVM based systems. So because of that, we do similarly do optimistic-based models. We do ones where ZK lags behind. But I mean, the only thing I'd add is we're pretty confident that with improvements in the ZKVM and basically how competitive the space has been, hopefully by the end of next year or maybe 2026, we'll have at least real-time proving down to a point where it's cost-effective for Ethereum. So that means under 12 seconds, end-to-end proofs put onto Ethereum. In the meantime, I'm quite excited about real-time solutions like space and time. So definitely that will be the unlock. Like that will be the big difference that makes it so most computation, most things done on chain can be brought into a co-processor. In the meantime, the applications are still more focused around async use cases.
And yeah, for us at Layers, like we are primarily focused on like the cost aspect of like the aggregation, because the block time on Bitcoin is like close to 10 minutes. So in that scenario, like we have not that much like time sensitivity compared to like the guys who are building on the Ethereum side. But the problem is like on the Bitcoin, like the cost of verification that's projected is pretty huge. So for that aspect, like we need like a longer time so that we can aggregate more number of protocols, and the aggregate like value of like a single protocol cost fees is lower enough that we can actually make it accessible to like most of the market.
Perfect. I think definitely like the variety of choosing real-time based proving for and then the choice between if you want to compute more operations and that'll take a longer amount of time. I think having that flexibility and optimizing for those specific use case and optimizing specifically for those solutions, I think has been very critical for that. I guess we talked a little bit about use cases for these ZK coprocessors. I guess starting with you, Ayush, what do you think the main use cases for the Bitcoin side of things, Bitcoin based or settling on Bitcoin would be, and then.
So like, yeah, on the Bitcoin side, I believe like the need of the ZK processors is far higher compared to the other networks. As here, like what we actually, like, let's take the L1 network. There, like the verification is somewhat not being like possible theoretically post OPCAT. To OPCAT it's possible, it's like very expensive that it's not usable at all. So in that scenario, like the need of coprocessors is pretty high, as you can offload a lot of computation of your own tasks. Like for example, if you're creating a DEX, it's very smart that you use coprocessors for handling all the matching engine, all the order, whereas you just do the end verification on the native Bitcoin chain. That gives you like the good aspects of like basically offloading the computation, and you can also get like a smart contract, pseudo smart contract functionality, because on the Bitcoin side natively you don't have that amount of smart contract functionality available, which can then be enabled by like offloading a lot of computation.
For us, we really just thought about like what applications can actually afford the fees added on by ZK coprocessors and ZK proving, and naturally we just looked at DeFi, because it's like if you think about what are the biggest successes over the past year, it's only been DeFi apps that have been doing like 50, 100, 150 million dollars in revenue, and then going there, a lot of those applications do want additional compute, additional state to increase their liquidity efficiency. So that's really been where we think the most amount of use cases for ZK coprocessors have been. Eventually, once ZK is cheap enough, then maybe games, NFTs, more fun things can use it. But as it stands, if you're charging even 1/10 of a cent per transaction, it's simply too much for the majority of applications.
Yeah, I mean, like, intelligent DeFi is definitely one very big category for ZK coprocessor use cases. The idea of, intelligent DeFi or data-driven DeFi is that you can dynamically change and tune DeFi protocol parameters on an individual user basis or on a protocol basis based on the historical interaction of your user or your market condition, like your proof of that using ZK. Right, so we definitely saw that as a very, very big use case, and we'll be launching our kind of a series of launch partners very soon on that category. But recently, we also have been focusing a lot on the mass adoption, the user adoption side of things. One thing I want to mention is that airdrops, right? So like airdrops, everyone knows like airdrop sucks now. It's a disappointment for both users and the project, because like for users it's black box, and for projects it's a cost center. And there's no way for you to actually build a trust-free system that continuously engage with your user and continuously kind of generate token to align with them, and in a very transparent and trust-free way. So we recently launched a new thing that is going to be a replace of the old one-off airdrop program called continuous protocol incentivization. And our first partner on this is Euro Money, which is a rising star in the stable token space. The idea is that instead of just doing one-time airdrops, we allow users to generate historical interaction with, generate proofs of their historical interaction contribution to the protocol, and then use that proof as a way to measure and calculate their contribution and generate tokens and align the incentive that way. Right? So we do think token issuance and token distribution is one of the most important use cases for blockchain, and how to align that better with the community is something ZK coprocessor can power.
That was really well said. Yeah, the data-driven DeFi where protocol parameters are tuned based on the user's historical interactions is really the future for sophisticated DeFi going forward. Like again, like when I first started writing contracts in like 2020, I was just shocked that I didn't have any functions to do something like run a query, like given my user just ask a basic question like what's the volume of transactions their wallet has executed on chain in the last week. I was like, wait, I can't do that? I can't do that in Solidity? What? But then you run into this whole asynchronous nature, right, where the user wants to transact as fast as possible. They don't want to wait 20 blocks on Polygon or 3 blocks on Ethereum or something. They want to wait maybe 1 block to get their transaction executed, maybe 2 blocks. And so the hard part is then as you lower the cost of actual ZK proving through writing a lot of optimizations to your circuit and like using better hardware and driving down the cost of ZK proving, then you also have to pay for on-chain gas to submit the data back to the chain and usually relay it to the client via a callback function. And there's also on-chain gas for ZK for the verification of the proof on-chain. And that gas, we have no control over. The gentleman up here, we can't control that. That's the target chain charging us. And so we could write the fastest, most optimized circuits possible that cost 1/100th of a cent to run a pretty complex DeFi calculation, but if the chain charges us 8 cents to verify the proof on chain, then that usually gets handed to the end user as transaction fees. And that decreases the quality of the user's experience. And so there lies the challenge that we all have to kind of come to grips with is like, how do you meet in the middle where maybe charge the user a little bit more for a data-driven, sophisticated DeFi experience, but not too more? And then we're unfortunately reliant on the L2s and L1s where our proofs are being verified.
Yeah, definitely different considerations related to that, and I hear that the primary use cases right now are the DeFi-driven ones, like the ones that essentially are driving the millions of dollars of transaction volumes, and then maybe like layer 2s as well are looking to essentially also come in with their own need for co-processing. So maybe like we'll see more or maybe more implementations on the different layer 2s that offer cheaper transaction verification costs, and then maybe that'll be the driver for more and more of these use cases outside of DeFi, and then or maybe like within DeFi and outside of DeFi. I guess for the final question, right before we end the panel, in terms of the long term, in terms of like adoption, where you see like a few years ahead, how what's your vision on co-processors, and how integral would it be within the blockchain ecosystem? Starting with you, Scott.
Yeah, okay, great question. We think about it like traditional app development in Web 2, where you have a API layer that contains all your business logic, your scripts for running calculations and understanding who users are. And your API layer for your app usually calls a database to get some context, that data, query results that feed into the business logic to make decisions. So if on-chain, the business logic for your DeFi protocol is a smart contract, our hope is that within the next year, 2 years, 3 years, I guess 4 years, DeFi developers start thinking that way. Hey, I'm writing a contract. My contract's going to need data. They embed either query IDs or actual SQL statements in their smart contract, and they just build that way. Like, I build my smart contract knowing that I have expressive access to like the entire chain history and a bunch of tables about transactions, events, storage slots, updates, and user history, and I can just like embed SQL in my smart contract the same way I would if I'm writing like a Java API or a Rust API or a TypeScript API for my web app. And again, like we'll have that asynchronous problem of like we have to abstract the asynchronous nature away from the user and make it feel to them like their smart contracts just doing that, and it's not like calling an external system, which is calling an off-chain system, which is doing computation, which is oracling the result back to the on-chain relayer contract, which is forwarding to a client. I hope, though, in 4 years, that's completely abstracted, and the chains just begin integrating their own co-processors. I've been asked so many times, like, Scott, what's the solution to the async? Well, the solution to the async is a new chain architecture where co-processors are part of the chain itself, not this external thing that sits next to the chain and oracles the solution, oracles the answer back on.
Yeah, definitely. So, I think we firmly believe that like a coprocessor is going to lead this kind of a glue and coprocessor architecture transition in the blockchain space, where blockchain is going to look more and more like a glue of different type of coprocessors. And there's going to be a diverse set of different coprocessors. Some of them are more going to focus on very generalized compute. Some of them are going to focus on historical on-chain data access. And some of them are even going to focus on machine learning and AI workload, verifiable AI workload as well. So I think all these things is going to unfold in the next 2-3 years. But I do agree with Scott that there is a very, very big opportunity there to have essentially enshrined the coprocessor blockchain. To essentially have blockchain have a coprocessor not as an add-on or accelerate component, but an integral part of a new type of blockchain. And this is something that we are also very excited about.
Yeah, I'd say the only thing I have to add here is, we also want to talk to applications and challenge them and ask them, like, what parts of decentralization and consensus do they actually need? Like, if I'm working with a game, maybe they don't need all the benefits of consensus and decentralization. So if we want to enshrine their logic using ZK on-chain, maybe we can keep the majority of their game logic off-chain just on a server. So it's like kind of those things that we want to play around with. Like, how do we bring the internet on-chain? Most of the internet probably doesn't need a lot of the security guarantees and trust assumptions that like distributed systems and blockchains give. So can we be selective about that? I think Polymarket's a great example. Like, most things actually don't need to be on-chain. And then I think coprocessors, because of how applicable they are and how they really increase developer expressivity, they're going to be the bridge between like all the real world applications and basically what's currently on-chain.
Yeah, and I just only want to add that, like, I totally agree with the point that, like, if you see the future of, like, most of the applications built on blockchain, the coprocessors will be the part of the architecture. Because if you see, like, any kind of new use cases or the current financial use cases, you want to implement them on the blockchain, then you need a lot of heavy computations, like, or you need a lot of amount of data. So in both of the scenarios, like, the coprocessors are basically the natural fit for it. And like moving this to the core architecture is like one of the things that is like, I think, like standard for all the new projects that are building. Like, for example, like we are building a verification layer. For us it is, and like for others like AI chains, like I'm talking to, for them like calling a coprocessor is like the standard protocol. It's like not like something new that they're doing.
Awesome. I see there's a consensus of having ZK coprocessors being an integral part of different blockchains, and maybe that's something that that in the future we'll see a bit more of, and then specific to those use cases of what on-chain data, what data do you need in a trustless setting as well. Thank you everyone for joining the panel, and yeah, give a round of applause for our guests here.
Yay! I'm extra loud and enthusiastic to represent the thousands of people who are live streaming right now. Bet you didn't know there were that many people. Thanks, you guys. Really appreciate it. It was a hoot. All right. Okay, well, just some comedic relief, or not really. Everybody's been asking me about this awesome shirt I have on. I mean, one of you in the audience also has one, right? Yeah, encrypted human. That's where I was. I was encrypted a little earlier. That's why I couldn't take someone off the panel. But welcoming back to the stage, one of my favorite people in the ecosystem is education lead at ZKM, Alice, who will be hosting the CEO of O1 Labs, Brandon Case, who is much taller in person than I'd ever imagined. Yes. Give a round of applause, ladies and gentlemen.
Yeah, thank you so much, Annie, for the introduction, and thank you, Brandon, for being here. I'm Alice. As Annie mentioned, I'm part of ZKM and House of ZK. We're joined here today with Brandon, who is CEO of O1 Labs. So thank you so much for being here today, Brandon. Really excited to have this interview with you.
Thank you for having me.
Yeah, of course. I'm wondering if we can first start off with your origin story. So I'm very curious to hear about your journey into both the Web3, also ZK spaces, and then also going into O1 Labs.
Yeah, my origin story. At what duration? Quickly, right? I tend to, I had this question asked of me a few weeks ago, and I talked about it for 50 minutes, so I'll go faster. Okay, origin story. Well, I saw a Slashdot post about Bitcoin when I was in high school. I tried to install the client on my parents' computer and failed. And that was like 1 cent Bitcoin. So then a few years later, when I saw $12, I was like, whoa, I can't miss this rocket ship anymore. So, so I built a computer with money I got from an internship, and then I mined Bitcoin using the free electricity in my university. I mined like several hundred, and then I deleted my hard drive. Oops. And you know, and then I stored them on some reputable public cloud sources that then got hacked, and all of them got stolen. So, you know, fun intro. After that, I was a little upset about crypto. So I didn't really pay attention when Ethereum was launching. I did dabble with like in the Tezos ICO because they use OCaml. I'm sure we'll talk about that at some point. The OCaml stuff in our stack. Anyway, so in and out of crypto, I was working at. I guess I always tended to be riding the waves of whatever's cool. And at that time, it was like MoLoSo, mobile location social. So I was at a mobile location social startup. And then we got acquired by Pinterest. And I found my little cool niche in Pinterest, and I did like really fun stuff with that team. But I pushed the boundaries of that space as much as I could, and I really wanted to work on something hard, like difficult, challenging, and interesting. And one of my friends from college was working on a new cryptocurrency project, which eventually became Mina. And I was like, that's cool. I started doing nights and weekends while I was still at Pinterest for a few months, and then I moved over full-time, and I started as an engineer. I moved around the company a lot. Fast forward, now I'm CEO.
Nice, and a pretty extensive kind of origin story that you have there. First from mining Bitcoin at your college, and then losing it all. But I'm sure that's still a very memorable experience that you can talk about for the rest of your life. And
it's a fun story.
Yeah, exactly. You'll always have a fun story to talk about. And then moving from Pinterest and then to O1 Labs, so quite a nice experience there. Wondering if you can also speak about like one of the main visions that I see Mina and also what O1 Labs emphasizing is the idea of building an internet from programmable cryptography. So I'm wondering if you can maybe elaborate on what that vision looks like.
Yeah. So the way that we think about it, well, I guess first of all, let me say Mina is a decentralized project. Lots of people are contributing. What I'm about to express is the opinion of O1 Labs and myself. And you know, I think this is super exciting, and and obviously there's a bunch of people in the Mina ecosystem who also are very excited by it. But I just want to, you know, for legal reasons, I'm speaking on behalf of O1 Labs. Okay. So yeah, we envision this internet powered by programmable cryptography, and it's important because it can enable developers to build like way more powerful applications than we've seen before. And I think it's not that Mina is the thing that by itself enables this internet. I think this next stage of the internet will have a lot of components in it that a lot of ZK projects are taking their, having their place in. And I guess, let me take a step back. What do I mean by this new internet? If we think to the origins of the internet, it was first just about information sharing. So, different universities would host information and you can go and learn, and it was very decentralized in all the good ways that we care about. A lot of community participation, censorship resistance, liveness. And then we added a little bit of cryptography, and this is fixed function cryptography, or this is the Web 2, the green padlock, the SSL, TLS encryption. And this enabled a much richer internet. So you could have Facebook and banking and YouTube, and a bunch of interesting applications. But we lost a lot of that decentralization. And just to harp on the cryptography part, this fixed function cryptography, its purpose is just to protect a connection between two servers. You can't do anything interesting with that cryptography. It's not programmable. Okay. So the next stage, programmable cryptography. That's ZK, FHE, MPC. These tools allow us to do a lot more than that SSL. Most importantly, they allow us to bring back decentralization. So we can actually have a real internet. They give us privacy. They give us a lot of cool stuff that we'll get to later when we talk about the benefits of these kinds of systems. And they enable these like super powerful building blocks which you can use to build cool applications. So there's an interesting post by ZeroXPark that mentions some ideas around this internet, and they talk about a universal protocol. So that's effectively, it's like taking data from somewhere and putting it somewhere else. So my passport, my ID, my Twitter, like my government information, and bringing it on chain or off chain, or in different places. There's also hallucinated servers. So being able to, on demand, create shared computation between me and my friends, or me and whoever else I'm interacting with, and these can be run by anyone, by me, by my friends, by a server sitting over there, and a few other things. But I'm rambling. So this internet is really cool, and we need a lot of different projects to fit together to enable this internet. But I think the most important backbone of this system, I shouldn't say most important, I should say a very important backbone of the system needs to be some kind of decentralized transport layer, some kind of system where all these proofs can come together and build on top of each other and get to the end users. And this is exactly where I think Mina fits in. So Mina, I guess we haven't talked about Mina, but it's a succinct blockchain, does a bunch of cool stuff. But one of the properties that I'll focus on right now is the succinctness. I already said that. So essentially, in one single proof, we can one single proof of everything, we like to call it, we can access information about lots of different programs. And we can build on top of that and recombine them to kind of do something interesting. And what's interesting about that from the perspective of a transport layer for the internet is as a consumer, like, so let's say I'm someone who's using a web browser or a phone and I'm interacting with an application. I can literally run a full node of Mina, not a light node. There's no sacrifices to any trust assumptions. There's no sacrifices to decentralization. I have full censorship resistance. I have full liveness guarantees. And connect directly to the network when I'm running my application or when I'm running an application that someone has built. This is something that today, either you have to use some kind of RPC service, some centralized RPC service. This is what most people do when they connect with MetaMask to Ethereum, let's say. Or if you're super savvy and intense, you have a server in your basement that's running a node. But I don't even do that. And I consider myself a sophisticated user of the crypto ecosystem. So this is super important. And then, again, this tiny proof, it's a nice place where sort of everything can come together and different pieces can build on top of each other.
Yeah, and I really like how you talked about how we progressed through the ages. Like first, the web was just about internet share or information sharing, and then we sprinkled in some cryptography. But then there's that decentralization component that went away. And now with programmable cryptography and what you're building right now with Mina providing that transport layer, we can go back to that stage again. So yeah, I really like that progression. And just wondering, on the topic of programmable cryptography, what you guys are focusing right now is using ZK as a means for achieving it. But you also mentioned there's some other tools available, like with MPC, FHE. Wondering just your personal outlook if you see ZK dominating as that tool for providing programmable cryptography, or perhaps we'll see a combination of a few.
I think we'll definitely see a combination. So of course we focus on ZK. We're one of the first. We're the first project to use recursive ZK proofs in production, and one of the first ones to use ZK at all. But and it's just where the tools are mature, I would say. But we've already done some experiments actually from years ago. We have some prototypes of integrating forms of MPC. We have a few experiments with FHE, but I would say, yeah, all these pieces are important. They all have different trade-offs and they do different things. I think ZK is really interesting because, both because of its maturity, but also because of the nice properties it has. Let's see if I can remember these. It has very small certificates. You can recombine them easily if you have a good recursive proof system. They provide a mechanism to sort of verify computation, of course, and they give you a nice, well, they give you privacy and a form of compression. So there's so many things you can squeeze out of ZK, and and it just gets better when you combine these other tools.
I see. And just on that topic, you previously mentioned about the idea of having that single recursive proof. And I believe you guys coined it as a proof of everything. So I'm wondering, what implications does this single recursive proof bring, and what does the proof of everything narrative mean to you specifically?
Yeah. Really, it's the engine that can power this internet. And there's another kind of meme like HTTPZ that I think is fun. So if it's some of the stuff I talked about previously, I guess just to we can focus in one level deeper. Like what particular properties does this give us? If I'm a developer looking to tap into this thing, it gives you a bunch of superpowers related to recursive proofs. So this sharing of information that this like super composability layer that this gives you the same sort of power that we see in I guess that we've seen in Ethereum, where you can have these protocols that layer on top of each other, like Curve, Convex, Llama, etc. You can do that same sort of thing if you have a proof of everything that like has these tendrils that you can recombine and reconnect to other things. It also, I guess one consequence of this is you get really interesting properties around incrementality. So what I mean by that is I can have an interesting conglomerate proof about some grand thing that's really expensive to prove, that I've collaboratively created, either by myself running a bunch of servers, a lot of users working together on a problem. Here, I'll take something concrete that's also kind of aspirational and academic. You could imagine a like formal proofs of mathematics that are proven in ZK, starting from core axioms for whatever sort of branch of mathematics you're thinking about, and different people can prove different theorems and lemmas about this information, and those theorems and lemmas are forever like baked into this proof of everything, and people can build on top of them. But if I guess this was a poor example for updating. But well, I guess in case the incrementality is in the sense that we can add a new theorem, we can discover a new theorem and then add it to our knowledge database. Knowledge is an example, like knowledge about mathematics is an example of something that's ever growing. But you can also have information about all your users that you've proven, and a user can take an action and you can update just that one user's state, something about them, and just kind of reach in and update that one part of the proof, and it's sort of very very efficient. And I guess kind of one more thing with this proof of everything. It's one way to think about it is it's a single global computation that everyone can contribute to, that is sort of ever expanding and ever, I guess, ever growing in knowledge, not just about kind of maybe mathematics, but about anything. And all these things combined together. And we can access sort of this grand collection of knowledge in this really, really tiny, from this really tiny like certificate and fingerprint. So I think there's, it's like inspiring. I don't know.
Yeah, and I really liked how you likened it to a knowledge database that anyone can contribute to that's ever growing, and how you can like adjust for different components within it. So I think that's a pretty powerful narrative. So yeah, thank you for that, Brandon. Also wondering, just on the use cases side within Mina and also O1 Labs, what kinds of use cases are currently being built on Mina, or what future ones do you hope to see being built?
Yeah. So we just had our first MinaCon in the Mina community. I think it was 2 weeks ago, or maybe 3 weeks ago. It was 2 weeks ago. And this was a space where we invited just like experienced builders in our community. We've had versions of our SDK for the programmability layer of Mina in iterative development with users for 3 years. So over this time, we've built this collection of experts who, many of which are doing this full time. Like they're just playing around with the tools and building on Mina. So yeah, so there's some really interesting stuff going on. I'll name a few. One kind of category that's really exciting is it's also like close, to being realized, because it's a little bit more straightforward than some of these other examples, which is anonymous voting. So with, again, like tapping into this proof of everything, so you get all these benefits around liveness and censorship resistance. You get privacy benefits from ZK. Also, something that's really core to Mina is we want to provide an interface that where people can run proofs locally, because you need that for privacy. If proofs are not being generated on the user's device, then you don't have privacy. So there's that, and then this incrementality again, I can incrementally sort of contribute to a vast crowd of people all voting in a scalable and secure and private way. So there's a few projects doing this. One that's like really exciting, ZK Vote. It's called, has a nice, they have a nice landing page and white paper and a prototype that's really close. So that's one thing that's really cool. There's a few L2s in the ecosystem which extend these nice decentralization properties of the base layer and sort of inherit many of them, but then with a little bit of trade-offs, give you super fast throughput or low latency, or like some extra fun feature. ProtoKit is one that's really exciting. Zecco is another one. Then there's, I guess there's some experiments. So I'll kind of migrate more in the longer term. So there's been some experiments around that I'm super excited about around science. So imagine, and there's a group that's been exploring this, but protein folding. I can prove that my protein was folded in a certain way to achieve this property in medicine, so that I can, invent a drug in my garage and not have it leak to Pfizer. So I don't need to hire lawyers to like facilitate some like drug acquisition in America. I don't know, but there's something interesting there, and you can extend that to like supply chain problems, like even in the kind of pharmaceutical industry, drug companies. If there's a small drug company that has some breakthrough, and they're being considered for acquisition by Pfizer or something, they have to work with these middlemen that charge hundreds of millions of dollars sometimes to prove that their system is working without leaking it, and it's just inefficiency. And it sucks when like money gets sucked out of the economy into these inefficient systems. It's kind of the same thing with like the same dream of DeFi. Like you can suck the kind of banking establishment sucks money out of the economy, but it's kind of providing a service that we can just get rid of when we use DeFi, and make it more inclusive and easier to access and all these things. And I think Mina's platform and ZK and all these things let you do this in the health space. Now there's some regulation and all these annoying blockers, but that's kind of like a really interesting thing. And then I guess one more thing that's maybe further out, maybe less far out than the health stuff, but I think more and more computation is going to be either done by some kind of AI system, like some AGI, whenever we get it, or depend on shit tons of data. And I think this is again like a little far out, but I think there's a lot of the nice properties we get from programmable cryptography, and most of those that Mina already provides, and maybe if we add a few more features, we can kind of fully get this. We can help kind of bring these really interesting AI systems on, into the world of the decentralized web.
Yeah, nice. And maybe for the protein folding aspect, you should contact AlphaFold on that.
Yes.
But yeah, very interesting to see like kind of the further implications of privacy here. So you mentioned not like cutting out that middleman, not having to deal with that, especially for those pharma companies, but then also you mentioned about voting, and then you mentioned about AI systems as well. So really great to see the really big landscape of use cases that we have here. I also wanted to touch on the how Mina is really helping with the developer experience. So you guys have your own kind of SDKs, and then even Snarky, your own DSL. So I was wondering, at least on the Snarky side, what was the intention that you guys had for developing your own DSL, and maybe you can talk about some limitations with existing languages.
Yeah. So so I'll do a story. I'll try not to ramble. So we started, so okay, let me take a step back. What is Mina? It's a blockchain with a pretty hardcore consensus mechanism, proof of stake consensus mechanism in it, and a bunch of other complicated like systems to make a real decentralized network, like a lot more decentralized than most of these other projects these days. But aside, and all of that is proven in a snark. And so, and we started building this towards the end of 2017. So at that time, what we had in the space of ZK tooling, like what ZK languages existed, nothing. It was essentially equivalent to writing assembly language. That's the tools we had. So we had really low level access to libsnark, which was like the only kind of production proof system at the time. And there were some experiments to get like C code running in snarks, but it was so inefficient and slow. So we literally were compelled to create a programming language because it was impossible to do what we wanted to do with Mina, to build such a complex system without having some tools, some language, a facility to let us reason at a higher level of abstraction than assembly language, effectively. So we started from that, and then it also happened to be the case that myself and Isaac and a lot of the early engineers working on this project are like obsessed with programming language theory, and there's not many programming language theory nerds that are also in ZK. There's more now, but especially at that time there weren't. So we were able to combine our passions, I guess, and create what originally was Snarky, which originally it's an embedded DSL in OCaml for creating snark proofs, but we've extended that and brought it to developers through O1.js, which is the same ideas but in TypeScript. So I guess just quickly, like the core of this, we chose to create a system that was like very much layered. So at the lowest level, like we still want to expose the kind of assembly language interface so that people can have low-level access to optimize things. But there needs to be a way to wrap that up in a nice package so it's easy to use with others. And the way to do that, if you're a programming language nerd, is you add types to things and you add functions. And so that's essentially what Snarky is. It's types and functions. And then I guess the other interesting thing is witness evaluation, so the stuff you do outside of the proof, and generating the constraints for the proof. And sort of just describing what the verifier does. Those two things are unified into sort of one interface. And so, anyway, we've taken that and we've brought it. We've evolved it over the years. It turns out developers don't really want to write OCaml that are not at our company, so we brought it to TypeScript. And developers want to write TypeScript. And I guess one thing I'll just end on, I suppose. I see crowds of people, so I feel like we're running out of time. It's so important to us when we were designing these tools, and we still hold this true. People don't want to learn a new programming language. They just want to do their fucking work, And this is why this new wave of ZKVMs is so great as well, where you can just write Rust or whatever. But okay, like let's say like you need to write a circuit for whatever reason. You need it to be faster. You need it to be you need to have more interesting access to the underlying depths of the proof system, which is something we provide. I don't want to learn some DSL that was probably, like, even if it was written by someone who's really good with programming languages, like, it doesn't have 1 million person hours of engineering put into it and all of its tools. And whereas something like TypeScript does have millions of hours of engineering effort put into the tooling. And so anyway, we express Snarky in all of its variants. O1JS is one. We're thinking about an O1RS. Not committed to it yet, but you know, it's very important to us that it's embedded within the language. So anyway, I guess one more thing on the like human side. We're structuring ourselves as an organization, and we've always focused on this. Like we really want to learn from users. We have what we call an exploration team at O1 Labs. This team, it's like a cross between DevRel and experimenting and working with users, you know, we really just want to build tools that are good to use and super powerful.
Yeah, thank you, Brandon, and really enjoyed hearing about all the design considerations that come about and how you really focus on the user side when incorporating these systems, and then also your vision as well with the proof of everything and then building an internet through programmable cryptography and how those kinds of intentions there really cater towards your decision making. So really enjoyed hearing that today and super insightful conversation. Thank you so much.
Thank you so much. Thank you for having me.
Yeah, thank you.
Yay! Okay, I feel like that's got to be a meme or like a quote on Twitter. Developers don't want to learn a new language, they just want to fucking build.
Yeah, I'll tweet that today.
Thanks, Brandon. Thanks, Alice. Okay, our next panel is going to be on using ZKs to implement layer 2 on Bitcoin. Yay! Ooh, the music's back.
Hello everyone, welcome to this panel where we're going to discuss today with the 4 guests how to use ZK to implement an L2 on Bitcoin. So today we have with us Jovela, co-founder at Fiamma. We have Orkun Kulish, co-founder at Cytria. Ayush Gupta, co-founder at Layer Edge. And Stefan Duan, dev lead at ZKM. Thank you for being here with me today. And I'm very excited to talk about Bitcoin scaling with you. So for context, Bitcoin is the most popular blockchain of today, also one of the most adopted and trusted, but it lacks some scalability features for it to have a more widespread usage. And today we're going to discuss how ZK can be used to address these scalability issues through L2 implementations. And we're also going to explore the role of OPCAT and BitVM recent developments on how to make Bitcoin more programmable and efficient. So the first question I would like to ask is, how do each of your projects use ZK? And what are the unique value proposals of your designs? And perhaps we can start with Jovela.
Hello, everyone. Yes, I'm the co-founder of Fiamma. So I will introduce our project a bit. So basically, our vision is to build the future of finance and the internet on Bitcoin. So there are a lot of like missing pieces, a lot of infrastructure that we need to build. So we think that definitely ZK is the end game for unlocking the potential of Bitcoin. So we build a ZK verification layer on Bitcoin that implement BitVM2 to inherit the network security of Bitcoin. And also, we are also building a pragmatically trusted Bitcoin bridge, also based on BitVM. In the future, we will also launch more infrastructure necessary to achieve our vision.
Yeah, hey everyone, I'm founder of Cytria. Cytria is Bitcoin's first ZK rollup. It's uses Bitcoin as a data availability and settlement layer, basically, to scale its security with better user experience and developer experience. It's a Type 2 ZKVM running on Bitcoin where developers can just pick their existing programs and deploy. And it will run with full Bitcoin security with a trust minimized bridge built in, so they can use Bitcoin in action without actually going through centralized and custodial solutions like wrapped Bitcoins or any other sidechain, basically.
Hi everyone, I'm Ayush. I'm from LayerEdge. So we aim to become the go-to security and verification layer on Bitcoin, and we do it like using the aggregation. So that we are trying to bring the cost of verification of a single chain on Bitcoin by like at 2 to 4% of the current cost using aggregation.
Hello, this is different from the ZKM and God network. So basically, God network is a Bitcoin layer 2 built on the ZKM and achieved the Bitcoin level security by verifying the proof by, on Bitcoin. Okay, so that's the first very important things that we use the ZKP to scale the BitVM, the Bitcoin. Okay, and another very important feature of the God network is we implement the decentralized sequencer. That means the decentralized sequencer can attract different participants, like the miners or the community, the communities. So we can use the ZKM to now those we use a proof network from the ZKM to generate the proof for the blocks, and then we allow the us to inherit the security from the Bitcoin. Okay.
Thank you, everyone. So one of the first things that comes to mind, to my mind, as someone that is not very knowledgeable about BTC scaling but has quite some knowledge about Ethereum scaling, is what was the primary reason why we could not build a Bitcoin scaling up till now, and what recent improvements in ZK technology have made Bitcoin scaling possible now?
Yeah, that's a very great question. So we know that ZK is a very prevalently used technology in Ethereum scaling. So basically, essentially, we all know that it can, just compress very complicated computations into very, small size, simple ZK proof, so that it can be verified really effectively on Ethereum. However, we cannot actually do that in Bitcoin until now, because you need to, if you want to, move that technology, the ZK in Bitcoin, the first thing is that you need to enable Bitcoin to verify the ZK proof. But now we have many new paradigm that can open the door for us, like BitVM. So we can enable Bitcoin to optimistically verify ZK proof. So which means that we can now ensure the state that they're being correctly verified by Bitcoin, and also for the asset bridging between Bitcoin L1 and also Bitcoin L2, it could become pragmatically trustless. So with this technology, we can say that what we are building are real Bitcoin L2s.
I think Bitcoin has been the home for the first of all applications. Even before Ethereum, people launched Satoshi Dice, people launched colored coins, Mastercoin, and even Vitalik wanted to launch Ethereum on Bitcoin through Mastercoin in 2014. But he couldn't because the tooling was not enough. And Bitcoin has changed a lot since then. Not maybe a lot compared to the other blockchains, but some important soft forks happened, like Segwit and Taproot, which eventually allowed us to use the whole block as a data availability layer instead of just stacking with 40 bytes or 80 bytes. So with this way now we are able to use Bitcoin as a data availability layer, which is the edge of being a rollup. where you get the full security of Bitcoin block space, because now we have the double spend guarantee, you have the censorship resistance of Bitcoin just transmitted to our rollup Citrea. And the second thing was obviously BitVM. I think last year, October, it was Robin's paper that came out. And immediately after, my chief scientist and I flight to Bitcoin Amsterdam to talk with him, actually. And in a month or two, we realized we can actually build a bridge using BitVM. And since then, we have been working on it. It's been more than a year. Recently, the BitVM Alliance founded. I think you are the only one in here that's in the alliance with us as well. So we are targeting to finish the BitVM implementation until end of the year. And hopefully after, we will have a fully trust minimized bridge that's only possible to build into a rollup, not another sidechain or other construction, basically.
Yeah, I totally agree with you on the fact that like after the BitVM, like the whole space has gone a lot of like boost, because once we are able to do like certain verifications natively on the Bitcoin side, then that opens like a big can of application that can be built. If we go towards the coprocessor way, then using that we can actually build a lot of like dApps which were earlier not possible, where all the computation will be like offloaded to a coprocessor, but all the verifications can be done natively on the Bitcoin side. And as we see like the growth of like ZK applications like heavily into like the Bitcoin ecosystem, like we designed like we found that the verification was relatively like a little bit costlier for the smaller application, which were basically built for one specific use cases. And for that purpose, like we started like working on the verification layer and how we can make it accessible to like everyone.
Since basically we have a lot of limitation when we implement the verifier on Bitcoin. That's we have some solution like the mission in BitVM. But here I want to say that yes, when we implement the verifier, most of the computation happen in the middle loop. So you can see that I think there's a paper that named Improving Pairing. There are a lot of optimization skills there. So the problem is, can we implement all those optimizations on BitVM2 right now? I think the answer is no. There's still a long way to go, I think. So so back to our projects, ZKM and Core Network on ZKM. So ZKM natively produce a proof based on the GNAC for the final proof. You know, ZKM is a layered architecture. We use a stack plank in the for the VM, and then we have a stack to SNAC, and the final proof is produced by GNAC. I don't know the difference between GNAC and ArcWorks. You know, BitVM to implement the verifier for the GNACs. Okay. So the middle loop for both is different. The middle loop of them is different. Oh, okay. So I want to say is how to optimize the verifier. Maybe is the key to implement the verifier on Bitcoin. Yeah, I just want to mention this part.
Okay, thank you. And so, from what I understood, BitVM was kind of a breakthrough in how to approach BTC scaling. But the other question I have is, how vital is it? And also, if OPCAT were to be enabled again on Bitcoin, what are the performances trade-off between using a BitVM approach, using OPCAT? Can you tell us more about it?
Yeah, sure. So for now, a lot of people will question like, you know, if BitVM is ever feasible, or how long does it take us to reach production readiness? But the answer is that actually it will be production ready very soon. Like, so for our project, we already have the full BitVM implementation on our verification layer. I think in one or two months ago, And then, and also for our BitVM bridge that we also have a BitVM alliance together that we are building like the foundation of it. So we estimate that that will also come out in the next 1 to 2 months. So yeah, so the answer is definitely yes. It will be production ready very soon. And your second question is around BitVM versus OPCAT. I think a lot of people kind of like overestimate the power of OPCAT. From our understanding, you can definitely streamline, like in the process of, how Bitcoin verifies Snark proof. But with Snark, like other proof system, it doesn't do much help. And then essentially, you still need BitVM even if you have OPCAT. And there are actually, more important issues that you need to solve. Other like potential opcodes that are better candidates to be reactivated compared to OPCAT.
Yeah, so for BitVM, like it's been built for like more than a year, but it changed actually like 3 versions. One was in the paper, which is based on gates, and the second was the CPU architecture, and the third one is the BitVM 2, or like variants of BitVM 2. It's changing a bit from now, from the paper, but it's still like the Snark verifier, and the Snark verifier is already being built. It's I think just like equal to 1 gigabyte of script right now, and there are teams working on chunking, and our team is working on Bitcoin Lite clients, as well as improving the winterness signatures. So it will be production ready very soon. It's not that far, or it is not unrealistic, but obviously OPCAT is something else. It needs to have a soft fork on Bitcoin, which is very hard to get through social consensus and also the technical challenges. But if we get ever OPCAT, I think it's we can still use BitVM style optimistic verification through OPCAT, but we don't need to do all the pre-signing stuff because we can build covenants using OPCAT. So it maybe still will be optimistic, but the experience for developers to build these bridges will be much more simpler.
Yeah, so like first I was like to tell like all the guys who are not very technical here that using the OPCAT we can do concatenations, and through that concatenations we can actually make whatever the process we are doing in the Bitcoin scripts more efficient. So like my point on the OPCAT is majorly like it will actually bring efficiency gains, but it's not what it's like projected to be, because if you see right now everyone is like going extraordinary like bullish claims on the OPCAT, which was somewhat exaggerated. Like on the Bitcoin implementation, like I believe it's like quite good. The thing is like using OPCAT we can get some efficiency gains there, but end of the day like the capacity of Bitcoin for processing is like relatively limited. So there we believe like there can be multiple different opcodes who can help that, because right now if you see the implementation it's like good for like few big players, but I see like there are a lot of challenges if you believe like there can be, let's say, 100 or 200 different protocols using like BitVM 2 all at once.
Yeah, so yeah, actually between the OPCATs and BitVM 2, basically it's like we implement the file based on Snark versus Stack. Okay, so basically when we from this point Snark is based on the group operations. It's more more complex compared to we verify the stack or we prove by stack. Yeah. So because the stack just needed the hash function. Okay, the hash function just needed the concates between 2 inputs and find and calculates the 1 output. Okay, so basically if we have the OPCATs, everything became easier, and it became as he mentioned, we don't even need the pre-sign, or we have not of pre-sign in Bitcoin too, right? So we don't need the pre-sign. We can verify the proof. We can really verify the proof by Bitcoin. Okay, so So from my my point is, I think we need to go forward with Bitcoin, with BitVM, and meanwhile, I think if the OP-CATs is approved to the mainstream, I think that's good for everyone, for the builder, for the end user, projects, So that's my.
Thank you. It's actually very interesting because some views presented are quite contradicted. And one of my questions is, on one side you have people that prefer snarks, on the other side you have people that prefer starks. On one side you have people that think BitVM is a very good approach. On the other one, some people would like to see OP-CAT enabled again. How do we make a coherent Bitcoin L2 space with all these different actors? And what would an ideal layer 2 space for Bitcoin look like with all these different actors and all these different approaches?
Yeah, so definitely there are many different opinions around this topic. And then for us, we think that at Fiamma, we would go for the most trustless and also the most pragmatic way to do things. So even when they're OP-CAT enabled, then we can incorporate that into our design. And then and also I think that we don't necessarily need a coherent L2 space in Bitcoin, because in the early stage it's good to have different teams that have different technologies. And from my perspective at Fiamma, we build things based on the fact that based on what exactly the problem is. So we see that now the problem is really in how to enable trustless Bitcoin transfer from Bitcoin L1 to other programmable blockchains, including Bitcoin L2s or other layer ones, and also how to enable more applications that can be built on Bitcoin, that can inherit the network security of Bitcoin. So that's why we build verification layer and also build the bridges and other protocols rather than directly build another Bitcoin L2s. So I think that we are also quite different in the case that we would look at the problem and try to solve it. And then a lot of other teams like Sachia, they're building L2s. They're also have a platform for other developers to directly deploy the apps on it. So I think it's good to have different things, so that you are not duplicating the work.
I think it's all about possibilities. Today for us, for our ZKVM, Stark is the best approach because it's faster and unbounded, and we don't have to write circuits from scratch. So our ZKVM proofs are actually Stark, but the verification is not possible through Stark on Bitcoin without having OP-CAT. So we do the best we can do by just wrapping the Stark proof into another Stark proof to be able to verify. If we were able to directly verify Stark, we will probably do that. But like I said, it requires OP-CAT to be added to Bitcoin through a soft fork, which probably takes time, and we don't want to get blocked by the Bitcoin social consensus. Instead, we want to just take the most practical approach to build what's possible today, and we can just improve our solution in the future if Bitcoin ever adds a necessary opcode for it.
And how we look at the future is very close to Fiamma, and that's why we are also building somewhere close to a settlement or a verification layer, basically trying to provide the Bitcoin security to most of the ZK chains that we can provide in a very cost-efficient manner. So for verification on the Bitcoin side, we actually prefer snarks, but the thing is what we are aiming to do is we have a lot of chains that have been built in the last few months. They have raised a lot good capital, and they have created multiple different type of ZK chains. What they're lacking is right now none of them is actually leveraging Bitcoin security in any of the possible ways. So what we are aiming to create is like a plug-and-play solution, how they can easily integrate their current stack to us, whereas we can provide them with like ultimate settlement and whatever like security needs that they require. Basically, infrastructure can be abstracted out for them so that they can focus on like building whatever vision for like whatever specialized apps or specialized games, whatever they're thinking of.
Okay, yeah. So for God network, yeah, I guess the question is about the decentralization and the programmability, right?
Sorry?
The question?
Yeah.
Yeah, is the balance between the scalability or the programmability, right?
No, it was more about the different approaches to scalability of Bitcoin,
Yeah.
and how do we make a coherent space, or even should we make a coherent scalability space? Like, for example, like Ethereum rollups basically all started by being like optimistic EVM rollups, because it was like the first approach. Should we strive for a coherent space as well on Bitcoin, or should we push for more innovation and new things and not rely on existing solutions?
Okay, yeah. So actually, I don't have much comments about this. Basically, for Go Network, we build on the ZKM, and the ZKM is a big ZK virtual machine ecosystem that support different layer one. Yeah. So Go Network basically it's natively a stacked design. So we have a decentralized sequencer. We leverage the ZKM generated proof, and basically I think that's more like Alias. That's we leverage different components and build the EVM compatible 100 EVM compatible layer for the developers. And the thing we also use the ZK use the technologies like BitVM to verify the proof for our God network. Make sure that it inherits the security from layer one. Yeah. So basically that's how it works, and yeah.
Okay, thank you. Another question I have is about trust assumptions and decentralization of Bitcoin scaling solutions, because it's not an easy topic, and I know the Bitcoin community is quite attached to these values. When using a Bitcoin scaling solution today, or in 6 months, or in a few years, what are the different trust assumptions that you make? How decentralized is it, and how censorship resistant would it be?
Yeah, I will give a very quick answer to this. So definitely for the bridge that we're building, then so far we still need to trust that one of the operators are honest. And then we are actually upgrading it to enable forced exits, which in other words, it means that you don't need to trust any operators in the future. So, but that's actually not a very easy thing to do. But we would keep, pushing this forward to minimize the trust assumptions.
Yes, so for any of the solution today, if you are not like getting double spend guarantee from Bitcoin and the data availability guarantee from Bitcoin, it's not possible to build anything trust minimized. So even though you have like BitVM bridges, if what you are building is a side chain which is on DA layer and on validators, then you add another security and another trust assumption, which makes everything not trust minimized anymore. So the only way is just using Bitcoin as a DA layer and then building a BitVM bridge is the only way to get trust minimized. Other than we have trusted solutions like Lightning, maybe even Arc, but those solutions are also like impractical on building applications. They're designed for payments, and they also have very strict scalability limits about the user experience, about the liveness, about the interactivity of them. So yeah, in the future, obviously everyone wants to be trustless, but it's not something easy to build. And especially for the solutions like we are building using ZK, it requires a soft fork.
Yeah, on the Bitcoin side, if we see, like we do not have any kind of like, complete native smart contract functionality. And what we're trying to do is like trying to emulate some sort of like functionality using the Bitcoin scripts. And so that like where we have come is like one of interest assumptions. I believe like this is like good enough for any of like the use cases which can be built majorly on the DeFi side, because theoretically speaking, you need one honest validator, but practically speaking, if you are one of the guys who are putting good amount of capital into any DeFi protocol, then you are incentivized to run your own validator. Until the process of running the validator is not very complicated and can be done like in a easy way, then inherently like the system will be honest, because there will be at least one person who's trying to secure his own capital, and in a way securing like the complete protocol.
Okay, so yeah, God Network, yeah, it implements, yeah, I should say God Network takes the decentralization as its first priority from day one. So the first component we build is a decentralized network, decentralized sequencer. Then decentralize the proof network. Okay, the decentralized proof network is already there from the ZKM. Okay, the next is decentralize the verifier by Bitcoin. So, okay, so I think so. For the security, when we say inheriting the security from the Bitcoin, okay, we usually include the security of the consensus of the layer 2, security of the lifeless of your layer 2, and okay, the last but not least is the verification of your verifier on Bitcoin. Okay, so. So from this point, yeah, I think decentralized is okay. Decentralized is really important from our perspective. Yeah.
Okay. Thank you. And in a world where Bitcoin scaling reaches its full potential, what are the implications for other blockchains and the blockchain ecosystem as a whole, and how crucial is ZK to achieving this vision?
Yeah. I think that Bitcoin would definitely be the center of the future of the crypto world, and also we also envision that it would be the foundation for the future finance and also internet, because it's still the most decentralized and most valuable blockchain, after all these years. And then so in our products, so basically we have like BitVM bridges or similar, implementation that we can actually trustlessly bring this BTC to all ecosystem, all layer 1, like Solana, Tron, Ethereum, ETH layer 2, Bits layer 2, different ecosystem, so that for the first time, Bitcoin holders can trustlessly engage in the DeFi fun things that happening at a programmable world. And also we can potentially still enable real world, real use cases of Bitcoin, like you can pay, basically maybe you can trustlessly mint your stable coin based on your Bitcoin, and then you use those stable coin or interest earned to buy the coffee or like other stuff, in the real world. So, so I think it would definitely be the foundation and the center.
Yeah, I think most of the other chains will be that, basically, because what Bitcoin created, like, it was the first blockchain, and everything comes after it is just tries to emulate some functionality that's not exist on Bitcoin. But with ZK proofs now, actually, we can do all the functionality on Bitcoin, just like we implemented EVM running on top of Bitcoin. So there's no need for other maybe EVM chains to also create an alternative, because you can do the exact same thing here, and you can just use the same asset Bitcoin for everything. So yeah, I think like it's already like there are a lot of chains out there that no one uses. So it will be much more like obsolete in the future as well.
So how we see like the Bitcoin is right now it is the chain which has the most amount of like capital on it, and that gives it a really big advantage compared to any other chain. Now the problem with the whole ecosystem is like you do not have any kind of smart contract functionalities, so you cannot do anything in a trustless way. And this lack of trustlessness is the thing that people are not interacting with a lot of like Bitcoin L2s or anything that's been built on Bitcoin. So once the security problem has been solved and user funds are actually secure, then it's a high incentive for the holders of Bitcoin to interact with these like protocols. And once we are able to achieve that, then that would unlock like a lot of Bitcoin liquidity for the Bitcoin L2s and everything built around it. And then that will actually bring in like good amount of developers. And with good amount of developers, we can create like a good amount of user experience. And once we have that, we can actually onboard like really new people doing something actually usable on the Bitcoin side. And here, how I see it, there's a little difference on the ecosystem is like the main Bitcoin will be more like a settlement layer, and all the executions will be happening either on a Bitcoin L2 or a side chain in a way because Bitcoin has a very big block time, close to 10 minutes, which is not apt for any kind of like real world application. So how I see is there will be like app specific, a lot of like layer twos which will be actually doing a lot of activities where people will be interacting with everything, and then everything will be settled on the main Bitcoin. This is how I see the future will.
Okay, yeah. So, okay, for the ZK, I think the first biggest application is the ZK layer, the Bitcoin layer 2, right? It's can empower the Bitcoin player, Bitcoin trader, Bitcoin builder to build all the different apps like the ecosystem in Ethereum, okay, DeFi, SocialFi, okay, everything, yeah. So it's a very big difference for Bitcoin, I think. So ZK also, you know, can, yeah, for developers, because we have for the Bitcoin we have the ZK, so we can trust the layer 2. We can, you know, have the more. We can use the layer 2 to do different DeFi there. So they can. That means we have more transaction. Maybe we can create more values, both for the user itself and for the validators. Okay, so that means it's also benefit for the Bitcoin sidechain or anything projects or any other projects like that. So I think ZK can, you know, make it real big difference for the Bitcoin. Yeah.
Thank you. I would like to know if we have any questions from the public. I think we do not. We do have one.
Right. I would like each one of you to see a little bit further in the future with Bitcoin as the liquidity layer, or all the other blockchains that supposedly only a fraction of what Bitcoin value is. Do you see a specific app each of you can kind of imagine for all of those?
I can maybe go ahead, like as a Bitcoin is the money, like it's created as a money, and like most of the other assets that is available on the market doesn't serve as a money. But as money, you have three properties like store of value, medium of exchange, and unit of account. I think Bitcoin has already succeeded on store of value, but the next two is the medium of exchange and then unit of account, which then you need actual places that you can use Bitcoin, and this excludes the custodial solution because it's just against the nature of Bitcoin. And as long as we are able to build layers and infrastructure to enable these two properties of the money, then I don't think any other asset than Bitcoin is required to be used as money. There will be obviously other assets in the world. There are many assets. There are stocks, there are commodities, but as a money, you don't probably need anything else.
Yeah, I agree. So definitely the store of value is the most prominent feature of Bitcoin. And so for a specific app that we envision is that it could be a stable coin or a payment app, so that you can actually have your Bitcoin, you know, locked trustlessly on a Bitcoin, and then you can also, you know, mint stable coins and also earn interest based on your Bitcoin. So you can also use in everyday payment. I think this is a much better approach than a lot of our fiat. Yeah.
How I see this ecosystem growing is like as like you guys said, it's correct. Like the Bitcoin is more like a money, and how I see is like there will be an emulation of whatever the financial activities that happen outside in the real world on the whole like Bitcoin space. And like how I see there is like there's like a really good opportunity if you guys like if anyone tries to use like core processors, because on the Bitcoin side we can do some sort of verification, but all the heavy computation or like we can create like actually very close to like order book or dexes and many other functionalities that are now coming upon Ethereum side, they can be directly emulated on the Bitcoin side, because on the Bitcoin we do not have any native smart contracts. So you can easily offload everything to core processors and you can just do the verification natively. So that can help you a lot.
Yeah. So when okay, yeah. So when we talk about the liquidity, I think the first important is we need be able to connect. I think we need to be able to connect the different chain. Like we have the different solutions for the permissionless bridge between the yeah, most of the layer 2 maybe EVM built on the EVM. Okay, so meanwhile we also need to consider Ethereum. We have a lot of topic about why Ethereum become what it is today. So I think from there we need to consider how to connect the different layer 2 and make sure that not go back to the layer 1 to the other layer 2. Yeah, we need to consider connect the layer 2s natively. Okay, so from this point, I think we may need to have a consensus of maybe have a specific between or maybe a framework that's between the different layer 2s that they can recognize each other, like we can, okay, this is very good. Basically, we in ZKM there's concepts like the entangled rollup. Okay, it's basically a framework that's a different layer 2 can interact with each other to make sure that the liquidity can be flow between different layer 2s. Okay, so yeah.
Okay, thank you everyone. This will be the end of this panel. Thank you for participating and answering the questions and the discussion.
Thank you.
Thank you.
Thank you.
Thank you.
All right. Thank you, everybody. Our next discussion, well, actually, it's a presentation, is going to be by the team at GOAT.
I missed the demo. I'm sorry. So when are you going to talk? Right now. Over there. Pavel's over there, yeah. Where's the clicker? Okay, he's preparing the demo. I'm just gonna go through my slides, and it'll be fine, yeah. And if he can't do the demo, I'll finish the slides for him. Okay, he'll finish those, and if he starts walking over, we'll let him. Yeah. Yes, thank you. But if you wanna move everyone out, so I'm not talking over people in the back, if we can just bring everybody forward. If we can bring everyone forward, and we can stop talking in the back, because my voice, I have a very hoarse voice, so I'm trying not to scream over everybody. Okay. And let's see if this works. Great, it works. How do I go back? how do I go back?
Oh, forward and backward.
Oh, let's go back. Okay, I can't go back. But anyway, we're scaling Bitcoin with Bitcoin VM2. So in this presentation, what we're going to do is explain to you mainly about what exactly GOAT network is and exactly how we're going to be scaling Bitcoin and exploring ZKM on a layer 2 with GOAT. Okay, so the point of the presentation that I'd like to bring to you, if this, okay, can we go back one slide? Can we go back? Yeah, thank you. So Bitcoin has a lot of scaling challenges. First of all, the cost over time is becoming exponentially more and more computationally difficult. Bitcoin is doubling its hash rate year by year, and with this hash rate exceeding computational costs over time, we have nothing to actually combat that cost. And development technologies such as layer 2s, there are not enough development technologies for Bitcoin that allow us to actually supplement for this cost. So as Bitcoin becomes increasingly more and more expensive over time, but the development frameworks are just not there, then what we worry is that Bitcoin will not have the mass adoption that we're looking for. And so Bitcoin adoption really is interdependent with the tooling that's involved. And so we lack modern tooling, and we do need to develop these tools. And another huge problem with Bitcoin and its scalability, and these are a little nuanced niche points, but they're very important to think broadly about, is that maximalism is not necessarily a favorable or even like a progressive style of innovating our technology stacks. And so when a Bitcoin maximalist is looking at you and looking at us, and we're trying to develop a framework that's actually going to scale Bitcoin, the problem that we're always facing is that when speaking with maximalists, the mentality alone is not anarchist enough in order to actually complete this narrative that they have about decentralization or sovereign data or even privacy for that concern. Right, so maximalism is actually stopping innovation, and we need to open our minds a little bit more about what exactly our solutions could be for layer 2 or for Bitcoin. And the fact that we don't have enough trust as holders, most Bitcoin holders, if you're a holder of Bitcoin, I don't think most people would hold and trust others and other custodials with their account or even with private equity. So it's very hard to convince a central sequencer, especially a large capital fund, to stake a lot of tokens, especially in Bitcoin, when there's already so little of it. So how little of it? Well, first of all, we have many coins. We have WBTC, we have BTCB, we have CBBTC. But of all of this supply, we have about 219 million holders of Bitcoin, but realistically, there's only around 300,000 to 500,000 actually daily active users with and using Bitcoin. So most of the protocols that are out there are explaining how they have a yield optimized strategy for their layer 2 network. However, how is it that you can generate a yield when you don't have enough transactions? And the analysis that we've done does not prove that anybody who states that they have a yield optimized protocol in Bitcoin is lying. So you're lying. We know that you're lying. And we know that we're lying because there's only 250,000 Bitcoin in actual circulation. So the percentages don't match up. When you allocate the yield and the optimized yield, which is anywhere between 3 to 5%, and you split that across 90 different blockchain projects, there's not enough Bitcoin to go around to make that yield. So either somebody is faking the number or the money is not actually there. So how do you decentralize this liquidity? Because the problem with Bitcoin is that it's overly collateralized, but also overly centralized too. It's not even mentioning it. We go to the next slide. Yeah. So our challenges when trying to think of a Bitcoin layer 2. These are the challenges that you're going to have to think of. First of all, the building a cost-effective and fast ecosystem. Cost effectiveness of a layer 2 and the rollup architecture is more of a data administration problem. If you have a DevOps that's actually engineering with you and your team, cost optimization is usually key when it comes to actually creating an infrastructure, or let alone a network. That's hard. But let alone you have to decentralize the sequencer. The decentralized, The decentralization of a sequencer is rough because you have to create a prover and a verifier relationship with computers. And they also have to enable a consensus that is strong enough to guarantee commitments to and from Bitcoin. So you have to enable some sort of sequencing relationship because BitVM2 and many of the other white papers that have come out about what exactly is a permissionless bridge in Bitcoin, it's always a centralized sequencer. There's never a decentralized sequencer in any of this. So when talking to a lot of Bitcoin maximalists, they're never saying, oh, like, thank God there's a centralized sequencer. They don't know about this. Like, Optimism is a centralized sequencer. Arweave is a centralized sequencer. They're all centralized sequencers. So, again, I'm gonna go through all of this, but eventually you have all of these project ending challenges, and so we needed to say, how are we gonna decentralize the sequencer? How are we gonna actually commit to and from Bitcoin using some sort of optimistic challenge process where we have a consensus? And how is it that we can actually bridge Bitcoin to an Ethereum node where we can actually lock in the GOAT BTC value where we have a mint and burn with a verifiable proof of correctness somewhere? How can we do that? So ZKM. ZKM is a generalized architecture. I'm gonna explain a little bit more about what can we go to the next slide? Next slide, there we go. So ZKM. ZKM has benchmarks, but these benchmarks prove, these prove multiple things. First, ZKM is general enough for us to run Starks, Plonks, as well as Gross16 through multiple instruction sets to create a zero-knowledge proof. Zero-knowledge proofs usually are free. They're not actually computationally expensive, especially if you're using quick error arithmetic or you're using specialized ZK provers, for example, right? There's optimized ZKPs. In MIPS, you're using a generalized and constant size proof segment. And so these segments are in constant size, so it's easy for us to prove large amounts of data using programs such as in Go or in Rust, and we're gonna do this with data. We're gonna do this now with general data that we could not have done this otherwise with a token proof, such as others that are gonna require a token. Others, like Alio, require a token. Others that don't require a token are like MIPS architectures. So this is the decision there. We use a generalized framework so that we can create a zero-knowledge proof in the cloud that does not rely on a token, and it also gives us a general framework for how to create a consistent size of our execution traces so that Bitcoin and GOAT network can create a winter snitch signature that can be posted and verified to and from Bitcoin. And how? So our cost and the entire stack is realistically these segments. So first, to relay back to the first thing, you need a cost-efficient ZK rollup. What is that? Well, first you have to use an in-house ZKVM. So the ZKVM needed to be hand-selected. We chose ZK MIPS because it was general enough for us to create a generalized commitment and verifier. The other thing is that, okay. The other thing is that we needed to generate a low-cost zero-knowledge proof. So because the cost of ZK MIPS is generally pretty conservative, the speed outweighed the cost. And so we have a well-balanced node that runs now roughly in terms of Amazon cloud credits. You can expect it to be anywhere around 8,000 to 9,000 monthly, but depending on DA and depending on prover and depending on how you're setting up your system, the key is that you can optimize memory. You can also optimize performance of a ZKM. So I'm giving you general cost, but I'm saying that the cost is already conservative. You can continue to optimize further. So you data sync with this ZKM. We have a roll-up economic model. We have an interesting white paper as well as a beige paper on our website on goat.network. I would give you a full synopsis of what that is, but it's essentially an economic paper on how exactly Goat Network intends to create a yield optimized layer 2. So what that means is that Bitcoin is our layer 1, and we are generating a verifier script through Bitcoin VM2, right? Or BitVM2. Our consensus relies on a decentralized sequencer that uses ZKM to roll up block space in order to create a commitment and to verify that commitment through Taproot. And so Taproot, acting as our verifier, we're able to then say some block space had some proof allocated to them, and we can verify this directly on Bitcoin. So the last panel was talking a lot about how now we do have an actual native solution for Bitcoin. Is this built yet? No. This is phases. So I want to point out that this is green, it's yellow, and then it's purple. So this is our phases. So it's effectively what we have done now. Today we have created the ZKVM, we have decentralized the sequencer to a layer 2, and we are also optimizing the token allocation of yield. So yield that's generated on Bitcoin can now optimize yield on a sequencer, and I'll show you what that means. So that's the realistic path forward. Can we go to the next slide? Thank you. This is effectively the diagram of what Goat Network is going to do. At the end of the day, you have BTC holders that can lock directly on Bitcoin layer 1, and you can decentralize the sequencer. Decentralized sequencers own the total lock of the Bitcoin, but they have a multi-party computation and an agreement of who actually makes the commitments to and from Bitcoin, right? So you create the SSR or the SRS ahead of time, and then now you have a strong guarantee that the committee of these operators, the one that's making the commitment, has the existential honesty assumption with Bitcoin. That is the risk. The risk of the commitment being incorrect is the fact that the one making the commitment can change the data when it's being committed. But when you have a multi-party computation, you're actually enabling the system to have an optimistic challenge with said data without necessarily revealing it. We're going to then issue YBTC. So every token on the network is GOAT gas, right? Gas tokens are Bitcoin. So everything from the ground up, we can relock this into a sequencer and then generate YBTC, which is the yield of the protocol. So when sequencers earn rewards, they're effectively minting the yield of the protocol because people have already staked and locked the token of gas, which is Bitcoin, to the sequencer. Okay, so you can do this from either L1 or L2. I hope that's clear, and we'll go to the next slide. Cool. I like to give this image of what exactly the end game is. Why are we doing all this? At the end of the day, we're creating an entangled rollup. It's a lot, but it is true. We have an entangled rollup scheme, and in the middle we have Bitcoin, and onto the side we're using BitVM2 and Taproot. We also want to be able to enable operators that have a multi-party computation in which this committee commits and verifies through Bitcoin. We then have operators that run an optimistic challenge process, and then we use such as Starks, Plonks, and Gross16 to create validity proofs in order to create an effective rollup in ZKM. And now the Ethereum virtual machine is the execution environment of Go. And so we're using Geth, and so this way we can actually wrap the node in Geth with MIPS. So it means that we're able to perform what's known as strong interoperability. Strong interoperability is when we can prove the state of execution as well as the node itself, as well as the time of block, how many blocks, and data that is on the chain now versus what it was yesterday. So effectively means we can prove time, block time in real time, and also make execution traces, which are effectively, I create a state of a program, I'm able to then prove the state of that program afterwards. So it means that we can say chain A had performed some transaction of either stake, lock, or deposit, and chain B is willing to accept the arguments passed to chain A because both chain A and chain B agree to the same prover and verifier, which is the decentralized sequencer. The decentralized sequencer holds the same zero-knowledge proof. Therefore, both chain A and chain B can rely on this idea of consensus between one another. Now, the ZKM is a little bit of a mysterious protocol, but I wanted to show you how general it is. Pavel over here actually has a whole other side of the demonstration lined up for you of how ZKM works and an example of it running in real time. And in case you wanted to use ZKM in your own Bitcoin project or even using it on Go, I would suggest, yeah, this is going to be pretty interesting. So take it away. Thank you. Hello? Oh, yeah, yeah.
Of course.
I'll take this.
Awesome. All right. Hey, everyone. My name is Pavel, and I'll be going over a real-world example using ZKM. A scenario that is currently present is that there are data brokers. Data brokers exist to essentially take data that is present in public domains, public records, or they go out and they buy it directly from providers, and they do so for advertisement purposes or different types of analytical purposes. And there are self-reporting mechanisms as well. So for example, survey data is collected from different users, and that survey data is also used within these systems. There currently is no way to collect this data in a way where it doesn't depend on a single centralized provider. We want to create a way where data is, anybody can actually send the data, and that data can be validated directly on the user's computer, and as a result, that data can be then appended to a database with the correct data types associated with it. So I don't need to essentially run any type of front end or back end. I can just have the database where it can accept a proof as well as the data, and you can be guaranteed that even if anybody, an untrusted source comes in, as long as they have a proof, a validity proof of that data validation, they could submit it. So I guess next slide. And next slide.
Can we click on?
Oh. Yeah. So we want to collect data from the user directly, and we want to reward the correct information with the proof of correct execution. And users can redeem the proof for an on-chain reward. In this case, I would demonstrate the reward being an NFT. Next slide. So this is the overall architecture of how it looks like, very simplified. The user provides input. It goes into the ZKVM program. It then outputs a proof. And using those same inputs paired with that proof, you can insert, the user can insert the data into the database in a way that you don't have to perform any additional data validation checks because the ZKVM already operates in that way. Next slide. This is a bit more complicated diagram. It basically outlines what is going on internally. We take the inputs and we structure them, put them into the guest program. The guest program is the actual program that runs within the ZKVM. And then that goes into and that outputs a proof, and then that proof gets returned to the user, and then, same as the previous diagram, we get the proof and the inputs directly going into the database. Next slide. The whole step-by-step process, program execution, proof generation, and then proof verification is the final step. Next slide. And the main benefits of this is we can upload any information directly to the database without a centralized backend checking that data. So essentially, we can do a super scalable way, and a way that guarantees that the data is, in fact, passes validation checks. And then one use case is that the form data validation for community compiled data sets. We see that AI and all these models are being trained on the different data repositories. So we can actually create a community collected data repository from anyone, and no single centralized provider can come in and change that data because it's secured via these ZK proofs. Next slide. And we have compliant data brokerage services and checking to see if the person has valid data before sharing. Next slide. So over here, I have a brief demo of this, and I guess we'll switch to the overall workshop slide. Perfect. So over here, I have a speedrun Ethereum app, and let's see. I'm gonna exit full screen just a moment. Okay, perfect. So I have over here, I can provide an email, an ETH address, and a number. When I click submit, this will go in and generate a proof related to the submission. So if I put in some basic information about the data and validity, and I click submit, this routes to an API,
And this API makes a request and generates a proof of execution. So over here, we have this being run within the ZKVM, and I know that's very small within this, but essentially we are coming in and we are running this program inside the ZKVM. We are given the execution and the results of that execution. Now, this took 30 seconds. This is essentially running a version where it's executing only. If I were to do a true execution, so if I were to make the exact same request, I might have to restart the back end, click submit, and then as a result, we can go in and we can see that there is a seg number in here. This is however many segments that it takes to prove this. And each segment, the amount of time that it'll take to prove. So here's a previous proof. So there's 31 segments, and it took roughly 210 seconds, or 1,210 seconds in order to prove and generate the prover output, or the proof of that computation. And the exact program for this proof of computation is within here. It's a Golang-based program. And all we're doing is we're checking and we're validating the email, the ETH address, and the number. And this is passing through this checker, which checks each and every one. And this is running within the ZKVM. And so it takes roughly 1,200 seconds, which is roughly 20 minutes in order to generate the proof. Well, we don't have that much time. So I did create a pre-created proof where once the proof is generated, we get the output. We can then send it as a client, and we send the transaction with the proof. Then we can see that we have the hash. I am the owner, I am the one who sent it, and I have an NFT of the resulting data. So I've essentially sent data. I have generated a proof with the input data, and then after that, I essentially relayed that information and proven that this proof, as well as the inputs associated with the proof, are correct and valid. And this is checked directly on the blockchain, and as a result, we can guarantee that the execution did in fact happen, and then this is a correct output and result. Now, you know, there's additional validation checks. If I try to mint the same NFT with the same data, it'll say, no, you can't do that because there's a duplicate submission. So this is how we prevent people from reusing the same proof or reusing the same information to the same data set. So we can include additional validation checks directly onto the smart contract because it knows what data that you're actually inputting. So as a result, we can have a append-only database where if you generate a valid ZK proof, you can append certain data to the information and then receive reward, in this case, an NFT, where you can then transfer it and do information from that. The code is open source, so you can try this out yourself. I've included the repo, and yeah, thank you. That's all I have to present.
So what's the advantage if you anyhow send the data to the database? So what is the advantage of the proof compared to the simple SHA hash? Right, so anyhow the privacy is compromised against the database because we send the input. So why shouldn't we just use a hash for that?
So, well, the hash doesn't necessarily expose the data. It just shows that the data that was provided matches that hash that was sent. So I can't, from this hash, I can't really derive the data of the information that I'm inputting. So in this case, I don't know what data that I'm committing. I just know that it's this data.
So you just send the proof of the input, you don't send the inputs?
No, you can send the inputs. And this can be to a centralized database as well. So the data broker and provider can also, say, well, like we will only accept information that you send to us directly. And so as a result, the data broker can have certain types of restrictions based on that. Or this can be like an open IPFS-based system where you can directly commit to an open data structure for this. So it's more of like a primitive where you can take this and bind this to different implementations based on the use case. If you're a data broker, you might want to be private with the data, but you still want anybody to be able to commit if they have like certain, if they pass certain validation criteria. Now, of course, we're doing it with very simple email form, and this itself takes like 20 minutes. But the idea is that we can take arrays or we can take entire spreadsheets and then compile it down into different individual records and then have all those records be validated without requiring a centralized database, or sorry, without requiring a centralized backend or front end to be able to manage this. So I can run this all locally on the device, and then afterwards I can just append to the database directly. I guess there's one more slide over here as well, just to what the limitations are, of course. So one of the things is that we can't check if the data exists before the payment is being sent. So that's unless I append directly to the database, or sorry, unless I append directly to the blockchain, then there's no way to really check if the data is available. So you likely need to have this matched with like a different provider with like, for example, BNB has a Greenfield, which is basically like a data storage layer. So likely some combination of architecture would be used in order to support this specific use case. But the idea is still the same. We can append to the database with a valid proof without requiring so much infrastructure in terms of backend and front end. Just with the ZK proof, you run it through the checker, and then you can send the data. Perfect. I think that's.
Clears up the like what you or can and cannot do. That's what these other examples are for as well. Like how would you complete a full program in use without rollup? Is that you're creating a program that you want to be able to verify data, or it's public data, and you can verify it against something. Yeah, he created a proof, but then the guy that's submitting the input can also verify whether or not the data had ever even been included to begin with. So now you can verify, not like accounts, doesn't mean it's, ZK is not like an Ethereum thing, right? Like, but you can set permissions on like input and output variants on a ZKM. So you can upload it through BNB Greenfield, and why that's a good idea is because it's a smart contract DA layer on Binance. And then you have Bash, which is the way of doing anything in your terminal, so you can actually create multiple environments to spread out your proof, so you can have multiple instruction sets running parallel. So the ZKM is, it's just a machine that's running, and of course you can set up proxies so you can protect. You don't want to do injection attacks with a DB. Even with Alio and other ones, any prover network that allows you to just inject straight into the database means that you can read from it and you can do a lot of bad things. You don't want to inject in DDoS. So that's why you would run those kinds of things. So you, yeah, just think about your stack and then like layer those on top of it. I think we're out of time though, yeah.
Yeah.
But you guys are doing a great job. That's fine. Yeah.
Awesome.
Okay. Thank you so much, Pavel and Dylan. Appreciate you. Also love a live demo.
Yeah,
almost as much as I love a dad joke, but you know.
Awesome.
I'll take that at ZK Hub. Okay. All right. A round of applause for the two gentlemen on stage.
Perfect.
Yes. Such a gentle applause. Yay. That's okay. We're getting to the end of the day. Wanted to thank you all for being here with us at ZK Hub. I know that there's a lot going on in the marketplace, tons of delicious Thai food to distract you and then also make you kind of tired for the rest of the stuff. But multiple concurrent events can also feel a little chaotic if you're not, you know, the most comfortable with navigating a new space. So appreciate you all for being here and for being so involved and active. I also just wanted to highlight that tomorrow's programming will be publicly available. Not that this wasn't publicly available, we just didn't do the most excellent job of making it easy to find. So we will share that on Luma. It will also be shared on the ZK Hub website. You just have to click into November 11th. It doesn't look like a button. I don't know who designed it, but it'll make for a good joke or a good memory at the end of all of this. They're really walking around like, there's talks happening? Like, what's that room with all of the equipment? So, all right, so on to our next talk. We have the Panther team as well as that's representing ZK Monk. Yeah? Okay, awesome. Round of applause, ladies and gentlemen.
Hello, everyone. My name is Igor Markelov. I am the app architect in Panther protocol. So, and today the topic of my presentation is private data sharing to enable compliance in DeFi. But first, let's start about compliance in traditional finance. What are the main requirements to be compliant in TradFi? So first requirement is to have KYC, so you need to know your customer, so you need to verify customer identity, to collect and validate identification documents, do a risk profiling of customers. You also need to do anti-money laundering. You need to implement transaction monitoring. You need to perform suspicious activity reporting and record keeping for some period of time. And as well as perform risk assessment of those transactions. And there is also a requirement to have a capital to prevent failures during some financial crisis or to cover risk associated with financial systems. There is also a reporting requirement, so you need to do a regular financial statements, and also you need to perform involuntary disclosure without explicit agreement of the user in your system. For example, if there is an order from the court and they oblige you to do that. There is also operational requirements, so you need to be cyber secure. You also need to implement consumer protection, so you need to be compliant with GDPR laws or, for example, with CCPA. You need also to do trading and market conduct, so ensure best practices of your execution. And of course, you need to have licenses and your employees needs to have certificates. And specifically today, the focus of my talk is reporting requirements, and I also will cover KYC and IML. And especially how we do implement it in Panther protocol. But let's first start what is Panther protocol. So we enable privacy for regulatory compliance for licensed operators. And in terms of technical requirements, we have the following. So we are having multi-asset shielded pool with unified Merkle tree, unified of accounts UTXO and assets UTXO. We also share anonymity set across different supported networks. So Merkle trees on different networks are synchronized. And to verify customizable rules, we use Grove 16 protocol. And what about components? So with the main components of the protocol, so is the account. We also have KYC and KYT attestation. We have a notion of zones inside of the protocol and zone operators, and we also do data escrow. So I'll talk about each component in detail. So what is an account? It's the same as in banking account you have. It's it's account that contains your information that allows you to do a transaction. It can contain some, for example, cryptographic keys or expiration dates or some limits of your operation. In Panther protocol, we do not store any private information inside the account, so only information required to perform transactions. So every transaction, as I said before, we use account UTXO, and every transaction, it spans the account UTXO, and then it creates new account UTXO with updated limits and other information encounters. So on every transaction, user proves that he owns this UTXO using Grow16 protocol, and we also assume that one user has one account. And how we do that, we perform KYC, so which stands for Know Your Customer. So we have this KYC is performed during activation of your account or renewal, and we use third-party service that is trust provider for us. This third-party service, it stores personal information, and it's managed by this provider. What exact information needs to be used for specific customer or zone is specified by zone operators. And if everything is okay, trust providers issues EDDSA signature that is later verified in circuits. We also perform KYT. On every transaction, user has to submit their KYT. So we have third-party services that is responsible for KYT of the transactions. What inside of this, there are rules that are specified by zone operators that I will talk about next slide, but these rules can define, for example, deposit and withdrawal limits, some internal limits, like one transaction cannot be more, let's say, than $100, and some inter-zones rules. So one of the zone operators can have different zones and define, okay, you can transfer from one zone to the other one, but not back. And if everything goes well, again, this trust provider issues EDDSA signature that is verified in circuits. Those trust providers, they have access, of course, to this private data because they need to know, for example, what is the token of the transfer, what is the amount, and source and destination address. And finally, who are the zone and zone operators? So zone operators is the licensed entities in our protocol, so they define some zones inside the shielded pool, and one zone operator can have different zones with different set of rules, and he or she defines KYC and KYT rules inside of each zone. It can also define transaction limits and inter-zone transfer permissions. So every transaction is tied to specific zones, and for the external observer, it's indistinguishable where the transaction happened. And finally, to be compliant with reporting requirements, we have data escrow. Data escrow specifically designed to enable involuntary data disclosure. When user is not cooperating and we have, for example, order from the court and we need to show some specific transaction and they needs to be disclosed. So for that purpose, on every transaction, the user encrypts private information of this transaction using public keys of data escrow manager. Then we verify this encryption inside the circuits and save this transaction on chain. Because this is the public inputs, encrypted information is the public input of the circuit. So basically this information is saved on chain. Also to remove incentive from the data escrow to open every transaction, we can implement some multi-party computational simple MPC that will share the keys of data escrow manager, for example, with zone operator or KYT provider or even a DAO. A little bit about the technical implementation. So for data escrow, we're using LGML on elliptic curve. So I'll talk about algorithm, how we do that. So on every transaction, user, before making a transaction, basically creates the random, ephemeral random, and computes ephemeral public key. Then he computes some secret using data escrow public key. This secret is basically point on elliptic curve, and then in order to encrypt the message, which is point on elliptic curve, he adds this secret to the point. And as a result, you produce C1 and C2, one of which is encrypted point, and the second one, ephemeral public key. And this encryption is checked inside zero-knowledge circuits. So in order to decrypt that, you go in a backwards direction. So you have C1 and C2 is your public inputs. So data escrow manager takes his private keys and computes the shared secret, which is a point on elliptic curves. And then just by negating this point and subtracting from the encrypted point on elliptic curve, he gets the original message. Okay, this works for the points on elliptic curves, right? But private information, it's not only points, it can be also some scalar data, and mostly it's scalar data. So we also need some way how we need to convert this scalar data to points in order to be able to encrypt them. So we use so-called encoding, scalar encoding, where we split large scalar numbers to 32 byte chunks in order to ensure that we can basically reconstruct these scalars. And we take these 32-bit chunks and multiply it by point generator, and get the point on elliptic curve. So when you decode, you always sure that you can go back, because you can basically search through the whole space of 32-bit numbers and finally find your point on elliptic curve. And the simple MPC, as I said before, so to remove incentive from the data escrow manager to decrypt every transaction that happened on chain, so you can use this simple MPC. So one of the public arguments can be encrypted further using the keys of, for example, Zone or DAO managers, and then using the same approach with Algamal encryption to put it as a public signal in the transaction. And in order to decrypt, so if you want to decrypt specific transactions, you first need to ask Zone Manager or DAO to decrypt these parameters for you, for escrow manager, and then only then escrow manager can do the rest. And this is just a summary slide how the whole process works. So we start with the private data that has scalars and encrypting and EC points, points on elliptic curve. Then we use scalar encoding for converting scalars to the points. We encrypt these points and then use MPC to distribute the keys. And all of those is verified in zero-knowledge circuits. And reverse process, again, it's very simple, basically the same steps, but backwards. Okay, so to sum up, we, in Panther protocol, enable involuntary disclosure via private data sharing. So we use zero-knowledge circuits, and we encrypt private information using Elgamal encryption. So we use a simple MPC to remove incentive to decrypt all transactions from data escrow manager. And as I said before, we utilize zero-knowledge circuits to verify encryption integrity. So all transactions are stored on chain, so it's always available. So a little bit about ongoing work. So we also want to improve scalar encoding. So we would like to make for data escrow manager to do decoding, for example, some to be computationally expensive. So to do so, to make sure that he doesn't decrypt all the transaction, and yeah, basically for that. And we also want to create selective disclosures, so when the user can disclose specific information, because in the example before I showed the decryption of the whole private data. But for the user, it's not always necessary. You can just decrypt or verify that some specifics of your transaction. For example, if it were lower than some limit. And finally, we are launching Canary Network on Polygon this month. So Please, everyone, welcome to test it. Thank you very much.
Thank you so much, Igor. It is no small feat to be launching on testnet, so kudos to you guys for that. And for our final presentation of the evening, we have Abbas, who will be representing Starkware at StarkNet. We have Abbas, many people online with us right now, so do not let this small group here be any signal that they're not excited for you, just as I'm excited for you. So, oh, you're here, hi. All right, so welcome to the stage, our guy, Abbas.
Okay, perfect. So, a quick intro about me and what am I here to speak about. So my name is Abbas. I'm currently a part of the ecosystem team at Starkware. Starkware does a bunch of ecosystem initiatives. I'm sure you know about what StarkNet is as a chain and what it does. As a layer 2 for Ethereum, going to be a layer 2 for Bitcoin as well, settling on both chains. But I'm here to talk about something very specific. I'll, of course, run through some details about Starkware and what it does. But yeah, let's maybe start with that. So StarkNet is trying to solve a very core problem in the ecosystem, that is there's a lack of ability to trust in institutions, and StarkNet is trying to solve that. Introduce an integrated web that allows you to trustlessly participate on chain, hold your assets, do a bunch of things that let you include yourself in an ecosystem. That is the user, someone who's a developer, someone who's an operator, where's a validator, there's a bunch of other stakeholders that can participate on chain. All of that is what StarkNet is to do and is currently doing. I'm sure you can already see some of the technical achievements StarkNet has, the TPS improvements, the focus on performance, all of those things. For the longest time, we've been focused on performance and improving on-chain capacity, allowing more innovation to happen on-chain, allowing things to be happening faster, whether it's for games, for DeFi, and so on. But lately, we moved our focus to even building more apps, just focusing on having more ecosystem participation, having devs show up, having on-chain contributions that matter a lot more, especially for traction. If there's a thriving ecosystem to build products on-chain, then it allows anyone to, or helps anyone as a team or as a product to come along and be like, you know what, I'm going to build on this chain because there's traction over here. And I can find talent, I can find a bunch of things beyond just early liquidity. So that's what my focus is. So like I said, I work on the ecosystem team. We had this initiative called the Wolfpack League. Some context about me. Prior to this, I've been a part of, an early member of this community called Super Team. I used to work with them. I led their bounty program for like 1.5, 2 years. Worked with Avalanche, helped them build their bounty program as well for a bunch of internal community members, ambassadors, things like that. Been in the ecosystem for a while, mostly focused on helping devs get started on chain. And that's exactly what we're doing here as well. Trying to help builders get started, contributors get started on chain, creators participate, get incentivized, get rewarded for all their actions. All right, so what is Wolfpack League? Wolfpack League is essentially for any creator and contributor to be a part of the StarkNet ecosystem, get rewarded on chain in Stark tokens for contributing to the ecosystem. Now that could mean you write a deep dive, an essay, produce some video material, write some memes, create some memes, build something. And all of that's possible. And this is an exclusive community of about 200 to 250 people that are part of the group. It's a Discord server where we manage, talk to them, engage with them. But it's an active community that does things on their own, out of their own interest. So they want to go contribute and they get rewarded on the back end. I'll speak about more on how that looks like, but you can always read about the platform itself on the wpl.xyz, and you'll find more information over there. All right. Where does this all come from? So like I said, I've been doing this for a while, building bounty programs, building communities for chains, ecosystems, products, protocols. And my theory is fairly simple. I think every chain, every ecosystem needs a good home base. A home base simply is you need someone to create an environment for and the right conditions for people to thrive in, and somewhere you want to go again and again, and especially virtually. We all have that in our local spaces. We have our friends that we want to go to and see often. We have our local communities, our religious places, a bunch of those things. But on-chain, virtually, we have very few. I think there are NFT projects, NFT collections, some people are like align with more, so you like show up in those communities more. You have some alpha groups you'll show up in more and so on. But how do you build those groups? It's hard. It's like catching lightning in a bottle, and we try our best to do that. So we have good infrastructure, of course. By that I mean just having the systems, the records in place to like accommodate members, their needs, their names, their roles, their contributions, everything that you need to like manage and reward as far as contributions are concerned. Incentive structures, core activity. Most teams do have a core activity. Let's say if you're a DeFi protocol, you'd be like, you know what, I need my users, my community members to come along, participate, use leverage, trade on chain, and then share a referral code with a friend. That's a core success metric for you. For many, it might be different. So identifying that, and lastly, community utility. I usually break it down into a few things. I think community utility comes down to access to networks, access to information, capital, resources. Whichever one you can provide the best, that's your mode. So, like I said, just value creation and adding to economy. We want to be able to build an ecosystem that lets you create value, and then you can create an economy around it. So that's exactly what we're doing with WPL. I won't go into details about this anymore, but because there's a lot more to cover. All right, so why do we need more talent on chain? The more talent there's on chain, the more sticky it is. Someone earning their first opportunity is much more sticky than someone participating on chain or gambling on chain. You could play on chain for once, let's say on a particular blockchain, and then leave it tomorrow because there's a better opportunity somewhere else. But if you start earning on a particular chain, it's much harder for you to leave. You're going to stick around because you've learned something that you can leverage with another team. And that's much more sticky, and that's our focus. So access to quality talent for ecosystem teams. Once you build out an ecosystem, our teams that are building on Starknet get access to quality talent, and they can participate, help build products, do a bunch of cool things. All right, what's WPL? Has a bunch of things. Like I said, you could go to WPL XYZ and find like an application form to start applying. It's an exclusive program. You get accepted based on a proof of work, but once you're in, you can participate and you can start earning points. Like I said, there's points allocation, there's tiered roles. So every role gets you a particular reward every single month. The leaderboard gets updated in real time. You'll see those rewards as well. And broadly, here's what it looks like. So every role has its own tier. So there's 1 to 13 tiers. So you start out with like a puppy role and go higher and higher in the wolf pack. And that's the theme we've gone with. Let's see if there's more. How do we do it? Can you go one slide back? All right, so we generally want to connect earning opportunities, reputation, and proof of work, and that's what we do. So if you go to this new platform that we've built, it'll go live pretty soon. You'll be able to access opportunities directly from the ecosystem. So we'll be posting bounties about various projects that you can build and work on, especially technical, but also non-technical opportunities. You could apply for those bounties. If they are technical in nature, then you'll be having an application process to go through. Once you receive approval to go and complete the bounty, you can go and participate and complete in milestones and receive rewards for the bounty. If it's an open bounty for, let's say, like writing an essay, doing a deep dive, doing a research piece, then you'll receive a reward as the winner of the bounty, whoever that is. So anyone can submit to that particular bounty process. And we connect all of it. We connect the bounty or a part of the reputation and as well as the proof of work. So you could technically have, like we do have this leaderboard. You could have this leaderboard where you can go search your name up and find information about yourself, the points you earned, the amount of money you earned. And if someone clicks on your profile, they'll find details about you. So if you ever want to share with people, hey, here's what I've done in Web3 or crypto as an ecosystem, here's what my contributions look like, just go ahead and shoot this link and let them type in your name and they'll find exact details about you on the platform itself. So you know it's verified, there's credibility around it, and it just adds up, it adds to your network. All right, like I said, it's all connected. So your proof of work, you can add information about yourself, your socials. You can add information about the projects you've done in the past that are outside the platform. So there's some connection over there. There's one place. It's almost like a resume, but there's some proof of work over there. And then lastly, you can wrap it all up by connecting your profile to the leaderboard. And in that case, all your bounties that you've done on the platform will show up with proof, with links, with Blockchain Explorer links for payments, all of that under one profile. So if anyone wants to go and double verify whether you've actually done a bounty and you've earned those prize pool, that prize pool amount, they could click on it, find the hash link, and just like check out if the money's been transferred to you. So that's verifiability for us. We'll do more on that front as far as points are concerned, incentivizing people are concerned, creating more programs for referrals, a bunch of cool things, but all of that is in V2. This should likely go live pretty soon, but you can anyway check it out right now. I would say go ahead, scan this, and then start applying to join the program. Once you're part of the program, you can wait for a bit, you'll receive an announcement or an email that says whether you've been approved or rejected, and then you can keep applying again and again, so there's no limit to that. But that's pretty much it. Thank you so much.
Thank you so much to you. Also, the fit though, I'm into it. Okay, I'm thrilled to be wrapping up for the day. I think we've had such, I would say, like in the best way, dense, like really, really informative educational content all throughout. So for those of you who've been sticking around online this entire time, shout out to you. I think, yeah, I hope that my comedic relief has been enjoyable. But I will see you all tomorrow for another full day of programming at 9:30 a.m. Is it Thailand time? I know in Vietnam it was called Indiana time or something like that. I was very surprised. It was not Vietnam time. In any case, have a lovely rest of your day. I hope you enjoyed the programming, and I look forward to seeing you all tomorrow. Yay! Should there be exit music, do you think?